question 5, the trigonometry section of this paper. And question 5 says 5.1, given that the square root of 13 sine x plus 3 is equal to 0, where x is an element of 90 to 270 degrees. Without a calculator, determine the value of the following. Okay, so we have to find the value of the following. So as you can see from the information that they give you, we have a trig diagram, okay, because it's really hinting at what x is and where x is and where our diagram is really. So let's go ahead and sort that part out first. We are given the square root of 13 sine x plus 3 is equal to 0. Okay, so with this, let us leave sine x on its own so that we can find out what sine is. So the square root of 13 sine x is equal to negative 3. And then we'll divide both sides by the square root of 13 to get sine x alone. So it means that sine x is just equal to negative 3 over the square root of 13. Okay, so now that we have this, we can use this to draw the diagram down. So with our diagram, let's figure out where exactly this terminal arm is going to lie. We are told that sine x is equal to negative 3 over the square root of 13. So sine is negative. So think about the quadrants where sine will be negative. Okay, so this is where all is positive, and then S, T, and C, right? So the places where sine is negative would be in tan and cos. But then this says that x is going to go from 90 degrees to 270 degrees. When you mark your angles, okay, starts at 0, 90, 180, 270, and then 360. So marking all the quadrants from 90 to 270 would be from 90 degrees to 270. So that is the second and the third quadrant. And so you're just going to pick the quadrant with the most ticks, which is the third quadrant. So our terminal arm lies in the third quadrant. Okay, so it will look like that. And then we just draw the arm. So it goes down, and then let's just put down what would be here. So this goes up to the x-axis, and it's always perpendicular to the x-axis. And the x that we're looking at, that angle, is drawn from here all the way to there. So that is x that we'll have. And we can put these down now. All we know is that sine of x is equal to negative 3 over the square root of 13. Now you know that sine is opposite over hypotenuse. So definitely a hypotenuse cannot be negative. So this negative is definitely going to go to the 3. So the opposite side, opposite of this angle, is going to be negative 3. So that's where the negative 3 goes. And then the hypotenuse is the square root of 13. So we only have to find the adjacent side. So let's go ahead and find it. So that is an x value. So we're saying, well, we can just call it something else just because we have x as the reference angle. So let's just call it a for adjacent. So a squared is equal to, and we're going to say, and we're going to take the hypotenuse squared, okay, and then minus by the other shorter side, which is negative 3 and squared. Okay, so a squared is equal to, that's 13 minus, that gives you 9. So 13 minus 9 gives you 4. So a squared is equal to 4. And then when you square root both sides, a is therefore equal to 2. So positive or negative 2 really, because it's the adjacent side. But based on the diagram, we'll be able to tell what it is. So do you see where this 2 is? It's going from this hand side all the way to this side. It is on the left hand side of the x-axis. So it's the negative part of it. So it means that this is actually negative 2 and not just 2. So a is equal to negative 2. And there we go. So we have all of this now. And now we can use the information that we have to answer the questions. The first question is to find sine 360 plus x. Okay, so sine 360 degrees plus x. This is one of those ones that confuse people. When you see plus x, then it kind of looks like the 360 minus x. It's not the same thing. So here's the thing with angles. If you have an angle and you notice that it is greater than 360 degrees, what you will do is subtract 360. So greater than 360, just subtract by 360 degrees, okay? And if you have an angle that is negative, okay, so negative angles less than 0, you will add 360 degrees, okay? So with this angle, you have 360 degrees plus x. You already have 360 degrees, and then you add in an angle to it. So it's going to be over 360. So just subtract 360 degrees from it. And that, if you subtract 360 degrees, it really just gives you sine x. So what is sine x? Well, we actually told, yes, we were. Sine x was -3 over the square root of 13. So that is our answer, and we're just going to put that down. So sine x is equal to -3 over the square root of 13. And that's our answer there. Okay, moving on to the next question. Okay, so the next question, 5.1.2, is we have to find the value of tan x. So with tan x, you just have to remember saw, ka, toa, with all of these really. And so tan is opposite over adjacent. So we're going to take the opposite over the adjacent side. The opposite side is -3, adjacent is -2. So you have -3 over -2, which really just gives you +3 over 2. And that is our answer there. Moving on to the next question. The next question is cos 180 degrees plus x. In your reduction, 180 degrees plus x appears in tan's quadrant. So it means that this would be reduced to negative cos x. And then you just have to find that. What is cos x? So cos is adjacent over hypotenuse. So we're taking the adjacent side over the hypotenuse. So -2 over the square root of 13. So remember, this negative is still there. And then -2 over the square root of 13, which just gives you +2 over the square root of 13. And there is our answer. Okay, so in these, I won't put them on the calculator because the calculator will rationalize the denominator. And you see that they said without using the calculator. So I'll just leave it like that. So that is it for question 5's first questions. And we move on to the next question. Question 5.2 says, determine the value of the following expression without using a calculator. So with this expression, we're just going to really do whatever we need to do on the expression. In the numerator, you have cos 90 degrees plus theta. That is cofunction. So we have to use cofunctions there. So the cofunction of cos 90 degrees plus theta, as shown on the screen right now, is negative sine theta. Okay, that's the only one that becomes negative, the one with the cos and plus. Okay, so we have that over, and our denominator, do you see what we have here? We have sine theta minus 180 degrees. Okay, you have a negative angle. The minute you see your angle is negative, overall this is actually negative because theta would be seen as an acute angle. And so if you take an acute minus 180, you're going to get a negative angle. So when you see the angle is negative, what should you do? You need to add 360 degrees to that. You don't even have to show them, you just show them the result of it. So this will now become, if you add 360 to negative 180, you're going to get a positive 180 degrees, and then plus theta. And then we have plus 3 sine, and we have negative theta. The angle here is negative, so what must you do? You need to add 360 degrees to it. So that's going to be 360 degrees minus theta. And now you can just go ahead and reduce. So it's equal to negative sine theta over, and let's reduce there. So that is in tan's quadrant. It's going to become negative sine theta. And then this is in cos's quadrant, but the function is sine. So that's going to become negative. But you see that you have a 3 here. So that negative that's supposed to go to the sine theta, right? You can put it in front of the 3 because it really just multiplies to the positive 3. So that becomes negative sine theta and multiplies, because it's next to it, to that positive 3. So it's giving you negative 3 sine theta. Okay, so whole lot of sine thetas. What we can do is leave negative sine theta on the numerator, but on the denominator, you don't have to take out a common factor because it's not really a common factor situation. These are like terms actually. It's negative sine theta minus 3 sine theta. It's like having negative x minus 3x, which is negative 4x. So in the same way, this is negative 4 sine theta. And now we can finally simplify this. So this is equal to, these will cancel, the sine theta and sine theta cancel. The negative and negative is gone. So what do you have on the numerator now? you have an invisible 1, because what happens is these are really just dividing by themselves, like sine theta divided by sine theta on the top and the bottom. Okay, so 1 over, and the denominator that's left is 4. So there we go. 1 over 4 is our answer there. And we move on to 5.3. The next question, 5.3, says, determine the general solution of the following equation. Okay, they've been very nice here. They factorized it for you. So you just have to solve. So since they factorized it, you have something times another thing gives you 0. Therefore, it means the first factor, cos x plus 2 sine x, is either equal to 0, or the second factor, 3 sine 2x minus 1, is equal to 0. Okay, so now we can just work on them. Okay, so let's go ahead and solve. So we're going to leave sine to sine x here is equal to, and when that goes over, it becomes negative cos x. Then we need to form tan, like we said. So to form tan, you're going to have to divide both hand sides by cos, because you want to make it sine over cos. So over cos x on both sides, because it's an equation. But here's something that we need to now take into account. You want tan x to be left here alone. Okay, tan x must be equal to some number. So 2 needs to go as well. So we might as well divide both sides by 2 as well. Okay, so this now is equal to tan x, because the 2's are gone. And then here the cos is gone, and you have negative and then over 2. So it's really negative 1 over 2 is equal to negative 1 over 2. And we just have to find the general solution for this. Now, with this equation, I have a video on this, and I show you how we can solve for these equations in a quicker way. Okay, that still gets you to the same answer. But please note that in the tan section, right, there's a place where I say plus 360 degrees, because I was still following the sine and the cos graph and how they go. It shouldn't be plus 360 degrees. Okay, it should be plus 180 degrees that you add, because the tan graph will repeat itself every 180 degrees. So for the sake of understanding, let's go ahead and use that quick method over here, and instead of the quadrant method, okay, so that you can understand what I mean by plus 180 degrees. Okay, so here's what we have. With a quick method, you don't have to consider whether your number is positive or negative. We don't care about that. All we're going to do is go ahead and find the reference angle, and we'll find it by taking tan over. So we'll say shift tan of negative a half. Okay, but we don't have to write that down. Okay, so shift tan and negative a half, shift tan of negative 1 over 2. And what do we get? We get a negative angle, which is fine. Negative 26 point. And I'll round off here. The reason I'm going to round off is because, do you see that this is tan of x? It's not tan of 2x. So I don't have to divide later on at the end of the day. So this is fine. We can leave it like this. And now we can go ahead and solve. So with your method, you'd probably think about the Cartesian plane and then say, where is tan negative? You know, but you wouldn't have even said shift tan of negative a half. You would have said shift tan of positive a half. With the quick method, you don't have to consider whether it's negative or positive. You just take it like that, okay? As negative if it's negative, positive if it's positive. But then you don't have to consider the Cartesian plane either. With a quick method, you just have to remember that for tan, it's always going to be theta is equal to whatever your reference angle is plus k of 180 degrees. And then if your angle is negative, okay, and this is what I made a mistake in that video. I followed the sine and the cos graph and how they work. If your angle is negative at the end of the day, all you will do to make it positive is add the angle that it takes to repeat itself, that graph takes to repeat itself. So in this case, we'll just add 180 degrees. Okay, so here our answer for x is equal to, and we'll say it is negative 26.57 degrees, but it's negative. So you want to make it positive so that it looks like the answer that the memo will give you. Okay, so plus you would say 180 degrees, and then because this is a general solution, we'll say plus k of 180 degrees. Okay, I'll tell them where k is an element of integers at the end. Okay, we can tell them k is an element of integers here just so that we don't forget. Okay, so let's just solve for that. What is 180 degrees plus that? Just take this answer and then add 180 degrees to it. And that's all. So the answer is x is equal to 153.43 degrees plus k of 180 degrees. And that's really all you have to do. Now I know with yours, you would have two solutions. But the thing is, the second solution does not need to be there. The solution with a bigger value, it doesn't have to be there. Here's why. It's because of the way the tan graph works. With the tan graph, okay, it goes up, then it's an asymptote, and then it goes like that, and then it just continues doing that, okay? It goes up again, asymptote, and then continues like that, okay? So this would be at 180 degrees. This graph will repeat itself every 180 degrees. So you don't actually have to rewrite that second case scenario. The second case scenario would have been, let's just pretend this was positive, because it's just going to make more sense if we pretend this was positive. Here's what I mean by this. The reason you don't have to write the second solution. Remember that in the first quadrant you have theta. And what we've really just done is written down the reduction for theta. We just said x is equal to whatever our answer is plus k of 180 degrees. The only reason we added 180 degrees here was just to make it positive so that it looks like the answer that we would have, for example, in the memo. But the other place that tan is positive is here in 180 degrees plus theta. Okay, so you took already what your reference angle was, and then they're just adding 180 degrees to it. So your second answer would be 153.43 plus 180 degrees. It will look like this, like that, with that number. But here's the thing, it is not really necessary. You can put it down if you want to, but it's really not necessary. And the reason I say so is because this graph will repeat itself every 180 degrees. You've already said that with k. So you now take in this and then also putting down this answer of 333 degrees is a little redundant. It's just a little repetitive because of course it's going to at some point equal 333 degrees. We're adding 180 degrees every time. That's why we have k of 180 degrees. So this is the general solution. You don't need the other one with tan only. Okay, and it's really just because of the way the tan graph looks like that. Okay, and just adds 180 degrees every time. With the cos and the sine graph, they're a little different. Okay, for example, the cos graph that looks like that, you see there is that bump where you have two solutions within one specific interval of k. For example, let's say k was equal to 1. You can actually have two solutions in that interval. Unlike the tan graph, okay, when you get an answer here, the next answer is just whatever that is 180 degrees later. Done. So this answer is just going to repeat itself, so you don't really need that. Okay, so that is it for that part. We're not yet done, so I have to solve for the other equation. So this is the second equation that we have. Let's go ahead and solve. We need to solve for x. So we've got 3 sine of 2x minus 1. So we can say 3 sine 2x is equal to 1. Then divide both hand sides by 3 to get sine 2x on its own. And this is equal to 1 over 3. And then now we can find our reference angle. So with this one, be careful because you have 2x, meaning whatever x is, you're going to have to divide by 2 at the end of the day. So let's go ahead and find the reference angle. What is shift sine 1 over 3? So we'll say shift sine of 1 over 3. And you see what it gives us. So we'll keep that answer. And it is 19.47. Okay, so your answer and your work in here is really just going to be like mine as well. With the quick method, when it is sine, all you remember is that your answer for theta is going to be whatever your reference angle is. And then you're going to say plus k of 360 degrees, and that's the first solution. And then the second solution would be 180 degrees minus whatever your reference angle is, plus k 360 degrees. And then you don't even bother on whether it's positive or negative. You just stick with that as the solution. So you can watch that video to see what I mean by that. Okay, Now, with this, there is no need to round off. I don't know why I'm rounding off. Shouldn't be rounded off. So I'm just going to leave it as 4712, just so that it shows that I have not rounded off yet. We'll hold on to that. Let's go ahead and solve for our angle. So first we solve for the angle before we actually get to x. The angle that we have is 2x. So we're saying that 2x is equal to, again, you're going to just say your reference angle, which is currently 19.4712, and then you just say plus k of the amount of angles that it takes for this graph to repeat itself. The sine graph repeats itself every 360 degrees. So plus k of 360 degrees. Of course, where k is an element of integers. We can just write it for both, it's fine. Okay, so that, or, okay, so I'm just going to put the second solution. So 2x is equal to, and then you'll take 180 degrees minus your reference angle, which is 19.4712, and then plus k of 360 degrees. Okay, so let's go ahead and solve for the first one. You see, with this, all you have to do is finally solve for x. So you see the 2 is in the way. We need to divide both hand sides by 2. And so therefore, x here is equal to this answer divided by 2. Okay, which gives you 9 points, and now you can round off. So this is going to be 9.74 degrees. So 9.74 degrees plus k of 360 divided by 2 is 180 degrees. Okay, so we're done with that one. Then we're here. So you first have to say 180 degrees minus the 19.47. So you can remove that 2 so that you have this, and then say 180 degrees minus that number. Okay, shift sign of 1 over 3, because that is the 19.47 that we have there. So 2x, first of all, is equal to, we're just solving for that first. It's 160.528. Again, I'm not rounding off yet. Then I still say plus k of 360 degrees. And now we can divide. So divide both hand sides by 2 to get rid of the 2. Therefore, x is equal to, and we're going to take that whole answer, right? And you're going to say the answer divided by, you can use the answer button. You press AC and then say answer divided by 2. And our answer is 180 points. And now we can round off 26 degrees. Okay, and again here, that 360 divides by 2 to give you k of 180 degrees. Okay, where k is an element of integers there. And there, of course, as well. So those are our solutions. Okay, so our solutions are this, this, and finally this. Okay, so that is the general solution. Moving on to the next question. We are on 5.4, and it says, given the identity cos x plus y multiplied by cos x minus y is equal to 1 minus sine squared x minus sine squared y. And we have to prove this identity. Okay, so deciding on the hand side that we're going to use, you see that with the left hand side, we can actually expand here. Okay, and then these are still multiplying. So we're definitely going to use the left hand side. With the right hand side, there's not much that you can actually simplify. I mean, you can. It's just really not going to make that big of a difference. Okay, we are going with the left hand side, and we're just going to rewrite it first. Okay, so with the left hand side, we'll say it's equal to, and you see that these two are multiplied. But we can use compound angles to expand that. So that's going to be cos x cos y, and then because it's a plus, it changes to a minus sine x sine y. And then this gets multiplied by, since we have two terms, we can just multiply using brackets. This gets multiplied by this, which is going to be cos x cos y, and because it's a minus, it becomes a plus here, and we have sine x sine y. Okay, so they're multiplying, so we have to FOIL it out. Definitely something is going to cancel because they're exactly the same, as you can see, but we have a minus and a plus. So you're going to have a term, two terms that will cancel. But let's go ahead and multiply. If you multiply the first term with the first term, you're going to get cos squared x, cos squared y, and then that's it. And then the first term with the second term, As you can see, nothing there is the same. So it's just going to be, I'll start with the sign. So plus, let's just put it, that's probably the thing that's going to cancel because it's positive and then it's negative. Okay, so positive sine x sine y, and then we're multiplying this by, and then we're multiplying by that. That's cos x cos y. Okay, and then it's these two that multiply. Okay, again, so that's minus sine x sine y cos x cos y. As you can see, they're exactly the same, but just the positive and the negative. And then the last terms would be these two that multiply, which gives you negative sine squared x sine squared y. Okay, so these two are going to cancel, and then we are left with cos squared x cos squared y minus sine squared x sine squared y. Okay, so now that we have this, we can compare it to what it should be equal to. Let's just see what we need to simplify. Okay, so when we compare these two together, right, this and this has three terms, 1, 2, and 3, right? And this has two terms only. But I see a sine squared and a sine squared x and a sine squared y. However, it's not really the same type right now because these two are actually together. But let's try to leave them. Let's just leave them. This is really just a trial and error thing at this point. And now, to be able to get a 1, you probably had the identity sine, squared x plus cos squared x, or it may even be sine squared y plus cos squared y. But we can't force it to be there. So here's what we can do. We can change any of these two so that we can, create 3 terms, because it's 2 terms right now. It should be more than 1. So with these, right, cos squared y and cos squared x, they can create 2 terms. Remember the identity sine squared x plus cos squared x, that this is equal to 1, okay, because it's a sine and cos. So with this, you can change cos squared x into 1 minus sine squared x. So that's what I'm going to do. I'm going to go ahead and change cos squared x. So change that, and now it is 1 minus sine squared x. But then remember that this is still being multiplied to this. So you see, you have 2 terms here now. That's great, because when it multiplies with this one, you're now going to have 2 separate terms here, and then this is the 3rd term. But let's just see how it works out. So cos squared y, then minus sine squared x times sine squared y. Okay, so we'll have to distribute here. So 1 times that stays exactly the same. So it's cos squared y, then times that is negative sine squared x cos squared y, and then this stays exactly the same. Now it's starting to actually look okay, like we can actually do something here with this. So we have 3 terms, great, but we need to have this at the end of the day. So it needs to have a separate sine squared x and a separate sine squared y. Now look at these two. If you group them together, do you see they have something in common? So we still have cos squared y, but these two, they have negative sine squared x in common. Then you'll be left with the cos squared y and the sine squared y, which can add up and give you 1. So that gives you negative. We have minus sine squared x. Then open bracket, what is left here? Okay, you took out the negative sine squared x, so you only have cos squared y left. Same thing here, you took out a negative. Okay, so when you divide, that negative is now gone, and you're left with positive sine squared y. Okay, these together give you 1, so you can rewrite them, and then in place of cos squared y plus sine squared y, we can say that that is equal to 1. So this gives us 1. Okay, so it just stays exactly the same. So really all we have is cos squared y minus sine squared x. Okay, how can we get this to look like this? We're not that far off anymore. Because do you see that this has 3 terms, and one of the terms that it has is minus sine squared x, which is also what we have, minus sine squared x. So the other term is 1 minus sine squared y. You have a cos squared y here, so you can change that using the identity of cos squared y. The identity of cos squared y would be 1 minus sine squared y. And then you have minus sine squared y. And that's actually how we get that. So you see, it is 1 minus sine squared x minus sine squared y. And if you like, you can just put them in the same order. 1 minus sine squared x minus sine squared y, which is therefore equal to the right hand side. So there we go. So it was just distribute, cancel where it needed to cancel, and then change one of those to the identities. Okay, you could have also changed this one as well, so it probably just worked out the same way. So that is that answer. Moving on to the next question. The next question, 5.4.2 says, hence determine the value of 1 minus, okay, so same thing that they gave us, right? 45 degrees minus sine squared 15 degrees. Okay, so you see it's in the same format. So if this, right, was the identity for this, then it means that you can just put that in place of it. Okay, so this would also be equal to, you're kind of going to view the 45 degrees as your x and that as your y. So this is the x, this is the y. So if this was equal to the right hand side, you can make it equal to the left hand side, because without using a calculator, you can't really just substitute. It's not going to work. So let's use the left hand side. The left hand side looked like this. We're just going to substitute in place of x and y, and we'll be able to find this. So since we knew about that, right, it means that this one is actually equal to cos, and in place of x, we're going to say 45 degrees, and then plus y, which is 15 degrees. So plus 15 degrees, and then multiply by cos of 45 degrees, again, minus 15 degrees, minus 15 degrees. Okay, let's go ahead and simplify. So with this, you don't have to use compound angles, because you see these are special angles already. 45 degrees plus 15 degrees is 60 degrees. What is cos 60 degrees? Okay, multiplied by 45 minus 15 is 30, so cos 30 degrees. Okay, so we can actually find this. Cos of 60 degrees using the circle, the triangles, or using the OHA rule, which I have explained before. Okay, cos of 60 degrees will be, so I can just put down the OHA rule here so that you guys can remember. So it goes like this, OHA, and then you say 30 degrees, 60 degrees, and 45 degrees. You use this when, you know, you're not supposed to use a calculator, because they would know. But in this one, they wouldn't, because they're using safe angles like 30 and 60, okay? I'm just trying to remind you of how this rule looks. So 30, 60, 45, OHA, and then you say 1, 2, 3, 3, 2, 1, and 1, 2, 1. Then in each row, you're going to square root the biggest number. So the biggest number here is 3, biggest number here is 3, biggest number here is 2. And so to find cos 60, remember that cos is ka in SOHCAHTOA, so it's adjacent over hypotenuse. We're going to go to 60 degrees and take the adjacent over the hypotenuse, and that's how we know it's a half. Then multiply by cos of 30 degrees. So again, it's ka adjacent over hypotenuse is going to be adjacent over hypotenuse, which is root 3 over 2. And so if you multiply these together, that's going to give you root 3 over 4. And there we go. So that's our answer. So that's what I mean by these are the safe ones. You wouldn't need the OHA rule for this. If you use the calculator, nobody would have known. Okay, but it's good to keep these, you know, for situations where you're not allowed to use a calculator at all. Okay, so that is it for that question. And then we move on to question 5.5. Okay, 5.5 says, consider the trigonometric expression, and we are given, so might as well just rewrite. They say rewrite the expression as a single trigonometric ratio. Okay, so we have 16 sine x times cos cubed x, okay? Things that we don't really want to be there, but we'll take them out. So 8 sine x cos x. So the first thing that we already see is that we have two terms. And since we have two terms, and that's really just it, we can factorize this. The first type of factorization we can perform on this is taking out a common factor. So what is the highest common factor between these two terms? Well, with the 16 and the 8, it is 8. With the sine x and sine x, it's just sine x. And with the cos cubed x and the cos x, it's cos x. And what is left? That's going to be, when those divide, it's 2. Those divide, they cancel. And when these divide, it is cos squared x. And with this one, it's just minus 1 because it's the exact same thing. Okay, let's see how we can take this further. So I know this is a double angle, so we can change that to cos 2x. And then this one. Okay, this one is a double angle if we write it correctly. So look at how we can rewrite this. So you're going to separate the 2 from the 8. So 8 divided by 2 is 4. So you're going to have 4 multiplied by 2 sine x cos x. And then you see how they'll change. So this one will change to cos 2x. And this one, as you can see, that is a double angle expansion for sine 2x. So this is equal to 4 multiplied by sine 2x times cos 2x. Okay, so you see what we have now. Now, do you see that these are in the form of sine of an angle, cos of an angle? That's again double angles because you have the exact same angle. So we could break that 4 apart into 2 multiplied by 2. So what you have is 2 times 2 sine 2x cos 2x. Okay, we've expanded it to that. And so because of that, you see that this is the same thing as sine 2 sine a cos a, right? So that is double angles that we're going to use to simplify that. It is going to be sine 2a. But our 2a is 2x. Our a this time is 2x. So this is equal to 2 multiplied by, and this is sine 2 times 2x, which is 4x. And yeah, that's what it gets to. 2 sine 4x. And that is our answer. Okay, simplified to a trig ratio, and that is it. Moving on to the last question in question 5. Okay, the last question for question 5 says, for which value of x in the interval where x is an element of 0 to 90 degrees will 16 sine x cos, okay, yeah. So where will that have its minimum value? Okay, we must think about this question carefully, because do you see that this, right, it's simplified to 2 sine 4x. So you have to think about what that graph would look like. The normal graph, right, the original graph, y is equal to sine x, it goes from 0 to 180 degrees. Now, they say from 0 to 90 degrees. We're going to have to understand what that means for this graph. So the original graph goes from 0 to 180 degrees. But now because the graph is y is equal to sine 2 sine 4x, right? Because that's your graph now. You're going to have to think about what that 4 does to this graph. The 4 is going to make your graph more narrow, okay? So it's not going to finish a cycle now in 360 degrees anymore. It's going to finish a cycle in 360 degrees divided by 4, which is in 90 degrees, which makes perfect sense. That's why they said where x is an element of 0 to 90 degrees. So you're still going to have a full sine graph, right? Where the maximum, because you see that 2 is the coefficient of sine, right? The maximum is 2 and the minimum is negative 2. But now these angles are a little different. Your new period is 90 degrees. That's why they said x is an element of 0 to 90 degrees, because it's going from 0 now to 90 degrees. It will finish one cycle like that. What they're asking us for is for which values of x, right, in that interval will this graph have a minimum value. So where is the minimum value? What is the x value that belongs to that minimum value in this graph right now? We can see that there's a maximum here, and so this makes this a minimum. Think about what all the angles are doing. You know now that they're all going to divide by 4. So what happens here is before, right, when we didn't have this 4 here, the normal sine graph, at this point where it's equal to -2 or -1 actually, because that's the original sine graph, the x value over here would have been 270 degrees. That's what it would have been, okay, because of the way it usually goes. It goes 0, then this is 90 degrees at 1, and then 180 degrees at 0, 270 degrees at -1, which is -2 right now, of course, because of that 2 that's been put in front of the sine, and then 360 degrees here, okay? So all these angles, all the answers that you used to have, they are just going to be divided by 4. So it's 270 degrees divided by 4, and that's where that minimum is going to happen. So you can tell them that the minimum x value is that x is equal to, and just show them it's 270 degrees divided by 4, and then we just find out what exactly that is, which, as we can see, is 67.5 degrees. So that is at 67.5 degrees. That's what that minimum is going to be, the x value, that minimum. Okay, so there we go. As you can see, that's a 1-mark question. It's not something that we had to do that for. I just put the graph so that I could explain that. Okay, so that is it for question 5. And then we move on to question 6 with more trigonometry. We are now on question 6, and question 6 says, in the diagram below, the graphs of f of x is equal to tan of x and g of x is equal to 2 sine 2x are drawn for the interval where x is an element of -180 degrees to 180 degrees. Then they tell us that A, 60 degrees and K, which is over there, and B are 2 points of intersection of the graph of F and G, as we can see. Okay, so the first question is to write down the period of G. Okay, so to find the period of a graph, you're always just going to think about what the original period would have been if it was not manipulated in any way. So the graph of G, when we look at that, you can see that it's a sine graph because it's 2 sine 2x, right? So think about what the original sine graph's period is. The original sine graph, this graph, it has a period of 360 degrees because it takes 360 degrees to complete one cycle. So every time it repeats this same pattern again, it's just completing another cycle. Okay, so that's another cycle that it completed. So the original sine graph takes 360 degrees to complete a cycle, and then you're going to take that amount and you're going to divide it by whatever is in front of your angle, because that is what is going to alter the period. That's what's going to change the period. So the number in front of x is 2. So we're going to divide this by 2. So if you divide that by 2, it gives you 180 degrees. So it means that this graph's period is 180 degrees, and that would be our answer. Moving on to the next question. The next question, 6.2.1, says calculate the value of k. Okay, so where is k? K is over here. So if this is k, okay, this is not a complicated one. You see that they gave you your graphs. They didn't hide anything in the graph. So to find this, you can already see that the x value is 60 degrees. Since this is A, because it can't be this is 90 degrees. So since this is A, just substitute the x value of 60 degrees to find the y value, which would be k's value. So substitute it in any of these graphs because this is a point of intersection. So we can use the tan graph because it's easier. You can simply just tell them that k would be found by saying tan of 60 degrees. And then find out what tan of 60 degrees is. Okay, so k is equal to, and tan of 60 is the square root of 3. So that is our answer. K is equal to square root of 3. Moving on to the next question. Next question, 6.2.2, says calculate the coordinates of B. So B is over here. Okay, so this is how you need to be looking at these graphs and just seeing how they repeat themselves. You see, with this first graph, this sine graph, right, g of x is equal to 2 sine 2x, you can see that we know now that this graph will complete a cycle within 180 degrees since the period has been changed. So we know that this is one cycle, right? And here it's completing another cycle, also in 180 degrees. So how we would find B is by actually looking at where B is. Do you see that over here, right, where we had this? because these two graphs intersect here, where in the positive part of where y is positive, really, they're going to intersect again 180 degrees before this, and that's over here. So to find out what exactly that point is, do you see that if it's 180 degrees before this, the only thing changing, we are moving to the left, the only thing changing is the x value. That y value is going to stay exactly the same. So we already know it's the square root of 3. So it means that this will just be 180 degrees backwards, which is minus 180 degrees. So you take it from where it is, it's at 60 degrees, and you say minus 180 degrees, and you'll find that. Okay, so that's all we're going to do there. What is 60 degrees minus 180 degrees? And that is negative 120 degrees. So it means that point B is actually negative 120 degrees, and the K value was square root of 3. So that is our point, negative 120 degrees and square root of 3. And see, that makes perfect sense. Negative 90, negative 120, and then negative 180. Okay, so we know what these points are. We know this is square root of 3 as well. Okay, so that is it for that question, and we move on to the next question. The next question, 6.3, says write down the range of 2g of x. Okay, so they are already changing it. So think about what g of x already is. G of x, they told us, was equal to 2 sine 2x. But now they put in a 2 in front of that. So that just gets multiplied by 2. So 2g of x is times 2, which is 4 sine 2x. Okay, so the range, think about what the range of the normal sine graph is. Normal sine graph, despite the fact that the period has been changed, the sine graph always goes from, or the highest point it will reach normally is 1, and then the lowest point is negative 1. So because the coefficient of sine, right, is now 4, it means it's going to go up to 4, and the lowest would be negative 4. So it's y is an element of, and you see, because it goes up to 4, so the lowest value would be negative 4 and the highest would be 4. And of course, we're using square brackets because at these points, at these y values, negative 4 and 4, you're going to have actual points that have these y values. So we use square brackets. So that is the answer over there. You could have also chosen to write this in set builder. So there you will say y is greater than or equal to negative 4, because that's really what it's doing. It's going from negative 4 to positive 4. So the lowest value is negative 4, meaning y is greater than or equal to negative 4, but less than or equal to 4. So that's another way that you could have written that. So that is the answer to that question. Moving on to the next question. We're on 6.4, and 6.4 says, for which values of x will g of x plus 5 degrees minus f of x plus 5 degrees be less than or equal to 0 in the interval where x is an element of negative 90 degrees to 0 degrees? Okay, let's break this down. First of all, let's take the inequality they gave us. You see that they're saying g of x minus f of x must be less than or equal to 0. It would be complicated to have to think about it like that, like trying to take g of x minus f of x and then trying to see, is that space going to be less than or equal to 0? Okay, so what we're going to do is rather take that equation and we will take negative f of x plus 5 degrees over to make it positive. So what we have is g of x plus 5 degrees and then is less than or equal to positive f of x plus 5 degrees. Okay, so that looks simpler now. So we can just focus on where the graph of g is less than or equal to the graph of f. I see that we have plus 5 degrees, but let's consider that at the end to not complicate things. Okay, so we also know that this should be within the interval of negative 90 to 0 degrees. Okay, so let's go ahead and look at this graph. Okay, so right now we don't really need these colors anymore. When we are looking for where g of x, right, because we're just really looking for where g of x would be less than or equal to f of x. We're not really considering the 5 degrees yet. Let's look at it like this. So when you're asking yourself this question, because you can see that g of x is less than or equal to f of x, what you should be looking for is where the graph of g is below the graph of f. Of course, within that interval they spoke about. They told us that the interval was between negative 90 to 0 degrees. So we're only going to look within this interval. So within this interval, where is G, the graph of G, lower than the graph of F? You see that over here, the graph of G is higher than the graph of F, all through here, right? And then they intersect at this point. Then the graph of G is now below the graph of F. And that's what we're looking for. We're looking for this place, this. Okay, and we're going to tell them exactly what the X value is. And then, of course, after that, it becomes above the graph of F. But that doesn't matter because we're looking within this interval. Okay, so to be able to actually find this, because we know it is now, it's just find what exactly this is, and we'll know that this is happening between this degrees all the way to that degrees. Okay, we will still apply the 5 degrees shift that we saw. So let's find out what exactly this is. What is that? Okay, so you have to think about how the sine graph behaves and the tan graph really. So with these graphs, they're very repetitive. They do the exact same thing over and over again. If you look at the sine graph on this side, do you see that from 0 degrees all the way to this point over here, okay, that it is 60 degrees. And this is a significant point because at this point, this is the point where the graph of F intersects the graph of G. Now, if you look on the left-hand side, do you see that the graph of F and the graph of G intersect again? So remember, these graphs are symmetrical, right? The way they behave, they really just do the exact same thing. So meaning, you see this part, right? This part, it's doing the exact same thing as this part. If you just took this and you turned it around, it would fit perfectly on this. So we can do that. You see, if you take this and we turn it around and then you put it here, do you see that it's going to fit perfectly on this? So that would mean that when this line, right, that we drew, when it was originally here, it went from 0 degrees and it took exactly 60 degrees later for it to intersect with the graph of F. So if we were moving to the left, how much degrees would we have to move for it to intersect again with the graph of F? It would also be 60 degrees. So if you move 60 degrees to the left, it's going to intersect with the graph of F over there. So that's what's going on there. This happens at negative 60 degrees on this current graph that we have here. Okay, so now we know what exactly that point is. And now we know that for this, right, not considering the 5 degree shift yet, now looking at this, we know that this is going to happen where g of x is going to be less than or equal to f of x. It's going to happen where x is greater than, because you see that it happens all through here. This is where the graph of g is below the graph of f. So this is where x is greater than or equal to, because we have to consider equal to as well, negative 60 degrees, but less than or equal to 0 degrees. And of course, they intersect again at 0. So that would solve this question. But our question specifically said g of x plus 5 degrees is less than or equal to f of x plus 5 degrees. So we have to consider that shift. So you see a plus and then it's adding to an x value. When you're adding to an x value, you're actually shifting to the left, not the right. When we're minusing from an x value, then we are shifting to the right. So it really just means that this answer that we had, or really these graphs that we have here, they would have been shifted to the left by 5 degrees. So this wouldn't be negative 60 degrees anymore. It would be negative 60 degrees and then move 5 degrees to the left, which would be negative 65 degrees. And this wouldn't be 0 anymore. It would be 0 degrees, but go 5 degrees to the left, which is negative 5 degrees. So really, these graphs, they would just shift from where they currently are. So all we're going to do is replace the negative 60 and the 0 degrees. So that means our answer would be x needs to be greater or equal to negative 65 degrees, but less than or equal to negative 5 degrees. And that is our answer. Okay, so that is it for that question. And we move on to the next question. Okay, 6.5 says, determine the values of p for which sine x times cos x is equal to p will have exactly 2 real roots in the interval, negative 180 degrees to positive 180 degrees. Okay, since we know which interval it's from, and well, you just know that they're not going to give you a brand new graph, okay? So this graph definitely relates to something that you already had. And already looking at sine x cos x, it probably has to do with the graph of g, because remember that g of x is equal to 2 sine 2x, right? And as you can see from that sine 2x, that is double angles that we have there. So we can expand that using the correct double angle expansion for that. Okay, so we can start from there. So that is going to be, we have g of x is equal to, and this is 2 first outside, but then this, the expansion for that is 2 sine x cos x. So do you see now that what we have is 4 sine x cos x? Okay, a lot like what they have, but they have is equal to p. Okay, so we know that they're using the graph of g, and they want us to have exactly 2 real roots within that interval. So from negative 180 to positive 180. If you look at this graph right now, okay, remember when you're trying to find the roots, you're trying to find the x-intercepts, okay? So make y equal to 0. So we can really just look at this as 0 is equal to, and then we have this so long. So let's try to understand how they can have exactly 2 real roots by looking at the amount of roots that they currently have. So the graph, remember, we're only focusing on the graph of g, the sine graph. So that is this graph. We can just highlight it so we can control it. We needed to have 2 real roots, exactly 2 roots. So count the amount of x-intercepts that you have. How many roots do you have? It has an x-intercept over there, 1, 2, 3, 4, and 5, okay? Intersects the x-axis 5 times. We want it to intersect only twice. So let's think about how this graph should be shifted. You can shift it, of course, if you shift it left or right, it's not going to change anything. It still has the same amount of intercepts, okay, x-intercepts. However, if you shift it up, look at what happens. If you shift it up to the point where the minimum values, right, where that minimum is supposed to be, is sitting on the x-axis, then you have exactly 2 x-intercepts. You have 1 over here and 1 over here. Done. And that's what they want. Okay, now, as you can see, that's not the only way that we can do that. We can either shift it up, or if it was still exactly where it was, what we could do is shift it down. So shift it down until it hits the x-axis like that. And then it has 2 x-intercepts as well. So you can see that there are 2 options, but now we have to find out how far we're shifting it. When it was here initially, how far did you shift it so that it can look like this? We can actually see how far we need to shift it. So thinking about what the lowest values were, you see that the minimum here, right, because this is 2 sine 2x, meaning the lowest it's going to reach is negative 2, and the highest it will reach would be 2. Okay, so that is the original graph. The highest it will be 2. So it means that for you to have shifted it from where it was to get it to this point, this is shifting it up first, you must have moved it, okay, it's from negative 2, and then now you moved it until that is no longer at negative 2, but is at 0. So you shifted it 2 units up. Okay, so we know that moves 2 units up. And of course, when we're looking at the graph, shifting it down also works, right? So if it was here originally, and you needed to move it down, you would shift it how many units down so that it can have exactly 2 roots. You would shift it exactly 2 units down, since the highest is at 2 and you want that highest to now sit on the x-axis to be at 0. So you moved it from 2 to 0, meaning 2 units down. So we know exactly how we need to shift these graphs. Okay, so remember how we still have this? So what I'm saying is we're going to shift those graphs 2 units up or 2 units down, and it should work out fine. So we're taking the graph that is the original g of x, it just looks like this right now, for sine x cos x, and if you shift it 2 units up, this will help it to have 2 x-intercepts. So you'll see how this will act as the p-value. So we're still focused on this equation, but shifting it 2 units up. Or the second option is to take this graph for sine x cos x and then shift it down by 2 units. Minus 2 is equal to 0. And now we can just solve. So at the end of the day, we need to find out what p is. So get the equation to look like this. Sine x cos x. Okay, right now it's 4 sine x cos x and then plus 2. So let's just simplify. We can take the 2 over. So that's 4 sine x cos x is equal to negative 2. Then divide both hand sides by 4 to get rid of that 4 because you need it to be sine x cos x. So right now we have sine x cos x is equal to negative 1 over 2. Or, and then over here we have 4 sine x cos x is equal to 2. And then divide both hand sides by 4 to get rid of the 4. And then sine x cos x is equal to positive a half. Do you see the two values of p, or that p can be, for them to have exactly 2 roots? So p should either be equal to negative a half or p should be equal to positive a half. And that is our answer. Okay, so that is it for the graph section of trigonometry. And then we go on to 2 and 3D trigonometry, which is in question 7. So we are on the last section of this paper. And it's the last section because the Euclidean geometry section is already uploaded. So I'm just going to compile them into a playlist so that the November 2022 grade 12 exam paper 2 is there. Okay, so we are on question 7, which is the 2 and 3D trigonometry section of this paper. And this is what we have. Question 7, AB is a vertical flagpole that is the square root of 5p meters long. So these are all in meters. Then they tell us that AC and AD are 2 cables anchoring the flagpole. Okay. B, C, and D are in the same horizontal plane. And then we are told that BD, as we can see, is 2p meters. And angle ACD is x. And lastly, angle ADC is 45 degrees, like we can see over there. Okay, so the first question is to determine the length of AD in terms of P. Okay, so let's just see where AD is. AD is over here. So if this is AD, how do we find the length of this? Well, you see that we have a right angle triangle. We don't have any angle in here because you see this 45 degrees here. It doesn't belong to this angle. It's this angle. So all we have right now is a right angle triangle. Do you see that in this right angle triangle, we have been given this side AB and this side 2P. So we can clearly use Pythagoras. So we can use the theorem of Pythagoras to find AD. Okay, let's go ahead and do that. Okay, so our formula is going to be AD squared is equal to, and we're going to take that shorter side squared, so that is 5p. We're going to just say 5 square root of p and then square that. And because it's the longer side, you're going to add the 2 other shorter sides. So that's 2p squared. So 2p, and we of course square it. Okay, so let's just go ahead and solve for AD. So AD squared is equal to, this would give us, sorry about that, that is not 5p, that is square root of 5p. Okay, so this would give us, if you square a square root, it breaks open, and so you have 5 and p squared plus 4 and p squared. So these are like terms, we can add them together, meaning AD is equal to 9p squared. Okay, so to find AD, we square root both sides, and therefore AD is equal to 3p. And there we go. Okay, so that is the first question. Moving on to the next question. The next question, 7.2, says, show that the length of CD is this. Okay, notice that there are only x's in here, but we'll just see. We'll see how we can come about that. Okay, so remember that we just found AD, right? So we should put that down. That would probably be helpful. So that's 3p. And they want us to find CD. Now, CD is over here. How can we find this length? Well, clearly we can't find it using this bottom triangle because we have literally no information here, nothing here. So that is already out of the picture. So what else can we use to find CD? Well, we can use this triangle. So in this triangle, what we just found is this AD. We found what AD is. And the other thing that we know in this triangle are some angles. So we've got the angle X. We've also got the angle 45 degrees. So that's very helpful. So what rule can we actually apply to this to find CD? This looks like the sine rule, okay? So with the sine rule, if you're looking for a side, then you need to have the angle opposite that side present. So right now we don't have anything, but we can actually find this because we've got X and we've got 45 degrees. So we can actually find that. Okay, so we're going to use that to find that angle, angle A, and then what or which angle and side can we pair up to use to find CD? Do you see that we have in this triangle this X, right? This is what we already have. We don't have to look for that. It has a value, X. And you see that opposite the X, you've got 3P. So those are the sides we can use. We can use AD and we can use the angle opposite AD. And then, of course, we can use CD because we have to. It's what we're looking for. And then we can use the angle opposite CD. Okay, let's go ahead and do that. Okay, so of course, doing that, you see that the only thing that was missing was this. So we need to find this. Okay, we can. It's a triangle, and you know that the interior angles of a triangle add up to 180 degrees. So to find this angle, we'll just say 180 degrees minus X and minus 45 degrees. Okay, so that's what we can do. We can start off with angle A and say this is equal to 180 degrees minus, we can just say 45 degrees minus X. And so this is going to be 135 degrees minus X. That's what A is. So we can put that down. That is 135 degrees minus X. Okay, now we can go ahead and use the sine rule. So we're looking for CD. And so we're going to take CD over sine of this angle. And then you also have, because you started with a side and then an angle, you need to also start with a side and angle for the next pair. So we will take AD, which is 3P currently, over sine of that angle. And that will be the sine rule. Okay, let's go ahead and put that down. So we are saying first CD over sine of the angle we just found, 135 degrees minus X. And then this is equal to AD, which is 3P, over sine of that angle X. Okay, and all we have to do now is make CD the subject. So you see that to make CD the subject, you can just get rid of this denominator. So to get rid of that, we can just use the multiplicative inverse. Okay, so you're just multiplying both sides by sine 135 degrees minus X to get rid of that. So it's an equation. What you do on the one side, you must do on the other side. So now that that's done, these two cancel and you're left with CD is equal to, and on the numerator, we have 3P times sine 135 degrees minus X all over sine X. Okay, so this is what we have. And let's just see. Okay, it doesn't really look like what we have yet. So there's clearly some more simplifying that we need to do. But you see that we are on the right track because you see we have sine X, we've got sine X as well. We've got 3P here, we also have 3P here. So we just need to simplify that. That's all. Okay, let's see. We can actually break this up. So you see we have CD is equal to 3P. Okay, so when looking at the angle 135 degrees, it is not over 360 degrees. So, you're not trying to get it back to that. However, we can reduce it. Okay, so you can reduce it. But straight away, we could already see that this angle has 90 degrees in it and then an acute angle. Here's what I mean. So we can break it up. We can say this is equal to 3P and we have sine. And now what this is if you break it up into 90 degrees and the other angle that you have, you're going to have 90 degrees plus what angle gives you 135 degrees plus 45 degrees. Okay, so remember, we are not changing anything. We are just changing the way it looks, but it still has the same value. Okay, 90 plus 45 is 135, and then minus x. So we can actually use cofunctions here. If we group these two together like that, so grouping those together, we can use cofunctions, and it's possible to do so because you see we have a plus sign. There's no confusion with that. Okay, so we're just grouping those together. So over, and we have sine x. And then CD is equal to, we have 3p. And then with this, you see, this is sine 90 degrees plus an angle. So you see how this gives you cos A. In the same way, sine 90 degrees plus 45 degrees minus x is now going to give you, you can just view the A as if it's the 45 degrees minus x. So it's just going to give you cos 45 degrees minus x. Okay, that's what we have there. And then all over sine x. Okay, so we clearly have to expand that more. So we can just use one of the compound angle expansion for that. Okay, because we can't reduce it, we can't use cofunctions on it, it's 45 degrees. So we'll just say 3p, and then let's expand. We have cos of a first angle minus the second angle. So this is going to be cos of that first angle, 45 degrees, times cos of the second angle, x. And then because it's a minus, that changes to a plus, according to the compound angle rule for cos. So we have now sine 45 degrees, and sine x all over sine x. Okay, this is good because these are special angles and we can actually expand those. Now, I would always say this because I have seen this happen in the past where your answer ends up not looking like what they told you it should look like. In this situation, they already gave you the answer. And the reason it doesn't look like that in this type of question was because you didn't stick to the rule of do not use a calculator for these types of calculations. So if you use a calculator, your answer will look slightly different. So instead of using a calculator for these cos 45 and sine 45, I'm going to use the OHA rule. So the OHA rule is meant for special angles and it works for all the angles. Any other angle that is not included in the OHA rule, you can just use the calculator. It will give you the exact same answer it's supposed to give you if you had used the circle, the trig circle, you know, with the different triangles that you form and then the different sides, or the triangles, the three triangles that you maybe would have memorized. So those are for special angles, but you can just use the OHA rule. We say OHA, OHA, and then you say 30 degrees, 60 degrees, and 45 degrees. Then you say 1, 2, 3, 3, 2, 1, 1, 2, 1. Then in each of these rows, you're going to square root the biggest number, not angle, number. Okay, so we square root the 3 here. Here we will square root the 3. And here we will square root the 2. And so to find cos of 45 degrees, we'll say cos, we know from saw, katoa, that cos is adjacent over hypotenuse. So we're going to go to 45 degrees, the 45 degrees row, and we're going to take the adjacent, which is a 1, over the hypotenuse, which is the square root of 2. And you also see that sine of 45 degrees will give you the same thing. That's saw, sine is opposite over hypotenuse. So that is at 45 degrees, opposite is 1 again over hypotenuse square root 2. Okay, so you see that it is 1 over square root 2 that we would get for both of them. So this is how this expands. We say CD is equal to, we have 3p, and then that gives you, it's going to give us 1 over square root 2. So we have 1 over square root 2 multiplied by cos x, right? And then plus 1 over square root 2 multiplied by sine x. Okay, all over sine x. Now, what you could do at this point is just take out the 1 over 2 as a common factor from this bracket. And so we'll have CD is equal to, and that common factor will just go in front of the 3p, okay, the 3p. So it's multiplied by 1 over root 2. Now I'm writing it like this for a reason, because that it is a fraction. You see the 1 is going to go with the 3p, and then that is a denominator. So it looks like that. And then in the bracket, what you're going to have is your cos x plus your sine x, which makes perfect sense. That's why they had that. They had sine x plus cos x. Okay, so we can also just put the sine before the cos. And then we have all over sine x. Now, you can put it as all over sine x, but it really just goes here. It's all over sine x, okay, because these two would multiply. Here's a quick explanation of that. The sine x is being divided by everything here. Okay, so if you're dividing by sine x, what happens is you're saying divided by sine x, but you have to make sine x a fraction so that it can work with these, because that has a fraction. So over 1. And of course, you would tip in times. So CD is equal to, and what happens here is you have these two multiply. Actually, all of these multiply because they're in the numerator. So you have 3p times, and we'll just say sine x plus cos x, changing the order of that. So it looks like our answer. And then over the square root of 2. Now, what happens with this is you tip in times. So you swap the numerator and the denominator. So they look like this now. And you see what happens when you multiply numerator and denominator. CD is finally equal to 3p multiplied by sine x plus cos x all over, and those two multiply to give you square root of 2 sine x, just like they said it would be equal to. Okay, so that was their answer as well. Okay, so that is it for 7.2, and we move on to the last question, 7.3. The last question, 7.3, says, if it is further given that p equals 10 and x equals 110 degrees, calculate the area of triangle ADC. Okay, let's go ahead and see the triangle ADC. Okay, we don't need any of these anymore, really. Area of triangle ADC. So this is triangle ADC. And to find the area of this triangle, as you can see, it's not a triangle with a perpendicular height. So because it's not that, we're going to use the area rule. With the area rule, you need one focus angle and you need two sides available. Right now, we actually have that. Remember, we found CD and we found AD as well. So we can use CD, AD, and the middle angle, 45 degrees. Okay, so we're just going to go ahead and use that. Okay, just keep in mind this was 3p. This we found CD. Okay, it's that long thing, but we'll include it. And we're going to just use this as a half times AD times CD sine of that center angle, angle D. Okay. Okay, so this is what we have. And now we can just substitute. So the area of this triangle is equal to a half times AD, which we know is 3p, right? Multiplied by CD, which we know is that. So we can just take that and substitute it there. And then, of course, sine 45 degrees. So sine 45 degrees. And they told us that p is equal to 10 and x is equal to 110 degrees. So just substitute. So this is a half. I'll just leave it like that. So a half multiplied by 3p. So that's 10 times 3. You see, it's just substituting at this point. And then sine of 110 degrees plus cos 110 degrees. So that's together. Cos 110 degrees. Then lastly, we just have over the square root of 2 sine x, which is 110 degrees again. And then lastly, we have sine 45 degrees. And you can just nicely substitute that onto the calculator and see what you get as an answer. Okay, and really these two were in brackets. Okay, so just don't forget to put that. Okay, so our answer is 143 point, and you see that 6 is going to round up, so 0.11. And these were in, they said that flagpole was, okay, they're in meters. So 143.11 meters squared. And that is the answer. Okay, so that is it for this video. And I will also add the Euclidean geometry section, which is already up. So it's just going to be a playlist. Okay, so then after this, I will go ahead and compile the paper 2 compilations. And there we go. You guys can use that to practice with maths. All the best for your exams in future. And I hope to see you guys in the future videos. Bye. So moving on to question 5. Question 5.1 says, without using a calculator, simplify the following expression to a single trigonometric ratio. So we have this expression and we have to simplify this. Okay, so first of all, please just notice what is going on here. We have first 1, then negative sine of negative theta, then the cos 90 degrees plus theta. These two are being multiplied. So it means that on top, if you look at the amount of terms you have 1, 2 terms on top, and then the denominator, you just have 1 term. Okay, so we're going to solve this term by term. That's how you should always solve expressions. Each term should work on its own. So the first term is 1. There's nothing we can really do with 1. So we just leave 1 as it is. And then we have sine negative theta. So how do we simplify sine negative theta? Okay, so there's 2 ways you can simplify it. You can simplify the grade 12 method or the grade 11 method. Now, I like to use, the only reason why I explain the grade 11 method is because it really helps you understand the whole fundamentals of simplifying trigonometric expressions. You see, we have negative theta. Theta represents an angle. You see on that Cartesian plane, theta lies here. It is all the angles that are less than 90 degrees. That's what it stands for. So technically, this has a size and it's saying negative theta. So whatever that angle is, it is negative. There's a general rule about angles that you need to remember. When an angle is negative, what you need to do is add 360 degrees to it. Okay, so I'm just trying to show you the step-by-step method and how it happened. If you add 360 degrees here to that, you end up with, you have a minus in front, then sine 360 degrees minus theta. And then here you have cos 90 degrees plus theta. This is a cofunction, okay? Remember all the rules of your cofunctions. These are all the cofunctions that we have. It's always going to be either 90 degrees minus theta or 90 degrees plus theta. Okay, so I do actually have a video where I explain cofunctions. Well, it's actually the proof of the compound angle formulas. Okay, and I do explain about that. So you can actually check that video out and that little part just to see that, because I don't want to go too deep into this. Just remember that everything here, if this is a sine, it will change to a cos. Okay, it changes to positive cos theta. This one will change because it's cos, it changes to positive sine theta. This one is sine, so it changes to positive cos theta. But then there's one more, and I see I made a mistake here. This should be a plus because we already had that. Okay, so cos 90 plus theta is the only one that changes to a negative sine theta. And of course, that video does explain why. So you can look at that again. Okay, so I'm just trying to be careful with these stuff just so that you understand why we're using certain rules. I don't want to just assume that you understand how it works. So this, okay, that's the one that becomes a negative sine theta. But you need to remember that this is being multiplied by that term. Okay, these two are being multiplied. So it's multiplied by negative sine of theta. Okay, over. Now look at this one. We have cos theta minus 360. Think about that. That reduction, does that look fine to you? Is that usually the kind of reduction you have in your diagram? The one that had 360 degrees is actually 360 degrees minus theta, not theta minus 360. So if you look closely at this, remember, theta represents an acute angle because we have 90 degrees here and theta here. All the angles less than 90 degrees. So it's saying that acute angle minus 360 degrees. So imagine that was like maybe 45 degrees minus 360. You're going to end up with a negative angle. So you see this case, this is a case of negative angles. And what do you do when you see an angle that is negative? You add 360 degrees to it. So if you add 360 degrees to this, look at what you'll get. Theta minus 360 plus 360. Those would cancel. And you'd just be left with cos and theta. That's all you're left with. Okay. So that's the rule. That's actually what happens. I'm just trying to show you what actually happens. Then we can go on to simplifying. We have 1 minus. Okay, so now if we're simplifying this, we have 1 minus and then sine 360 degrees minus theta. Remember again in the Cartesian plane where we have 360 minus theta, this is the quadrant that belongs to cos. Cos is positive in this quadrant. Sine is negative. So you see, you leave that negative here, but this one now becomes a negative sine theta. Then multiplied by negative sine theta over cos theta. Okay, is equal to, now because these two are being multiplied, the sine, this, and this are being multiplied. So if we multiply these two together, you see that we're going to get 1, and then this multiplied by this, because we still have minus here. This multiplied by this gives you a positive sine squared theta. Negative times negative is positive. So sine squared theta. This minus is coming from here. Okay. Over that we have cos theta. And this is equal to, and now look at this. You need to remember your identities. Your identities are, we have this rule, sine squared of theta plus cos squared of theta is equal to 1. Now, if you made cos squared of theta the subject, so cos squared theta is equal to, notice that on the right hand side you have 1 still, and you would have to take sine squared of theta over so that this can be left on its own. So this is another one that you have. Cos squared of theta is actually equal to 1 minus sine squared of theta. So we're going to change that. So this is actually cos squared theta. That is what is equal to 1 minus sine squared of theta over cos theta. Then on the top, a cos would cancel with the cos on the bottom. And then you see that your answer is just cos theta. And that is that simplified. So it's not supposed to be that long. But the only reason why I did that is because I really wanted you to understand how that works out. Okay, move on to the next question now. So look at what we're given. We're given that cos of 20 degrees is equal to P. Without using a calculator, write each of the following in terms of P. Okay, so this is basically one of the trig diagrams that you can get. This case, it's a rare case, it hardly happens, but here and there they will actually put it in. So with this, they're telling you that cos of 20 degrees is equal to P. Very different from the other ones that we had. Before, they will always say cos of, or theta, right, is equal to something like 2 over 3, right? But in this case, they're telling you the size of the angle. And when they tell you the size of the angle, this is them helping you to know which quadrant it will fall into. Think about it. On your Cartesian plane, which quadrant does 20 degrees fall into? Okay, that is an acute angle. It will fall in the first quadrant. So it means your terminal arm is going to be here, your radius. And then you're going to have 20 degrees measured here. Then you see, they say cos 20 degrees is equal to P. So it means that we're saying cos is adjacent over hypotenuse. So it means P is your adjacent side. What is your hypotenuse? If you have to put P as a fraction, it is kind of like a whole number. You put it over 1. Okay, that's going to be the denominator of it. So your hypotenuse is 1. And this is how we're going to look at this. So I drew the terminal arm, but remember you also have to draw a line going down to the x-axis, and this line must be perpendicular to the x-axis. Then the adjacent side, so he has 20 degrees. What is adjacent or next to 20 degrees? It will be this side. That side is the P. So that's the value of P. And then our hypotenuse is 1. So that's 1. So you see that here, we just have to find the opposite side. Okay, now I refer to the opposite side in terms of coordinates. This is, because you see, whatever this length is, it's a y value. So I refer to that as y. And of course, this one is r. That's 1. And then this is x, because you see, this number here is an x value. So we need to find y. So to find y, I'm going to use Pythagoras, because this is right angle triangle. So we can say y squared is equal to, so we're looking for one of the shorter sides. So you're going to say is equal to r squared minus x squared. Okay, Y squared is equal to, what is our R? It's 1. So that's 1 squared minus, what is X? It is P. So minus P all squared. Okay. And so 1 squared is just 1. So we have Y squared is equal to 1 minus P squared. Then you need to solve for Y. How do we solve for Y? To get rid of this square, we need to square root both sides. So if you square root both sides, you need to remember something. When you square root both sides in an equation, you need to add positive and negative here. The reason why is because if you have 1 all squared and it's equal to 1, right? Let's say we have an equation, x squared is equal to 1. And you square it with both sides and you said, oh, x is equal to 1. Well, that's not completely true. This is an equation. X squared is not the only thing that is equal to 1. And this is not completely true because if you said 1 all squared, yes, it is equal to 1 because we're saying x squared, something squared gives you 1. Okay, but if you also said negative 1 all squared, it will also give you 1. So you see there are two solutions here. And the exponent on the x actually gives you a hint on the amount of possible solutions you have. We have two possible solutions here. Okay, so you need to always add that plus minus. Okay, now the reason I only explain this is because new people may be looking at this video. I know I have explained this in previous videos, but then I can't also just assume that you've seen them. So y is equal to, now this is where we decide. You see, we know it's in the first quadrant. And as you can see, look at the y value there. Whatever that y value is, it is a positive number. So we're going to take positive, not the negative. So it's just a positive square root of 1 minus p squared. That is our y value. And let me just move this over to this side. So that is our y value. We have the square root of 1 minus p squared. Okay, our diagram is complete. We have r, we have x, and we have y. And now we can actually solve what they're asking us to find. Let me just make some space here. Okay, so we have the first question, 5.2.1, actually just says we need to simplify cos 200 degrees. Okay, so when you're simplifying this type of angle, look at this angle, 200 degrees. Which quadrant does that fall under? We have 0, 90, 180. Then we have 270 here. So you see that 200 degrees is just past 180, but it's less than 270. So it falls into this quadrant. So we need to use this reduction for it. This reduction is 180 degrees plus theta, and it belongs to tan. Okay, so when we're looking at this, we're just going to simplify this. This is going to become, I'm just showing it step by step and how it works. So this is going to become cos of, we're going to build 200 degrees using this. So we're saying 180 degrees plus what is equal to 200 degrees. That's plus 20 degrees. Okay, then if you actually reduce this, using the fact that we are in tan's quadrant, cos is negative in tan's quadrant. So this is going to become negative cos of this angle, the theta, okay, which is 20 degrees. So this is what we have, negative cos 20 degrees. And if you see in our information, you can use it here. You can actually find it here. Find out what cos 20 degrees is. That is, cos is adjacent over hypotenuse. But you could have also just looked at the fact that they told you at first cos 20 degrees is equal to p. So if this is negative cos 20 degrees, then this is equal to negative p. Okay, so that is our answer for the first one. Moving on to the next one, we have sine negative 70 degrees. Okay, so there's kind of two ways of solving this. You can solve this thinking about cofunctions, but also just remember, first of all, that this angle is negative. Okay, so I would always like to show the step-by-step way, just so that you see that things don't just happen because, you know, you just made it happen. There's a step-by-step process. The angle is negative. Naturally, when angles are negative, you would add 360 degrees to it. There's also the shorthand grade 12 method. Okay, you could have also just said, let's measure negative 70 degrees. Because the angle is negative, you would not measure this way, you would measure this way. So we would measure like that, 70 degrees. Now, because it's 70 degrees, it is below 90 degrees. From here all the way to here is exactly 90 degrees. So it means that this negative 70 degrees, that angle would only fall within here. It would not go beyond this line. So which quadrant does it fall into? It falls into cos's quadrant. So cos is positive in this quadrant, meaning sine is negative. So if you were just simplifying this, this would have become negative sine. Then you can just say 70 degrees. See, that's what I meant by this is the grade 12 method. It's actually quicker to do that by measuring rather than adding 360 degrees because the angle is negative and then still reducing it. Okay, so now that we already have this negative sine 70 degrees, well, 70 degrees, it's already acute. So how do you actually simplify this? And you see that 70 degrees, yeah, it doesn't have a 20 degrees. So we need to actually change this to become 20 degrees. It needs to have something to do with 20 degrees. So let's change this, and we're going to change this using cofunctions. So what is the cofunction for sine 70 degrees? Okay, with this one, it's because it's numbers. Just think about how the cofunctions work. You only have two types of angles in cofunctions. You have either 90 degrees minus theta, or you have 90 degrees plus theta. Okay. And I'm actually just going to put it in a diagram. Now, please note, this diagram does not exist in real life. I just use it for cofunctions because it works well. Here, I have 90 degrees, okay? This is 0, this is 90, of course, that's 180. This part, I call this 90 degrees minus theta. And I also see it as the first quadrant where everything is positive. The second quadrant is 90 degrees plus theta. And I see this also as the second quadrant where sine is positive. Now, this is how I work. It's only for cofunctions, okay? So we're going to have to think about where would 70 degrees fall into. Is it going to fall in 90 degrees plus theta, which you can see is past 90 degrees, angles greater than 90 degrees, or would it fall into 90 degrees minus theta, angles less than 90? Okay, it will fall here. So because it falls here, look at how we're going to do this. We're going to say, still have the negative there, sine, and we're going to create 70 degrees using this. 90 degrees minus what gives you 70 degrees? So that's 90 degrees minus 20 degrees. Okay. Then we're going to now finally change it using cofunctions. This diagram helps you to change it. You're going to keep the minus on the outside. But what does sine 90 degrees minus 20 degrees give you? It's the same thing as sine 90 minus theta. Okay. That would simplify to, it's a cofunction. It's first going to change to cos, right? But then you have to think about it. Is it going to be positive or negative? Well, it's 90 minus theta, so it's going to be positive because look at this. In 90 minus theta, you ask yourself, is sine positive in this quadrant? Yes. So your answer, your result is also going to be positive. So it's positive and it changes to cos. And then, of course, you have the 20 degrees. So you see that you have negative cos 20 degrees like the previous, which is also going to be equal to negative p. Please also let me know if I'm over explaining things. The reason why is because in trig, I've seen so much matrix who actually misinterpret certain things, and then I don't know where exactly it happened along the lines as they were learning throughout grade 10, but then they confuse a whole lot of things, especially like with that thing that I explained with the sine of negative theta, basically that. So there's a lot of rules that I noticed are misunderstood. That's why I'm explaining like this, but please let me know if it's a bit too much. Okay, and then moving on to 5.2.3. Yeah, I feel like we need more space for this. Okay, we'll see. Sine of 10 degrees. You see, these questions, is very important to actually go through these types of questions. You see this one? Yeah, it's a trig function, diagram. It's a trig diagram, and you should really practice on that. This one, it was bound to come in. They always, like, if they had to do that, there was no way they were going to waste all these marks and not put this type of question. Sine 10 degrees. Okay, very weird one. Now, it's a question that would literally only be asked in matric because in grade 11, you would not know about double angles for you to answer this. For this one, you actually have to use double angles. Let me put down the double angle formulas so that I can show you why I'm saying you need to use double angles. So these are the double angles, right? These four formulas. Of course, there is that extra one for sine, that half sine 2a. Okay, but I'm not really focusing on that right now. The thing about this is, look at what we have here. we have sine 10 degrees. Remember how I said that everything has to be related to 20 degrees because this diagram has 20 degrees. So we need to relate everything to 20 degrees. Like we were able to reduce this and get it to 20 degrees. We'll be able to get this to 20 degrees. We need to also find a way to make 10 degrees 20 degrees. So what does 10 degrees and 20 degrees have in common? Well, 10 degrees is half of 20 degrees. If you notice something about what the double angles do, look at what they all do. If you have your cos 2a, that's double of whatever a is. It becomes cos squared a minus sine squared a. Again, you have cos 2a, double of whatever a is. This is the reason I'm going to use double angles, because 10 degrees, double of it is going to be 20 degrees. Okay. So now we have to see which formula can we actually use to actually find this. Okay, so how do we find out which one will work? So for this, let me just try a random one. The reason why I'm doing this is because for you to understand why something doesn't work, you have to actually try it for yourself and see why it doesn't work. Let's say I just pick this random one, or let's take one that is more promising because we have sine. Let's say I was like, okay, we have sine, let me take this one. Okay, I'm not saying that's going to work, but let's just try it. So we're saying sine 2a, but we're relating it to 10 degrees. We're calling a the 10 degrees. So instead, this will be sine 2 times 10 degrees is equal to 2 sine. Then we have a, which is 10 degrees, and then cos a, which is also 10 degrees. Okay, with this, you should be able to simplify this expression and basically find out what sine 10 degrees is. Look at how we're going to do this. Sine 2 times 10 degrees is sine 20 degrees. That's not a problem. We can actually find the value of sine 20 degrees because it's 20. In the diagram, we can actually find sine 20 degrees. Sine is opposite over hypotenuse. So you see, this part is okay. We can still find that. Then we have is equal to 2 sine 10 degrees, which is fine. We can leave this here because what we're actually going to do is try and make this the subject of this equation. Then we have cos 10 degrees. Now this is where the problem comes. How do you actually simplify cos 10 degrees? There is no, you see in this diagram here, this is 20 degrees, not 10 degrees. I can't actually say, oh, cos 20 degrees is adjacent of hypotenuse. No, that's not true. Cos 20 degrees in this situation, in this diagram, can be found by saying adjacent over hypotenuse, but not cos 10 degrees. So the problem here with using that one, just because it's sine doesn't mean you need to use it. The problem here is I can't find the value of this. I may be able to find this. I may be able to make this the subject, but I can't find this one. So this rule is not going to work. And something you can do is actually try the other rules as well. So as exercise, go ahead and try the other rules and see which one will work. But now I'm already showing you that the one that will work for this is actually this one. So let's look at this. If you have cos 2 and we have a, right? A is 10 degrees. So 10 degrees is equal to 1 minus 2 sine squared of a, which is 10 degrees. Look at what we can do here. Cos 2 10 degrees, okay, that is going to give you 20. So that's cos 20 degrees. We can find that. We already know what cos 20 degrees is. They told us in the beginning that cos 20 is equal to p. We can find that value. Okay, so we have this value is equal to 1 minus, now you have this. You see, you have 2 sine squared of 10 degrees. This is not a problem. We want to solve for sine 10 degrees. Here, look at your sine 10 degrees. All you have to do is make that the subject. So now this becomes an equation where you're trying to make that the subject. Okay, let me get rid of all of these just so that we have some space. Okay, so how do we make that the subject? Well, you have one term here, 1, and then you have minus 2. What we can do is take that negative 2 sine squared 10 over. Okay, so if you take that over, it becomes a positive 2 sine squared 10 degrees. And I'm just going to take this over as well. So first of all, on the right, we still have 1. Then taking this over becomes a negative cos 20 degrees. Okay, let's fill in the stuff that we already have. Cos 20 degrees, remember, is P. That is the value of P. So I'm just going to put in place of cos 20 P. So cos 20 is P. So I replace that with P. Okay, this is what we have. Now we just have to simplify, make sine 10 degrees the subject. We can go ahead and just divide both sides of the equation by 2 first. Then we have sine squared 10 degrees is equal to 1 minus P over 2. And then to solve with sine 10 degrees, you would just square root both sides because this is being squared, square root that. But remember, you always have a plus minus, okay? But remember, you're saying sine 10 degrees. 10 degrees falls into which quadrant? The first quadrant. So it's going to be positive. So don't worry about that. It just stays positive. So this is equal to, so finally, sine of 10 degrees is equal to the square root of 1 minus P all over 2. That is our answer there. Okay, this question has popped up a couple of times. You will always notice it because it's always going to be the angle they asked for would be half of whatever your reference angle was here. Okay, so moving on to the next question. The next question, 5.3, says determine without using a calculator the value of, and we have this. Okay, so let's just focus on the amount of terms we have. See, cos A plus 55 is being multiplied by cos A plus 10. And then it's being added. So look at this, that's one term. And then we have sine A plus 55 again, and then sine A plus 10. Okay. This looks like compound angle formula, and it looks like it's singing the cos song. The cos works like this. It says cos, cos, sine, sine, and then you have A, B, A, B. Then in the middle, in this case, we have a plus. So plus. Okay, so this is what we have. Now we have to just verify that it really is literally singing that same song. As you can see, you have cos, cos, cos again, and sine, a sine. Then we also have, let's see, is it actually saying AB, AB? You have this first value here, A plus 55 degrees. Let me use something light. So you have this first value here, A plus 55 degrees. Okay, let's say that stands for A. If it really stands for A, it should repeat itself again here. Look at that, it is repeating itself again. Okay, then we have the A plus 10 degrees. And that A plus 10 degrees is representing the second angle. That should be the exact same thing over here. And you see that? It's the same. So it really is singing the cos song. So just like we would take this and simplify it to cos, okay, using compound angle. Remember, the formulas are in the formula sheet. Cos, then you would say A, and because this is a plus here, in the cos song, this changes to a minus. I just call it a song because that cos, sine, sine. Okay, then minus B. That's what that would become. It's the exact same thing we're going to do here. So in this, we're going to actually say cos, and then what was our A? What represented our A? Our A was this first one, the first angle they gave us, which is A plus 55 degrees. So that's A plus 55 degrees. Then we have to say minus B. What represented our B here? That was the second angle, which is A plus 10 degrees. You see, A plus 10 degrees is two terms. So when you're subtracting, you need to add brackets to protect that because it's going to multiply in. So that is A plus 10 degrees. Then we close that. So I'm just going to use big brackets to close it. That's what this simplifies to. Now we just have to simplify this part. So it's equal to, we're going to have cos, and now we have A plus 55 degrees, distribute in negative A, distribute negative 10 degrees, then this is equal to cos. You see the A, positive A and negative A would cancel, and you have 55 degrees minus 10 degrees, which is 45 degrees, and cos 45 degrees is equal to, well, if you use the calculator, it's the square root of 2 over 2. If you use the rule that you're actually supposed to use, is going to be 2 over the square root of 2. Okay, that rule, well, it's going to take a bit long to explain it now. So maybe in another video, I can use that as an opportunity to explain more on trigonometry. Okay, so there we go. That's what we get. So even if you put this answer, I'm sure if you gave this answer, they'll still be fine with it. You gave this answer, it's okay. Okay, but don't take my word on that. I'm not too sure if they're strict on that. Okay, moving on to the next question, 5.3. Okay, 5.4. This is what we have. They say consider, and then they give us this. And they want us to prove the identity above. Okay, so it's not an equation, it's an identity. In identities, you just have to prove that the left-hand side is going to be equal to the right-hand side. Okay, so I like to start by stating which side I'm going to work with. We only have a negative sign x here, so can't use that side. We have to use the left-hand side. So I'll say left-hand side is equal to, and just rewrite all of this. Okay, so now we can start with this. Okay. We have to really think about this, and that's the thing about trigonometry. It's not something that you can just like do mindlessly. You have to really think about it and see how should we simplify this. So on top we have 3 terms. Okay, so first of all, the first thing you could think about is the fact that these are expressions that you eventually want to simplify and become just negative sine x. You see, negative sine x does not have a 2x in it, meaning first of all, these 2x's, they need to go, they need to change. So how do we change them? Now is where you really need to think about it. Okay, so thinking about how we're going to change this. So first of all, thinking about how we're going to change this. Sine 2x can only be equal to 2 sine x cos x. So this is going to help a lot. Already knowing, okay, this one can only simplify to that. So if that changes to positive 2 sine x cos x, and then we have minus cos squared x here. Okay, think about this. You have sine 2x cos x, and then you have a cos 2x. What should we change this to? Just so that it can simplify well. So look at the fact that you have a negative cos squared of x. Okay, you have a negative cos squared of x. This could have been a trinomial had this been positive, right? If you had this here, positive, and then eventually this maybe became something like that, then yeah, it could be a trinomial. But as you can see, this is never going to just simplify to sine squared x, right? And this is actually negative. So the best thing to do here is get rid of this. So what this needs to change to, it needs to change to something that will help to get rid of negative cos squared x. So what do we need to get rid of negative cos squared x? You need a positive cos squared x. So choose one of the double angle formulas that will include a positive cos squared x. Okay, so which double angle can we actually use that's going to get rid of that with a positive cos squared x? You could use the cos squared x. Let me actually put that in another color. You could just use instead the cos squared x minus sine squared x. And that will get rid of that problem. Okay. Because you see right now, we don't know how we're going to simplify that with something here. So now that can go away. Okay, so we have a denominator still over, and honestly with these trig expressions, the best way to improve in it is just to do a lot of them. So something that you can really do is work on it a lot first until you realize, okay, I really don't know the answer. Then check the solution. Okay, so then we have over, and we have sine x minus 2 cos x. I still don't know what to do with this. There's nothing I can really do with that. I can't simplify it further. Is equal to. Then on the top, this would cancel with this. And look at what we're left with now. We're left with negative sine squared of x, and then positive 2 sine x cos x. That's what we're left with. Over positive sine x, and then minus 2 cos x. Okay, so this is what we have. I need a bit of space. Okay, so this is finally equal to, on the numerator, you see, how many terms do you have? You have 1 and 2. What's common in both terms, because they can't be added together, so take out a common factor. We can take out a common factor of sine x, okay? But that might not really be the right thing to do, because look at the denominator. It's probably going to cancel with whatever is left on the numerator. So let me just show you. If we just took out sine x as a common factor, it's not that you're going to be wrong. Okay, then we open a bracket. You see what will be left if you divide. So negative sine squared of x divided by sine x. Okay, it's still negative. One of the signs cancel, you're left with sine x. Then over here, if we divide that, you're just going to be left with a positive 2 cos x. You see, now look at the denominator. The problem with this is it's close to being the same, but this one is negative, this one is positive. This one is positive, that one is negative. So what we should have actually taken out as a common factor is not positive sine x, but negative. Now, you'd be like, how would I have known that? It's not a problem. You could have left it like this and said, okay, fine. Instead, because of this, what I'm going to do instead is on my denominator, I can take out a negative, or you could even do that on the numerator. It's just an extra step. So you can take out the negative as a common factor again. But I'm actually just going to do that on the denominator just to show you that it is possible. So we just have sine x minus sine x plus 2 cos x. And then over, look at what you have now. If you take out a negative as a common factor, you're going to see now you will have the same bracket. So negative as a common factor, it's like saying sine x divided by the negative. Remember, what we're doing when we're taking out a common factor is you take out the common factor and you ask yourself, what do we multiply to this to get back to that? You see, it's like multiplying by a negative 1, really. So what do I multiply to negative 1 to get to positive sine x? You would multiply by a negative sine x. Okay. So I'm not going to leave it as a negative 1, just negative. Then we're doing the same thing here. What do you multiply to negative 1 to get to negative 2 cos x? You're going to multiply by a positive, because positive times negative is negative. Positive 2 cos x. Okay? But the division way is just easier when you say this divided by that. The negative cancel becomes that. Okay. So now you see we have the same bracket, same thing on top, and it's one term on top, one term on the bottom. Now we can cancel. You cannot cancel across terms normally. That's common with that. So that's gone. Now we have sine x divided by a negative, and remember it is a negative 1 actually, an invisible 1. So that is negative sine of x. And as you can see, that is your right hand side. So it is finally equal to your right hand side. Okay, moving on to the next question. So 5.4.2 says we have to determine the value of this. Okay, if you look at the numerator, you notice that this is exactly the same as the numerator here. Okay, it's only the denominator that is different. Okay, so how do we simplify this now? We're going to let's look at the fact that we have. Let's actually just simplify the same way. Since the top looks like this, how did we simplify this numerator? Let's follow that up to the last place it was simplified. You see, we got this to look like this, then we got it to look like this, and then we eventually simplified it to look like that. So you can start from here if you like, or start from here. To be safe, I'm going to start from here. That numerator, I'm just going to replace this with it, because I know it's going to simplify to that on top. That's why they put it as the second question, because I would have expected them to say hence determine the value of this. But that is going to be your numerator, that part. Over, and so now we can actually just simplify this. So we just have a negative 3 sine squared x plus 6 sine x cos x. Okay. So how do we actually do this now? It seems like we have to take our common factors on the top and the bottom. So the good thing is, you see you have negative and positive, negative and positive. So really just take out the same thing in both. Here, we can take out what is common. We can just take out, I'll just take out a negative. So take out a negative sine x. Open brackets. So you're saying this divided by this is just going to give you a positive sine x. And then this divided by that is going to give you a negative 2 cos x over. Then here, if we also take out a common factor, what's common? I'm going to say negative 3 sine x is common in both, because you see, and you have a 6, 3 is in there, or negative 3. Open a bracket, and so this is being divided by this. Those two numbers will cancel. Sine squared just gives you sine x. And then positive 6 divided by negative 3, that is going to be a negative 2. Then, of course, the sine and sine cancels, and you're left with cos x. Okay, so that looks nice. That looks good. It looks like it's going well. So this would cancel with this, and then we're just left with, okay, negative divided by negative is a positive. Sine cancels with sine. So what are we left with? It's not a 3, okay? On the top, you have a placeholder of 1 there. Even though negatives would cancel, you still have a placeholder of 1. So your answer is 1 over 3. That's your final answer. Okay, so that was for 3 marks. How much marks was this one for? 3 marks as well. Okay, so moving on to the next question. Okay, so moving on to 5.5, it says given 3 tan 4x is equal to negative cos 4x, and 5.5.1 says without using a calculator, show that sine 4x, okay, is equal to negative 0.5 is the only solution to the above equation. Okay, so we are taking this. Okay, so this is not an identity. So we have 3 tan 4x is equal to negative cos 4x. Okay, good thing they were consistent with the 4x. Whenever we see tan, you can change it to sine. So let's go ahead and change that tan to sine over cos, not sine. So we still have the 3, and we're going to change this to sine 4x over cos 4x is equal to negative 2 cos 4x. Okay, fraction here, number here, so we can actually just take this and put it over 1 because it's an equal to sign, cross multiply. So this is going to be multiplied by that, and that's going to give us a 3 sine 4x, and then this gets multiplied by that, and that will give us a negative 2 cos squared of 4x. Okay, so this is what we have now. If you look at this expression, yeah, this has cos, this one has sine. What we can do is, since this has 3 sine, and I always see this as a hint towards this, because this has 3 sine 4x, okay, it means that it could possibly become a trinomial, because we can look at the sine 4x like just an x, or just to remove the confusion, let me call it a k. So it's like 3k, right? But here you have negative 2 cos squared of 4x. It's going to have to stay consistent. You can't have a cos squared, but then you have a sine and you're saying it's going to turn into a trinomial. We need to change this into a sine, okay? Because it's squared, we can actually change it. Remember that cos squared of theta is equal to 1 minus sine squared of theta. So we can change it like that. I'm going to say negative 2 still. Then because you see it's changing to something that has more than one term, I'm going to put brackets. So this now, this cos squared of 4x, just treat the 4x like a theta. So that's going to become 1 minus sine squared of 4x is equal to 3 sine 4x. Okay, that looks more promising to be a trinomial now. Now if you multiply this in and distribute it, we're going to have negative 2, then a positive 2 sine squared of 4x, and then we of course have the is equal to 3 sine 4x. Now I'm not taking it over because I noticed that this is already positive here. So as a trinomial in the order of its degree, this one would come first, positive 2 sine squared of 4x. Then I can take this over, so negative 3 sine 4x, and then of course the negative 2 is still on the left, so minus 2 equals 0. Look at how you can view this. The sine 4x, pretend the sine 4x is a k. So this is actually just 2, then sine 4x is k, but you have squared, so k squared, minus 3, then you have sine 4x, which is k, and then minus 2 is equal to 0. So this is what we have. How would we factorize this? As you can see, there isn't a common factor. It's one of those ones where you kind of have to use a method of factorizing. And I have a video on my channel about factorizing trinomials and also these types as well. So look at what we have. You're going to have to factorize this, and I'm going to use something called the cross method. I look at the first term, 2k squared, and that is going to be, what is the factors of 2k squared? It's 2k times k, that gives you 2k squared. Then what times what gives you negative 2? That will be 2 times 1. But you see, put in this order, it's not going to work, because if you multiply that, remember one of this already has to be negative. If you multiply like that, that's going to be a 2k. If you multiply like that, that's also a 2k. That cannot give you 3k in the middle. So instead of putting it as 2 and 1, I'm going to change it to 1 and 2. Okay, now that it's already in this form, because we have a minus 3k in the middle, it means that the factor that becomes negative, okay, should be the bigger factor. The bigger factor here is going to be formed by saying 2k times 2. That's going to become 4. So I'm going to give the negative to that one. So negative 4k, and then k multiplied by that can be a positive 1 plus. So k times 1 is positive k. Negative 4k plus k is equal to negative 3k. So you see, now we have the middle term. So if you are factorizing this, it really just becomes 2k plus 1 and k minus 2. Now, I know I am using this in form of k. It's kind of like saying, first of all, let sine of 4x be equal to k. Now we're going to substitute in place of k. Let's put sine 4x back in. So I only do this, or you can do this, to make it simpler, to simplify. Now to put it back as what it actually is. Therefore, if we're factorizing that, it actually becomes 2, and then the k is sine 4x. Sine 4x, then plus 1, and then open a bracket. Then we have k again, which is sine 4x minus 2 is equal to 0. And now we have this factorized, and now we just have to solve. Okay, so solving for this, we're going to say either this bracket is equal to 0 or this bracket is equal to 0, because two things are being multiplied and they give you 0. One of them would have to be equal to 0 for that to happen. So that's the logic behind that. So 2 sine 4x plus 1 is either equal to 0, or it's a case that sine 4x minus 2 is equal to 0. So let's just solve. Okay, now they didn't really say find the general solution. They just said you need to show that this is the only solution. Okay, so let's just simplify, we're not solving for x. So we're going to say, take this 1 over, and this now becomes 2 sine 4x is equal to negative 1. Divide both sides by 2, and we have sine 4x is equal to negative 1 over 2, which is negative 0.5. So that is sine 4x is equal to negative 0.5. Or we have this part, sine of 4x is equal to 2. Now, this is not possible. The reason why is because look at the sine graph. The sine graph is just saying sine 4x. Its amplitude is the number in front of sine 4x. There's an invisible 1 here. Its amplitude is 1, meaning this sine graph would only go as high as 1 and as low as negative 1. Okay, so it will look like that. And so because of that, it's never going to go beyond 2. We will never find a solution for sine of 4x being equal to 2. 2 will be way up here. The sine graph will never reach there. So the minute you see that, and there's no amplitude there, it's only like invisible. So there's an invisible 1 there. You just know that this cannot be equal to 2. Okay, and that's really the reason why. You don't have to draw that down though. Okay, so this is it, meaning sine 4x is equal to negative 0.5 only for this one. Okay, that is 5.5.1 done. Moving on to 5.5.2. Okay, this question says hence. So it has something to do with the previous question. Hence, determine the general solution of x in the equation this. Same thing as the previous. You already knew that this was the only solution. So only work with that. Only work with sine 4x is equal to negative 0.5. And that's what they're saying, hence. So we just need to find the general solution of this because that is all of this simplified. Okay, so we have sine 4x equal to negative 0.5. First of all, when you're finding the general solution of an equation, you first find the reference angle. Okay, so I'm not saying this is 4x, I'm finding just the reference angle first. And you find the reference angle by taking sine over. When you take sine over, it becomes sine negative 1, the inverse of sine basically, right? And you find that on the calculator by saying shift sine. Now, there are two ways of working this out. In this video, I actually want to show you those two ways. Remember, if you're okay with the first way, you can skip over to the next question. There are timestamps in the description. So, for the sake of everyone else, I'm just going to explain it the two ways. The first way, we're going to work with the fact that we are going to use quadrants. Okay, one way you use the quadrants, the other way you don't. When we're using the quadrants, or specifically reductions, using the reductions, this is what you're going to do. You're going to say, okay, we're saying shift sine and we have a negative 0.5, but we just want the reference angle. We don't care that the angle is negative. Okay, so we're not going to say of negative 0.5, we're going to say of 0.5 or half. Still the same thing, right? And when we find that reference angle, what are we going to get? Shift sine of a half is 30 degrees. So like you can see, 30 degrees, that's what we get. And this is now how you're going to solve. First of all, you're going to consider the fact that sine of 4x was negative, right? So sine of whatever you had was a negative value. And ask yourself now, in which quadrants is sine negative? Sine is negative in the third and the fourth quadrant. So that's what we're going to say. It's in the third and the fourth quadrant. So we're going to use these reductions. In here, we have 180 degrees plus theta. Here we have 360 degrees minus theta. We're going to use those reductions on this that we have. Since we have sine 4x now, we're just solving. Now we're finally solving for 4x. Here, we just call this a reference angle. But now we're finally going to solve for 4x. So I'm saying 4x is now equal to. Then you're going to use the reductions. The first one you have is 180 degrees plus theta. So we're saying 180 degrees plus theta being our reference angle. And our reference angle is 30 degrees. So plus 30 degrees. Then this is a general solution. We're not solving for the exact values of x. So because it's a general solution, you need to say plus k of 360 degrees in this case, because we are speaking about the function sine. The sine graph repeats itself every 360 degrees. So you say plus k 360. Now other schools may use N or T or P or any letter. You can. That's why at the end you need to tell them what k is. That's why we say k is an element of integers. Then we say or. So that's the first part we have, right? First, that one. Then we have to use this 360 quadrant. We are solving for the actual angle we have. The angle we have is 4x. We're saying 4x again is equal to 360 degrees minus, and now theta, our reference angle, is 30 degrees. Again, it's still sine. So we're going to say plus k 360. In class, you may call this 360k, still the same thing. I just like to say k in front so I don't forget it, because I notice when we write fast, I end up forgetting the k there, and that's wrong. So that's why I put the k in front. Then you need to say, now you're telling them what k is, because everybody has different letters for this. They may have. K is an element of integers. It can only be integer values. Okay, now we can finally solve for these. So what is 180 plus 30 degrees? We're saying 4x is equal to 210 degrees plus k 360 degrees. And then finally solve. If you want to solve for x, you're going to have to divide both sides by 4, but everything gets divided by 4. So look at what happens. We have x is finally equal to 210 divided by 4. So 210 divided by 4, that gives you 52.5 degrees. 52.5 degrees. Now, plus k of what? What is 360 divided by 4? 360 cut into 4 quadrants is 90 degrees. So, plus k of 90 degrees. You see, this solution is now repeating itself every 90 degrees and not 360 degrees anymore. Okay, then we can have here over here, we're just going to say divide both sides again by 4. Well, let's just solve for that first. So we have first 4x is equal to 360 minus 30 is 330 degrees, and plus k, 360 degrees. Don't have to rewrite that again. It's written once, it's fine. Divided both sides by 4, and then we're going to have x is finally equal to, so just put O here, 330 divided by 4, and that gives you 82.5 degrees, plus this divided by 4 is k of 90 degrees. There we go. And those are your general solutions. So remember I said I'm going to do 2 methods. If you are okay with this method, you can go on and skip. Then I will do a second method and show you that the answer is still correct. Okay, the second method is not using reductions. Well, technically you are using reductions, but you're only using the reductions that belong to the specific function you're working with. Okay, so this is how method 2 looks. This same equation, sine 4x equals negative 0.5. I'm just going to call it sine 4x equals negative a half. In this method, you only have to remember the reduction for sine. If you're working with sine, you're only going to think about it like this. Sine, okay, whenever you have sine and you're solving for sine, you're only going to ever use these 2 reductions. You're going to use theta and 180 degrees minus theta. Finish. You don't use anything else. You don't have to think about stuff too much. So the second method, this is what we're going to do. We don't even bother that this is negative. We're simply going to take sine over. To find that reference angle, we're literally just saying this is equal to, and we're going to say shift sine of negative 1 over 2. So shift sine negative 1 over 2, what does that give you? It's going to give you a negative sine theta. So shift sine negative 1 over 2, negative 30 I mean. Negative 30. So reference angle is finally equal to negative 30 degrees, right? And we're going to use it like that. So look at what we're going to do. You will always use the functions, or really the quadrants, the formulas belonging to this function. So we're only using those 2 because that's where sine is positive. Okay, so now to finally solve for 4x, so to solve for x, we're going to say 4x is equal to, the first quadrant we have is theta, meaning whatever your reference angle is, use that. So theta is negative 30 degrees. And I'm going to just say plus k of 360 degrees because this solution will repeat itself every 360 degrees. Then you can say, or 4x is equal to, and we're going to use that 180 degrees minus, and then we have negative 30, so negative 30 degrees plus k of 360 degrees, where k is an element of integers. Then now that we're at this point, now there's 2 routes you can take here. You can either identify that you have a negative angle, and if you want your answer to end up looking like this one immediately, what you can do is, okay, I have a negative angle, let me add 360 degrees to the negative angle. So you could have just done that, add 360 degrees from here. Now that will give you 4x is equal to, and then that's going to be 330 degrees plus k, 360 degrees, and I hope you see what's going on again. Okay. Then here you see you have 4x is equal to 180 degrees, and then you can just multiply in like that. So that's going to be 180 degrees plus 30 degrees, which of course gives us a 210 degrees again, plus k, 360 degrees. And as you can see, we're just doing the exact same thing. So there are 2 methods that you can take. Okay, so you can do that. Another thing that you can do, I'm just trying to show you this just so that if you actually did one method, don't think now your answer is wrong. Your answer may not even be wrong. There's also another way where you don't add 360 here, but you leave this as it is. First of all, we're just going to divide both sides by the 4, right? And look at what we get. X is equal to negative 30 divided by 4. 30 split into 4 parts. 7.5. 7.5 degrees, right? Plus K of 90 degrees. This is your final solution for X. Sorry, it should be negative because it's negative, okay? If this was your solution, it's not wrong. For this one, I'm not even going to bother too much. Even if this, you divide both sides by 4, you end up with the exact same answer as you had over here. With this one, what I mean by your answer is not wrong is the problem with this, not problem, it's not even a problem. The thing about this one is this is negative. This angle is negative. Now, this is slightly different. Because the angle is negative in this situation, I know people will think, oh, just add 360. No, you don't add 360 for this particular solution. This particular solution will repeat itself every 90 degrees. So you don't add 360, you add 90. So look at this. If you said X is equal to negative 7.5 degrees plus 90 degrees, right? Just to put it in a positive angle. Right now it's just negative. You see, so the difference between this one, okay, this solving for X is that this answer is repeating itself every 90 degrees. But when we have 4X here, the reason I could add 360 degrees is because this solution as 4X is going to repeat itself every 360 degrees. Okay, so if you had to say that negative 7.5 plus 90 degrees, look at what it gives you. You see that? That looks familiar. 82.5 degrees plus K of 90 degrees. That is the exact same thing we get here. You see what I mean by it's not wrong, it's just negative. And that's not a good or bad thing, it's just how you measure it. Okay, so that is it for this question. And we finally move on to question 6. Okay, so we're now on question 6. And question 6 says, in the diagram below, the graph of f of x is equal to tan of x minus 45 degrees is drawn for where x is an element of negative 90 degrees to 180 degrees. So this is a tan graph that we have, but notice what is going on here. Always notice the things that happen here. First of all, this graph has minus 45 degrees. Remember, when you are affecting the x, if you have a minus, it means that the graph is actually moving to the right. If you have a plus, then it's moving to the left. Okay, it's the other way around for the left and right movements, the things that affect x. So as you can see, this has moved 45 degrees to the right. Okay, that's how the graph has moved. So you can already just think about it like the original tan graph, everything that it has here, like here, say the number that it has at 90 degrees, it's supposed to have that 45 degrees before this because the graph itself moved to the right from where it originally was. Okay, so let's keep that in mind as we move on. The first question they asked, 6.1, is write down the period of f. So the period of f, now when you think about the period of a graph, is how long does this graph take to complete a cycle? In the sine graph, very simple. You have a sine graph, look at what it does. It does this, up, down, hits there, and done. That is one cycle. And a sine graph takes 360 degrees to finish a cycle. Just a normal sine graph, a graph that has not been altered in any way. So the tan graph, on the other hand, that's why we say plus K of 360 degrees in general solution. The tan graph, you would remember that we say plus K of 180 degrees because the tan graph actually takes 180 degrees to complete the cycle. Now you have to also check, has the cycle been altered? Has the period been altered? You just have tan and you have an x on its own, right? Then minus 45 degrees. When you know the period is altered is when you have something in front of the x. So if you had like tan 2x, then the period has been altered, okay? So it has not been altered in any way. So it's behaving like a normal tan graph, it's just shifted to the right, meaning its period would still be 180 degrees. Okay, I will be doing this from time to time. I don't want this to just be a memo where I'm just going to tell you the answers. I really want you to understand why things are happening in it. Okay, moving on to the next question. Okay, so question 6.2, this is what they ask us to do. They say draw the graph of g of x is equal to negative cos 2x for the interval x is an element of negative 90 degrees to 180 degrees on the grid given in the answer book. Show all intercepts with the axes as well as the minimum and maximum points of the graph. Okay, so they are telling us to show intercepts and minimum and maximum points. So we just also remember to do that. Okay, so the graph we have is g of x is equal to negative cos of 2x. To be able to draw this graph, okay, within this interval, and here's the graph paper already, to be able to draw this graph, you need to understand how the original cos graph works. So the original cos graph is y is equal to cos of x, that graph. So from this, we're going to find out what is actually happening to this new graph. G of x is equal to negative cos of 2x. Okay, so let me draw a simple cos graph. Let's say we have this is our y-axis, and so let me just actually make it 4 lines down. So we're going to go from here, and then here's our x-axis. So this is 1, this is negative 1, and let's just go till 360 degrees. So in the middle, we will have 180 degrees. So let's say 180 degrees here, and then 90 degrees and 270 degrees. Okay, so the normal cos graph, you can basically find this even by using your calculator. If you say cos of x, okay, so the first x value that we have, and the first x value that we have would be here, 0 degrees. So let's find out what cos of 0 is. You see, cos of 0 gives you 1. So it means that at 0 degrees, your y value is 1. And if you tried cos of 90 is going to give you 0. Okay, so you can try that on your calculator. But then cos of 180 degrees normally would give you negative 1. And then cos of 270 would be 0. And cos of 360 would be 1. So it forms a cos graph that looks like this. Okay, so we join it like that, and then it curves up and there. So this is one cos graph, and this, we will regard this as one cycle. The cos graph and the sine graph, they take 360 degrees to complete a cycle. That's what they do. Okay, so this is one cycle. So it means that after 360 degrees, right? So if we go from 360 degrees to 720 degrees, okay, that is 360 degrees later. You will have the exact same pattern. Again, you'd have it go like that, round and back up like that. And this will continue till positive infinity and even negative infinity. Okay, so now that we understand how this graph looks, we need to understand, so from this graph to this, what actually happened? Well, first of all, let's deal with the fact that we have a 2x over here. So you see 2x. So what is the 2x doing? Well, let's think about what the period of the graph is. You see, in this first question, they asked us for the period of f, okay? And f is a tan graph. The tan graph normally completes a cycle, okay? Just like this one. A cycle just means how long does it take to repeat itself again. So a tan graph completes a cycle in 180 degrees, but a cos and a sine graph completes a cycle in 360 degrees. So the original cos graph has a period of 360 degrees. Okay, so if it has a period of 360 degrees, what kind of period does this one have? What is the period of this one? Well, you have a 2x here. When you put a 2x here, to find the period, the new period, you're going to take the old period of the original graph. It's a cos graph, and you will divide that by whatever number is here, the coefficient of x, which is 2. This is going to have a period of 180 degrees. So what does this mean? It means that this graph that we had like this is going to now complete one cycle. It's going to have this exact pattern, but it will not complete a cycle in 360 degrees anymore. It will complete a cycle in 180 degrees. So it's going to look like this. If I take this graph and I copy it, I just want to show you what it's going to look like. Since it's taking 180 degrees to complete a cycle, right? This is what's going to happen. This graph that looked like this before, it's going to complete a cycle in 180 degrees, and it's going to look like that instead. You see, so now it's completing a cycle faster. So that's what's happening with that 2x part. Okay, the graph is becoming more narrow. Then now let's talk about that negative. Okay, what is this negative doing? Remember, you have a g of x is equal to negative cos 2x, right? G of x stands for the y values of the graph. It means whatever cos of 2x is, you're going to take that and you're going to multiply that by a negative. Okay, so along with the period, I actually forgot to say this. You're also supposed to now find out. So I need another graph. I want to just show you what happens to all these angles here. You see the same way the period, right, gets divided by 2 by the coefficient of x. All the angles that you have here, we're also going to take them and divide each of them by 2. So as you can see, this graph, this new one, is going to complete the cycle in 180 degrees. So I'm going to just draw it till 180 degrees. So if we have 180 degrees here, then look at what is going to happen. We're taking this graph and we're looking at the fact that, so before we had at 0 degrees, this is 1, this is negative 1. At 0 degrees, okay, we had a y value of 1. But now all the angles, just like the period, they're going to get divided by 2. But you see, if you say 0 degrees divided by 2, it still gives you 0 degrees. So here we will still, if you just say y is equal to cos of 2x, you're still going to have a y value of 1, okay, at 0 degrees and 1. Okay, and let's just focus on this one for now. So we will translate it after. We're going to find out what this negative is going to do to it. So here we still have a y value of 1. Then what are we going to have next? You see here, the next point that we have, let me actually move this graph away, the blue graph, okay? So I will put the blue graph where it's supposed to be. Here we have 90 degrees. This 90 degrees as well, that angle is also going to get divided by 2. Just like the period, all the angles now get divided by 2. And that's going to give you 45 degrees. So now what happened at 90 degrees, where we had 90 degrees and 0, we're going to now have at 45 degrees. So now we will have 45 degrees and a y value of 0. Then the next angle we have 180 degrees. Again, that angle is going to get divided by 2. And we're going to get 90 degrees. So what happened at 180 degrees in the original graph, where we had 180 and negative 1, we're now going to have at 90 degrees. So that's going to be 90 degrees and negative 1 as your y value. And then lastly, we have 270. Okay, so second last, 270 degrees, you're going to take that and you're going to divide it by 2, which gives you 135 degrees. And so we're going to take 135 degrees. Whatever happened at 270 degrees now happens at 135 degrees for this graph. So 135 degrees and 0. So that's your y value, 0. Then lastly, as you can see, it took 360 degrees here to complete a cycle. It's completing it in 180 degrees. What happened at 360 degrees, you say 360 divided by 2, will now happen at 180 degrees. So that's 180 degrees and 1. Okay, so this cos graph ends up looking like this. Okay, like that. It's squeezed. So that's this part, okay? This y is equal to cos of 2x. Now, all of this is not supposed to be happening as you calculating. I mean, you can do little sketches, but you probably do it with a pencil, then you can erase it, just so that you can draw the g of x, okay? But this really happens in your head most of the time. You understand the old cos graph and you start to translate it into the new one. So remember, the new one is actually this g of x, but I want to put that actually on this paper. So let's see what happens. Now we know this is what this graph over here looks like. But what will g of x look like? G of x says negative cos 2x. So remember that g of x stands for the y values, meaning when we say y is equal to cos of 2x, for example, when we say y is equal to cos of 2 bracket 0 degrees, okay, like this one here, we get a y value of 1, and you can even try that on your calculator. But because this says g of x is equal to negative cos of 2x, that answer that you get, that 1, is now going to be multiplied by a negative, okay, or negative 1 really, because g of x has a negative in front of it. So I'm translating the g of x graph now. So this is what's going to happen. All the y values that you had for your graphs, they're going to get multiplied by negative 1. So this is what our g of x is now going to look like. At 0 and 1, we're now going to have 0 degrees and negative 1. So that's what's going to be here, 0 degrees and negative 1. Then at 45 degrees, now we're going to have 45 degrees and 0. If you take 0, the y value of 0, and you multiply by negative 1, it still stays 0. So you still have 45 degrees and 0. Then at 90 degrees, you see we have a y value of negative 1. Instead, we'll have 90 degrees, and the negative 1 gets multiplied by negative 1, which gives you a 1. So 90 degrees and 1. 90 and 1. Then at 135 degrees, we're going to say 135. The y value is 0. 0 times negative 1 is still 0. 135 and 0. Lastly, we have 180 degrees and 1. That gets multiplied. It has a negative 1 now, so 180 and negative 1. So that's how that looks. But then, let's also understand now how will this part look? Because they said we have to draw the graph for this interval, negative 90 to 180. So the thing about the cost graph is, so if I draw this is going to look like this now. And then it curves down like that and like that. So that's what that looks like. So remember how I said that the cost graph is just going to repeat itself every 360 degrees, the original one, right? But now, of course, because this graph, its period has been changed, okay? We have 2x now. It now completes itself every 180 degrees. So this is what this one's going to look like. If we have the same graph, and I just want to show you what it's going to look like behind this. So if we drew intervals for negative numbers as well, like behind here. So if we drew intervals like this over here, you see the same graph, this exact graph. It will repeat itself again 180 degrees before this, because of course this graph has been altered, the period is changed. So look at this now. This graph is now going to be here again like that. You see? So the cycle is now repeating itself every 180 degrees. And so because it repeats itself, it means that whatever happened here is going to happen there again. So when we're counting this, we have 0 degrees. Then at this point again, it's symmetrical, you see. It's symmetrical here. So it's symmetrical where it started from. So from here, when you go backwards, it's going to do the exact same thing. Here, instead, you're going to have negative 45 degrees and 0. Okay, then here you had 90 degrees and negative 1. The next value, the next point, that's going to have a y value of negative 1 is now going to happen at negative 90 degrees. And then you had 135 degrees and 0. The next point that will have a y value of 0 again here would be negative 135 degrees. And lastly, of course, 180 degrees and 1. The next point is going to have negative 180 degrees and 1. You see what I mean by it is symmetrical. So that's how it looks. Okay, so from this one, now we know what this one is going to look like. Okay, so we have 0 degrees. Then at negative 45 degrees again, you're going to have, since this is 45 and 0, you're going to have another point here, 0. Okay, at 90 degrees, you had 1. Then it's going to happen again at negative 90 degrees. Negative 90 degrees and 1. So that's what the graph is going to look like. Okay, there. So something like that. Let me just make the line more. Okay, I'm just going to leave it like that. So the name of the graph is G. So just put G. But also just remember that they said that you also have to show or intercept minimum and maximum points of the graph. So I'm also going to just do that. For the intercepts, I'm not going to write the points down, because even on a parabola and stuff, you don't have to write those points if it's an intercept. If it's intersecting here at negative 2, you don't have to write negative 2 and 0. You leave it like that. Okay. So for the intercept, I will just leave it. So that is an intercept, 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 and here's a y-intercept. Okay, but this y-intercept, I'm going to write the point, because this, they said you need to indicate, show all the minimum and maximum points. I don't know if this is necessary, but since they said show all, so I'm just going to show it still. The coordinate here is 0 degrees and negative 1. So I'm just writing it 0 and negative 1 degrees. Okay. And then the another point that is a minimum or maximum would be here. We have a maximum. This graph will not go beyond this. That is the highest point. Then it starts to decrease again. So here we're going to have negative 90 degrees and 1. And of course here we have 90 degrees and 1. And lastly, we have this point 180 degrees and -1. Okay, so that's how I'm going to leave that graph, and that is 6.2. Okay, moving on to the next question. Okay, moving on to the next question. 6.3 says we need to write down the range of G. Okay, so if you think about how this graph goes, the range is all the possible y values the graph will have. So if we're looking at the y-axis, look at all the y values this graph is going to have. G, right? You see it has a y value here, and here, and here, even below here. But look where it will never go past. It will never go past 1. This is the highest y value it will have. You see, if you draw a straight line, you'll see it will never pass 1. And it will also never pass -1. That is the lowest y value this graph will have. So the range can be written as y is an element of from -1 all the way to 1. Now the kind of brackets you put here is important. If you put round brackets, you use round brackets for things like infinity and when the point is not included. What I mean by when the point is not included is if this y value is not an actual y value on this graph. In this case, this is a y value on the graph. You see, there is a literal point that has a y value of 1 and a literal point that also has a y value of -1. So because these points are included, I don't have to use round brackets, but rather square brackets. So that's how you'd write that. Other ways of writing this, you could have also just said y is greater than or equal to. Okay, so equal to because this is also a literal point, a literal y value on that graph. -1, but less than or equal to 1. So that's another way you could have also written that. Okay, moving on to the next question. The next question, 6.4, says the graph of G is shifted 45 degrees to the left to form the graph of H. Okay, determine, so 45 degrees to the left to form H. Determine the equation of H in its simplest form. Okay, so there is a new graph. The name of the graph is h of x. It is formed by taking g of x and shifting it 45 degrees to the left. Remember, when we're moving to the left, you're not going to minus because when you're moving to the left or the right, you are affecting the x value. When we're moving up or down, you're affecting the y values of the graph. So when it's moving to the left, you say plus. When it's moving to the right, you say minus. It's the other way around, remember, for the x's. But it doesn't work like that for up and down. So here, I'm saying the new graph of G is formed by taking all the x values of that graph. And then, because it's moving to the left, we're going to say plus 45 degrees. Now, all we have to do is apply this to the equation of G. So I'm saying h of x is equal to, let's find G. What you're going to do is, you see this is G of x plus 45 degrees. It was supposed to be G of x, meaning wherever you see x, you will replace it with x plus 45 degrees. So the graph of G was negative cos 2x. So instead, we're going to have negative cos 2 in place of x, x plus 45 degrees. And we have to now simplify this. Now it's weird that I put it like this. Cos has a bracket in front of it because it has an angle. So I'll just use big brackets here. Okay, so this is what we have. And we have to simplify this, put it in its simplest form. So h of x is equal to, we have negative cos. And so here we can distribute the 2 into these angles. And so we're going to have in a bracket 2x. 2 times 45 is positive 90 degrees. And then this is equal to, okay, so how do we simplify this? We have a 90 degrees, which immediately you see 90 degrees, you should think of co-functions. So let's think about co-functions. Let me put it in the right order. Notice that co-functions usually look like either 90 minus an angle, theta, or 90 plus an angle, okay? So instead, I'm going to rewrite it with 90 degrees first. So negative cos, then I say 90 degrees plus 2x. Okay, now we can actually change this nicely. So this is actually the same thing as, don't worry about the negative, we will apply that. But I'm focusing on the cos, this part, cos 90 plus 2x. This is the same thing as cos 90 degrees plus theta. What does this one become? Remember, in your cofunctions diagram, it's the only one that becomes negative. So it becomes negative, and because it's a cofunction, it changes to sine theta. Okay, same thing we're going to do here. So we still have this negative on the outside. Then this becomes negative. So I'm going to put brackets. Negative sine of whatever angle we have. We have 2x. That's what we're using, not theta. We're using 2x here. So 2x. Then lastly, h of x is equal to, we will take that and multiply it in, distribute it, and we have a positive sine of 2x, and that's h of x. Okay, so that's how we work through that one. Okay, moving on to the next question. So 6.5, we have used the graphs to determine the values of x in the interval where x is an element of negative 90 degrees to 90 degrees. This is important to take note of. It's not the same as all the other ones they have been given us like that, you see. So that stops at 90 degrees. Okay, and for which, first they're asking us about f of x. F of x is the original graph we have. F of x needs to be greater than 1. So we need to find out where is f of x greater than 1. So looking at our graph, remember the tan graph, that is our graph of f. H was this new one that we just created. Okay, so this is our graph and we need to find out where is it greater than 1. All you have to do here is, okay, I was just trying to get those out of the way. So this is what we have, right? We're looking at the graph of tan because that's f, right? And we just need to see the places where it is greater than 1. So mark a line, a horizontal line, because greater than 1 refers to the y values. So where is it greater than 1? Here's 1. These are all the numbers greater than 1. So here you can mark a horizontal line so that you can find out where is this line above 1. Okay, so where is this graph above 1? So look at it. It's over here. That's greater than 1 over there. It's also greater than 1 over here, but this is where now you need to hold on and consider whether we can take this or not, because you always have to look back at the instruction. You see, they said where x is an element of negative 90 to 90. So let's already mark a barrier line so we know we don't take past that. Okay, so is it only for this question? No, it's for both questions because they put it here. So we're going to put a line here. I'm not going to take anything past that. So I'm not even going to consider that. I can't take that anymore. They want only greater than 1 between negative 90 to 90 degrees done. Okay, they didn't say greater or equal to 1, just greater than 1. So it will be everything above here. So here, okay, that point over there, that point, keep going. So let's see, what are the x values that belong to this point? Look at that. If you line it down to the x-axis, it's this point over here. You would have to compare it to negative 90 degrees because at negative 90 degrees, the y value of this tan graph is 1. Okay, so these numbers, look at the numbers here. They are numbers that are what than negative 90 degrees. They are moving towards the side, so greater than negative 90 degrees. Okay, and it's a tan graph. Remember, the tan graph has asymptotes. Look at the first asymptote it has at negative 45 degrees. So it's here greater than negative 90 degrees, but it will not go beyond this because there's an asymptote here. And then, of course, after the asymptote, you see, look at the graph. They all have values less than 1. So the answer for that would just be where x needs to be greater than negative 90 degrees, but less than negative 45 degrees. Okay, that would be your solution for that. Okay, so that is that. Then we move on to the next question, the last question for question 6. Then 6.5.2, we have to determine the values of x for which 2 cos of 2x minus 1 is greater than 0 for, of course, those same intervals. Okay, for these intervals. So with this question, you see, at this point, this is the last question. They will not introduce a brand new graph. As you can see, you see the cos 2x. It's probably related to that graph of g of x. And just remember, g of x is equal to, let me actually put it in blue so we'll focus on it more, is equal to negative cos of 2x. So let's take this inequality and let's try to get that part to become negative cos of 2x. So if we have 2 cos 2x minus 1 is greater than 0. And then let's think about what we should take over. Notice that this one is negative, negative cos 2x. Okay, so we want whatever has cos 2x to stay negative. So how about we just take that over to this side? So this is now negative 1 is greater than negative cos of 2x. Then, of course, we have to solve for this part. But remember, we want negative cos of 2x to stay. So I'm going to try and leave this here, meaning I just need to get rid of the 2. So let's divide both sides of the equation by 2. And so here you have negative a half. Remember, we divided by positive, not negative, so that doesn't change. And then we have the sign, and we have now still the 2's here cancel. You're left with just the negative cos of 2x. Okay, now we know we have g of x over here. Let me just rewrite this in a way that it's just going to make more sense where this is in front. So I'm just going to put negative cos 2x over here. The negative a half is over here. Now you just have to follow the sign of the inequality. You see, the open side of the inequality, the mouth, is facing the negative half. So here, write it facing the negative half. So this is basically what we have. And so they basically want us to find out, since this is the graph of g of x, where is g of x going to be less than negative a half? Okay, so where is it going to be less than negative a half? Let's look at the graph. So if this is the graph of g of x, but remember, we have to find out where it's going to be less than negative a half between negative 90 degrees all the way to 90 degrees. Okay, so I'm going to draw a line here, again, just to separate that. I'm not going to go past this. So if this is 1, 0, negative a half would be somewhere here. So if we have negative 1 over 2, right? I want to find out where the graph will be less than this. So I'm just going to draw a horizontal line representing that point, negative a half. And I just want to find out where does the graph have y values that are less than negative a half. So as you can see from that, that would happen in all these places over here, all the way here. Let me just use something darker. So it's all these points in between here. But where does it start? In other words, where is the cos graph itself? Okay, where does it have a y value of negative a half? You see that it has a y value of negative a half here because this is the y value. We need to find out what exactly that x value is. And where else does this happen throughout here? So here, if you look throughout, it also happens here again. Okay, here the graph has a y value of negative a half. We also have to find out what exactly that x value is. And obviously, if you do go on, you also see that the graph would have also intersected here. But the reason I'm not going to even bother about that point is because we cannot go past this line. We must go from negative 90 to 90 degrees only. Okay, so how do we find out now what these two values are? So you can see it's between 0 and 45 degrees and then 0 and negative 45 degrees. Remember that the cos graph is symmetrical. First of all, we will be able to find this one over here. Okay, the reason we'll be able to find this one over here is because we have the equation of the graph of cos, negative cos of 2x. So this is how we will find this one over here. Okay, it's the one that is between 0 degrees all the way to 90 degrees. So I'll do that over on this side. So this is how we can find that. Since we already know the equation of the graph, right? And we need to find out where the graph is equal to negative a half. I'm just going to say, where is negative cos of 2x equal to negative a half? And all I'm going to do here is solve for x. And I'll show you what it means when you solve for x. Okay, so I'm going to solve for x just to find that first point. So it's not going to be as general solutions. We're just solving for x, that's all. So if you solve for x here, first of all, we need to get rid of that negative. Divide both sides by negative 1. Cos of 2x is now equal to positive a half. And then to solve for x, you're going to have to take cos over. And so you have 2x is equal to shift cos of a half. And this is really a grade 10 kind of equation that you would have seen. In grade 10, you guys got equations like this. Okay, so 2x is equal to, if you say shift cos of negative a half, so shift cos negative 1 over 2, it gives you 120 degrees. Okay, so oh, why did I say negative 1 over 2? It's 1 over 2. 1 over 2, sorry. It gives you 60 degrees. Okay, that didn't even seem right. So it gives you 60 degrees. Then we have to solve for x, of course. Divide both sides by 2. And look at what we get. X is equal to 30 degrees. I want to show you what this means in the graph. So x is equal to 30 degrees. This is where it happens, here. Okay, that's where we get that 30 degrees. So since we know this is 30 degrees, remember what I said about the cos graph. It's going to repeat itself basically. Remember, this is just negative cos of 2x. It's not negative cos of 2x minus 45 degrees. It's not being shifted to the left or to the right. The period of the graph is just being changed, and of course the y values are being multiplied by -1. So if this graph is doing this over here, right, all the way to 180 degrees, it completes one cycle. It's going to do the exact same thing after 0 degrees, or really just before 0 degrees. So exactly the same thing. So think about it like this. If you have 45 degrees, we have a y value of 0. Then at -45 degrees, you also have a y value of 0. Then if here at 30 degrees, we have a y value of -1/2, then it means that -1/2 as a y value will appear again at -30 degrees. Okay, so now we know these two numbers, right? And we're just basically trying to find out where is the graph of this, right, going to be less than -1/2. That was the inequality. So we found out that this is this region over here. Let's map it to the x-axis. So you see, it's a point here, here. These are all the places where the graph of g is smaller than -1/2. So what are these x values? You see, they lie between -30 and 30, all of these values. So it's where x is greater than -30 degrees, but less than 30 degrees. And that will be your solution for that. So there we go. X is greater than -30 degrees, but less than 30 degrees. Okay, moving on to the next question, question 7. Okay, so we're on question 7, and question 7 says, in the diagram, A, B, and C are points in the same horizontal plane. Okay, so there it's on the same horizontal plane. So it's kind of like the ground of this. Then we have D is a point directly above C. That is, DC is perpendicular to AC, and DC is perpendicular to BC. So there you have perpendicular lines. Then they say it is given that ACB is 100 degrees. So there's 100 degrees, CAD is 30 degrees, AD is 20 units, and BC is 8 units. Okay. They want us to first calculate the length of AC. Okay, so when you see them asking you actually for numbers, it feels better than them asking you for you to just determine, let's say, AC in terms of x. It's better than that, honestly. So we have the length of AC. AC is this part over here. How do we find the length of AC? Just look at what is AC part of, what triangle is it part of? Well, it's part of this big triangle, but unfortunately here all we have is 100 degrees and 8. That's not enough to actually find this length. So we can focus on this triangle instead. So this triangle is right angled, which is good, meaning you can possibly use Pythagoras, but as you can see, Pythagoras is not possible here. You only have one length. You don't even have that. Neither do you even have AC. Second thing to use when you see right angles would be trig functions. Okay, so if we're using trig functions, let's first of all understand which sides we're going to use. Definitely we're going to be using AC because it's what they asked us for. You have to relate AC to 30 degrees. Where is AC in respect to 30 degrees? It is next to 30 degrees. So this is your adjacent side. Then in this same triangle, you need to take something that you already have, like the length of something that is already available, which would be AD. AD is 20 units. We know that already. And what is AD in relation to 30 degrees? It is the hypotenuse. Okay. So you see the function we have here, we have adjacent and hypotenuse. Where does that appear? So if you remember that word SOHCAHTOA, so about cos, sine, and tan, you see that adjacent and hypotenuse would appear in cos. So you're going to use cos for this. So we're going to say cos of what? Cos of the angle that we're referring to, that we related these sides to. That was 30 degrees. Cos 30 degrees is equal to the adjacent side, which is AC, over the hypotenuse, which is 20 units. And all you have to do now is just solve for AC. So get AC on its own. To get AC on its own, we need to get rid of the 20. We can multiply both sides by 20. And so this will give us 20 cos of 30 degrees being equal to AC. So you can put that onto the calculator and see what you get. And that gives us 10 square root of 3 units. So that is the length of AC. Moving on to the next question. So I'm going to actually put that down just because we need to really always put down what we have. So that is 10 square root 3. Then next question, 7.1.2 says we need to determine or calculate the length of AB. AB, now that we have AC. So AB, A all the way to B, opposite it, we have 100. If we had one of these angles like this, we could have easily just used the sine formula, but we do not have that, so we can't use that. Okay, so let's look at what else we can use. Since AB is part of this bottom triangle, you see that we have BC, we have AC, we have the middle angle. They want us to find AB. So this is clearly the cos rule that you have to use. So remember, the cos rule basically says you always have to start with the length. We'll say this length, AB squared, is equal to, then you take the other length, BC squared, plus that one, AC squared, minus 2 multiplied by BC multiplied by AC, and then you say cos of that angle, okay? And the angle is 100 degrees. And in this case, this formula is fine because we want AB. I apologize for the noise outside. I'm not sure if the mic is picking it up. Okay, so looking at this, we're going to just say AB is finally equal to, AB squared is equal to, what is BC? BC is 8, AC is 10 square root 3, so 8 all squared plus 10, well, you don't have to all say all squared, it's just 8 squared plus 10 root 3 squared, and then minus 2 multiplied by 8 multiplied by 10 square root 3 cos of 100 degrees. Okay, so you can put this all onto the calculator and let's see what we get. Or you can already from here square root both sides. So square roots just to find AB. And so AB is equal to all of this. Okay, just make sure you punch everything in properly. And when you put that 10 square root 3, make sure you just come out and then square it, okay, with the side. And so you see AB is equal to 20.2 decimals. It looks like it could be 1 decimal, but okay, 20.30 units. Then moving on to 7.2, it says, if it is further given that ABD, angle ABD, is 73.4 degrees, calculate the size of ADB. Okay, so with all these questions, always make sure you fill in what you have. So AB is now 20.30 units. I'm going to put that in there so I know that is now 20.30. Okay, so let's see what they're saying. They said if angle ABD 73.4 degrees. ABD is ABD. You see, that is actually this whole angle. Okay. So this is a 3D object. This is like the face of the object. We're looking at that angle. Okay. So that angle is the 73.4 degrees. If that is the case, they want us to find ADB. So what is going to be ADB, this angle? Okay, so let's look at what we have. We unfortunately don't have this entire angle, this face, okay, this part here, the DAB. So we can't use interior angles of a triangle, but let's look at this. Since they asked us to find this angle, what side is opposite it? It's this side that we found, 20.3 units. And the angle that we have, it should also have an available side opposite it. So here it has an available side, 20 units. So we can use the sine rule for this. Okay, because we're looking for an angle, I'll start with the angle first. So I'm going to start by saying sine of that angle. Actually, we would have just called this angle D, but okay, let's just call it ADB over, and then over the side that you have. The side you have is 20.30. So 20.30 units is equal to, again, we're going to have to say sine of the second angle we have, which is this over here, the 73.4 degrees, over the side opposite it, which is 20 units. Okay, this is our equation. So we just have to solve for this equation as it is. Remember, we're just trying to find the value of angle ADB. So instead of cross multiplying, something we can do is try and make sine of ADB the subject by getting rid of 20.30, and you do that by multiplying both sides by 20.30. Okay, 20.30. Then we're going to have sine of ADB is equal to, and we have all of this basically. So when all of this is being multiplied, this is sine of an angle. This can go in front of it because it's a number that you're multiplying to this function. So it's now 20.30 sine of 73.4 degrees all over 20. Then to solve for ADB, so to get that angle ADB, you're just going to take sine over. So now we have ADB, that angle is equal to, and when sine comes over, it becomes the inverse, which is shift sine, and then we just say 20.30 sine 73.4 degrees all over, close that bracket. So that's going to be very important in the calculator, over 20. Okay, so let's see what we get here. Okay, and so ADB, angle ADB is equal to 76.58 degrees rounded off to 2 decimal places. And that is it for question 7. And okay, we're on question 5, and 5.1 says, in the diagram below, P is the point 12 and 5. And then we have T is A and B, and they tell us that OT is perpendicular to OP. As we can see, we have a 90-degree angle there. And they also tell us that PS is perpendicular to the x-axis. Okay, also a right angle triangle over there. And POS, angle POS is equal to theta. And the questions are, the first question is, without using a calculator, determine the value of tan theta. Okay, so let's go ahead and start with that one. So with 5.1.1, tan theta, we're really just looking at this diagram. So do you see that we don't really need, since we know the tan, right? Remember the tan using SOHCAHTOA. The TOA part is for tan, which is opposite over adjacent. So you don't even need the hypotenuse for this. So don't go ahead and start finding it now. You don't need it here. So we're going to go ahead and say the opposite side. Let's go ahead and see what exactly that would be. Here's theta. The opposite side is this. Now, what exactly is this in our coordinates of P? As you can see, this is a vertical line, meaning it's telling you what exactly your y value is. So the y value is 5. And then the x value, okay, that's your adjacent side. That is 12, because you're going to go 12 and then 5 up to get the point P. So since we have that, the opposite side is 5 and the adjacent side is 12. So there we go. That's our answer for the first question. And the next question, 5.1.2 says, we need to find sine theta. Now we need the hypotenuse. So we're going to have to use Pythagoras since we have a right angled triangle. So we're finding OP. So we can say OP squared. So let me just say 5.1.2. OP squared equals, and we're going to take the shorter side squared plus the other shorter side squared. So that's 5 squared plus 12 squared. And then we're just going to find the square root of this. So what exactly is that going to give us? OP would be the square root of all of that. Let's just find that on our calculator. And we get 13. So that is equal to 13 finally, right? So now that we know the hypotenuse is 13, we can actually find sine. Sine is SOHCAHTOA, is the saw part, which is the opposite side over the hypotenuse. So opposite over hypotenuse, which is going to be, our opposite side is 5 over hypotenuse, which is 13 as we see there. And that will be our answer for that. Okay, moving on to the next question. So let me actually just tell them that sine theta equals 5 over 13. So we'll get our full 2 marks. The next question is 5.1.3, which says, you need to, without using a calculator, determine the value of A if TO is equal to 19.5 units. So TO is 19.5 units. And you need to find exactly what the value of A is. Okay, so this type of question has shown up a few times. So what we're going to do here is we are going to use the theta and the fact that they gave us 90 degrees over here. Because they're speaking about T, which is in the second quadrant, we can go ahead and drop a vertical line down. And we know we're referring to this triangle over here. But what's the reference angle that we're using? Well, you notice how in these diagrams, right, you always have the angle being drawn from the x-axis to the line, okay, to that radius or that terminal arm. It's always been drawn like that. Well, that's the angle that we have expressed here. What happens is you can, using your reductions, reduce the size of that angle so that it becomes an acute angle. Okay, so we really just need to find what exactly the size of this angle is. The size of the angle that OT forms an angle that is made up of the theta and the 90 degrees, which if you calculate is really 90 degrees plus theta altogether, theta and 90 degrees. So that's our reference angle over there. So we can go ahead and use that angle and we're going to use it to find A. But we need to do this in a way that is actually going to help us to quickly find A. So let's figure out where A is in our diagram. A, as you can see, is your x value. So your x value is going to be here. Just like you see, this was the x value 12, right? Because we have to go 12 units to the right, then 5 units up. So that is our x value over here. That's A. And then B is our y value because that's the height. That's y. So B over there. So in order to find A, do you see that A is your adjacent side, ironically? Okay, it's not because it's A, it's just because it is the actual adjacent side. Since your angle, your reference angle is this side, then your adjacent side is here. B is the opposite. Since they gave us 19.5, let's try to focus on using that hypotenuse and only the A. So if you're using an adjacent side and a hypotenuse, what function are you going to use for that? The function with A and H, adjacent and hypotenuse, would be cos. So katoa, okay? Cos. So let's go ahead and use cos here. So with 5.1.3, what we're going to say is we're going to find cos of this angle 90 degrees plus theta. So cos 90 degrees plus theta, and find out what exactly that is equal to. So cos 90 degrees plus theta is equal to our adjacent over hypotenuse. Okay, we have to use what they asked us to find and what they gave us. So that's A over 19.5. That's A over 19.5. But here's where we use some of these trigonometry rules that we know. So when you look at this, cos 90 degrees plus theta, what does that look like to you? That is cofunctions. So if you look at cofunctions, which I'm putting on the screen right now, right, the cos 90 degrees plus theta, that will give you negative sine theta. And you see how it gets reduced to theta again. So negative sine theta is equal to A over 19.5. And now we just need to solve for A. Okay, so to find the value of A, well, we already know what sine theta is. In relation to the diagram that we have here, this was in terms of theta. We knew what sine theta was. Sine theta is 5 over 13. So negative sine theta is negative 5 over 13. See, we're using the other diagram to help us solve for this diagram because it was in terms of theta. So this is equal to, and we can go ahead and say, well, let me write it like this. Negative 5 over 13 is equal to A over 19.5. My A always looks like a 9. Okay, so there. Now we just need to solve for A. As you can see, since A is over here, Instead of cross multiplying, because then you're going to have to divide, you can just get rid of that denominator of 19.5. Since we're dividing by 19.5, to get rid of it, you multiply by 19.5 on both sides. So really just saying that cancels and you have a alone is equal to, and if you say 19.5 multiplied by negative 5 over 13, you would get your answer. So let's go ahead and do that. And that gives us, well, you can put it as a fraction if you want, but as a decimal, it gives us negative 7.5. And that is our value for A. Okay, moving on to the next set of questions. The next question, 5.2, says, determine the value of the following without using a calculator. So we have a trig expression and we have to simplify it. Always just make sure you simplify everything that you can, okay? If something is too big, you reduce it. If there's a negative angle, add 360 degrees to it. If there are co-functions, use your co-functions. And the main thing is be careful when simplifying, to simplify carefully and not quickly so that you don't make little mistakes. Okay, so what we have here, we have sine 360 minus x, just like sine 360 minus theta. That is in cos's quadrant. It's supposed to be in cos's quadrant and sine is negative here. So that would become negative sine of our angle there, which is 2x. Then we have multiplied by sine of negative x. So I'm going to actually simplify on screen just to show you what happens. You see that we have negative x. X represents your angle, which means your angle is negative. When your angle is negative, you need to add 360 degrees. And so what really happens is that becomes sine 360 degrees minus x. And if you simplify this, it becomes, because it's in cos's quadrant and sine is negative there, it becomes negative sine x. Okay, all over. And over there, you see that you have co-functions. Remember your co-functions? Okay, so that simplifies to positive cos x. Then we continue plus, and we have 2 cos squared of 180 degrees plus x. Now, regardless of whether the cos 180 degrees plus x becomes positive or negative, it still gets squared because we have squared over there. So the reason I'm saying that is because if you simplify that, you see that that is actually tan's quadrant, that 180 degrees plus theta, right? So you know that that's supposed to become negative cos x, but then it gets squared. So it becomes positive afterwards. So that is 2 cos squared x. Okay, so this is what we have now, and we're just trying to simplify. Okay, so first and foremost, we see x, and then there's a 2x. So clearly that needs to go, that needs to change. What can we do with sine or negative sine 2x? Well, first of all, these two are multiplying and they're both negative. So they're going to, the negatives will become positive. So the negatives are gone. And when we go ahead and simplify that, that is double angles. And we only have one expansion for that, which is 2 sine x cos x. And then we multiply that by sine x. And this goes all over cos x. Convenience, okay? You see that those will cancel. And we have plus 2 cos squared x. And this is equal to our coses, cos x and cos x cancel because we are multiplying all through. If there was an addition sign here, you can't cancel that cos x. Okay, so then we have that. And this is now 2 sine x times sine x is sine squared x, and there's no denominator now, plus 2 cos squared x. And as you can see, this looks like the identity for sine squared x plus cos squared x being equal to 1. So the only thing here that we need to take out is the common factor of 2. So take out 2 as a common factor, and we have sine squared x plus cos squared x. And we know that they give us 1, like the identity. So this is equal to 2 times 1, which is equal to 2. And that is our answer. Okay, so that was quite simple. Just make sure you practice a lot of these grade 12s. And the memo is there. You can use the memo. Just ensure that you are practicing first before looking at the memo. Because if you keep looking at the memo and you keep seeing the answer, it doesn't actually help you get there. The thing about maths is that you have to kind of struggle to get to that answer. Okay, so just keep pushing. Okay, moving on to the next question. And we move on to 5.3. And 5.3 says cos 42 degrees is equal to the square root of k. So without using a calculator, determine the value of sine squared 69 degrees in terms of k. Okay, since they told us cos 42 degrees is equal to k, and we now need to express this in terms of k, then we need to find a way to make that angle 69 degrees, right? To get it to look like 42 degrees, to get it to actually be 42 degrees in some way, or really just get it to relate to 42 degrees. Now, the angle that we have is already acute, so we can't even reduce it. So since reduction does not work, what we can just decide to use is cofunctions, okay? Because it's another form of somewhat reducing an angle, okay? We can try using cofunctions. So I'm going to go with cofunctions because I can't really reduce 69. So let's start off. We're saying sine squared 69 degrees. And let us go ahead and use cofunctions. So we're going to say sine squared of 90 degrees minus what gives you 69 degrees. So if you say 90 degrees minus 21 degrees, okay? And then you can apply the cofunctions to this. So this, just like in our cofunctions, right? Since sine 90 minus a is equal to positive cos a, we're going to go ahead and say this is equal to cos squared of 21 degrees. Now, I don't have to consider that it's squared because the thing is that if you find sine 90 minus 21, it becomes positive cos 21. So I don't have to really just overthink this squared because it's not going to become a negative either ways. Okay, so we have cos squared 21 degrees. And now what can we actually do with this? So we're still trying to focus on how can we get this to relate to 42 degrees? Well, 21 and 42, they do actually relate with each other. Do you see that 21 degrees is exactly half of 42 degrees? So that means we're probably using double angles. So this is half the angle, you know, with your double angle formulas, as you can see them here, right? We have, since these are speaking about cos, right? Cos 42, and we have cos squared of 21 degrees, which is half of 42 degrees. We know that we're going to be using the cos 2a formula. So what I'm looking at this as is the 21 degrees, because it's half of 42 degrees, that's going to stand for your a. Okay, your a is the 21 degrees, and then the 2a is double 21, which is 42. Okay, so this is how we can use this. So we're going to use the cos formula, that one, the cos 2a, the double angle formula for that, which is cos 2a equals, and we can use the one with the cos squared since we have a cos squared of a, okay, half that angle. So we can use this one, which says 2 cos squared a minus 1. And this is going to be equal to, we have cos of 2a here. So that is 2 times, we know a is 21 degrees, which is, if you simplify, is really just 42 degrees. So cos 42 degrees is equal to 2 times cos squared of 21 degrees, which is our a, and then minus 1. Now, remember what we're trying to solve for. We're trying to express this, the value of this, in terms of k. You already know that sine squared 69 degrees, that's what is equal to cos squared 21. So you just have to make this the subject, cos squared 21 the subject, and by doing that, you would have found sine squared 69 since it was equal to that. So let's go ahead and make that the subject. Okay, because it's already positive here, I'll leave it here and leave this as cos 2 cos squared 21 degrees, but I'll take that negative one over. But here, remember, it needs to be in terms of a. We have a cos 42 degrees here, and they told us that cos 42 degrees is equal to the square root of k. So that's the square root of k, which is equal to this. And we're taking this negative one over and becomes a positive one. Okay. Remember, we're just trying to solve for the cos squared 21 because that is equal to sine squared 69. So we're going to have to get rid of the 2 by dividing both hand sides by 2. And so this means that cos squared of 21 degrees is finally equal to the square root of k plus 1 all over 2. And that is our answer. Okay, that is for 3 marks. And we move on to the next question. Okay, we're on question 5.4, and it says, given the identity, and we have sine 5x cos 3x minus cos 5x, and then all of that over tan 2x minus 1 is equal to negative 2 sine squared x. And we need to prove the identity. So already from looking at this, you can see the left-hand side has more detail than the right-hand side. We can actually expand it and simplify it further and get it to this point. So we're going to go ahead and start with the left-hand side. So we'll just say left-hand side equals and rewrite what we have on the left. And now that we have this, we can go ahead and start simplifying. So I want you to notice something about this. Do you see that we have sine, cos, sine, right? And then we have 5x, 3x, 5x, 3x. That is the order of compound angles. So that is the compound angle for sine, the one with a minus. Just like we have that in the form of sine A, cos B, and minus cos A, sine B, okay? Because you see, the A is consistent. It's both 5x and the B is consistent. That can get reduced to sine of, just like the way that gets reduced, it gets reduced to sine 5x, and we have minus 3x, okay? Sine A minus B. That's what it gets reduced to. And we have over. Now I'm already looking at tan, and tan can be changed to sine over cos. So let's just change that. Because this is one fraction on its own, I'll just give it a bracket. So put it together. And we know that this is being divided by tan 2x, which is really sine 2x over cos 2x, right? 2x. And then we have minus 1. Okay, so we'll apply that later. So this gets reduced to 5x minus 3x is 2x. So that's sine 2x. Divided by, but because we're dividing by a fraction, you can tip and times. So you tip by swapping the numerator and denominator of that sign, right? And then you change your division to a multiplication sign. So we have that, and we have minus 1, of course. Now, when we have this, do you see that we can actually cancel the sine 2x diagonally? They will cancel. And so you're left with only cos 2x minus 1. Let's just look at what we need to get it to be. We need to get it to be negative 2 sine squared x. And the first thing I already noticed is, first of all, that is sine, and there's no 1. So the fact that it's already sine, you know that you have to change that cos 2x to one of the expansions of cos 2x, right? But that has a sign. And that one would be the 1 minus 2 sine squared x. And then we still have minus 1. So what happens here is your positive 1 would subtract with your negative 1 and become 0. And you're just left with the negative 2 sine squared x. And that is equal to your right hand side. And we have proven the identity. The left hand side is therefore equal to the right hand side. Okay, moving on to the next question that comes after this one. Okay, so it's like general solutions, and then we're just going to actually find the specific solutions. So you're going to treat this as your reference angle, and I'm going to try and use this as a way to correct a mistake that I made in that general solutions video I made when I spoke about the easy method, the quick method, and the standard method that we work with. Let's say we had tan of theta was equal to negative root 3, right? And so you were trying to solve for theta, like the general solution. So we would say our reference angle is equal to, now I don't consider the, quadrants, okay, because that is the standard method that we work with, but I was working through it using the quick method. I just want you guys to remember this. With this one, when we take tan over and we find shift tan of negative 3, which is going to be negative 60 degrees, shift tan negative square root 3, sorry, right? It's negative 60 degrees. So we're going to use that angle like that. Once we find our solutions, remember for tan, it's very simple. You don't have to overthink this. You just say theta is equal to whatever that was, and then you say plus k of 180 degrees. If you want to make the angle positive so that the answer looks like the answer you would have gotten if you used your quadrants, the standard method, right? Make sure you add 180 degrees to make it positive. The reason why is because the tan graph repeats itself every 180 degrees. Okay, it has a cycle of 180 degrees. So if you want to get that to become positive, you have to add 180, not 360. I know I said 360 there. I was a bit tired. I was already working on the paper 2 of May to June 2024, and I had to edit it that same night, so I didn't see that mistake. I apologize for that. Okay, so we're going to work on this. We just need to make tan of 2x be equal to 0. Okay, so tan 2x being equal to 0, let's solve. So just like we worked on that other one, we're going to find the reference angle. So say reference angle is equal to shift tan. Of course, you won't include this. It's not necessary. Of 0. Okay, now tan 0 is still 0 degrees. It doesn't really change. So our reference angle is 0 degrees. So now that we're solving for x, we're going to take this value here, okay? That was in front of tan. You're going to take that and say 2x is equal to, and we are going to take our reference angle, and then you're just going to say plus k of 180 degrees. And done. That's the quick method, right? So we're just saying it's 0 degrees plus k 180 degrees. And as you can see, once you divide both sides by 2 to solve for x, and then when we divide both sides by 2, we get x here is equal to 0 divided by 2 is 0 divided by 2 is 0 degrees. And then k 180 divided by 2. 180 divided by 2 is 90. So that is k 90 degrees. Okay, so remember that you need to solve for this interval. Okay, you need to solve for x within that interval. Remember, k is an element of integers. So it's not a big interval, so it won't take that long to solve really. You're just going to go ahead and substitute values for k and see which ones work. So we can actually solve for x here. Because it's just 0 plus k 90 degrees, it can't really go much places. You can decide to substitute in place of k. You could substitute 0, okay? And if you substitute 0, because we need to substitute only integers, you see that the x value you're going to get there is 0 degrees, and then 0 times 90 is 0. So that's 0 plus 0, so you get 0. And we know that 0 is within that interval. And then if you put anything other than 0, it's really not going to work. It's just going to be either too big or too small. So if you try, for example, -1, -1 times 90 is -90. 0 plus -90 is still -90. That is way beyond the interval. It's too small. And if you tried +1, that's going to be +90. 0 plus 90 is 90. That's also above. So in this case, right, that's all that works if you make tan equal to 0. But here's what we need to consider. They want us to tell them the value of x for which the identity is going to be undefined. And the reason why I'm doing this is because we're specifically using the function tan. You see, the tan graph has something that sine and cos graphs don't have. It has asymptotes. And those asymptotes, at those places that it has asymptotes, the graph is actually, well, if you found the equation of it, for those x values, it's undefined. Okay, so because it doesn't have a y value at those points. Okay, so, and you just need to remember where exactly this happens. So remember we have tan 2x here, right? But the normal tan graph, the y equals tan theta, where does it have an asymptote? And we don't have to overthink this just because the interval that we're using is really small. So I'll just use a tan graph that goes from 0 to 180 degrees. I will not be too extra with this. Where this has an asymptote is at 90 degrees. It has here, okay? If you find tan 90, it's going to say error on your calculator because there is an asymptote at that point. So tan of 90 degrees, complex infinity, okay? Because there is an error there because of the asymptote. So we have to also consider this now because it's a tan graph. So you see, this is something that you need to include in your answer, okay? If they ask you this question and you see that denominator was tan. Okay, so in this case, how do we actually find out what x should be here so that we don't end up including this asymptote? So in this one, right, because this is the graph of y equals tan theta, this is when tan, right, we have tan 90 degrees, when the theta is equal to 90 degrees. But remember here you have 2x. So if you know that tan 90 degrees would be undefined, right? Then what exactly should x be if the function we have is tan 2x? Well, to get this to become 90 degrees, you would have to make x 45 degrees because 2 times 45 is 90. Tan 2 times 45 degrees then is going to be undefined because of that tan 90. So that's another thing we have to include here. So I'm saying this because this is a situation of tan. So you just remember that if you ever have a denominator of tan and they ask you that question, for which values of x would it be undefined, you need to include that because of the asymptote that it has there. So, or x should be equal to 45 degrees because at 45 degrees for this function, that's going to make that angle 90 degrees, and at 90 degrees we have an asymptote. So that is our answer over there. X is equal to 0 or x is equal to 45 degrees. And we move on to the next question. Okay, 5.5 says, given f of x is equal to 2 cos x minus sine squared x, we need to show that f of x can be expressed as this. So in other words, you need to get this to look like that. Okay, let's go ahead and take what we have. We have f of x is equal to 2 cos x minus sine squared x. So we have to get this to look like this. The first thing I notice is that we don't have a sine. So I know that we need to change that clearly. And what I do notice here is we don't have a sine, but we only have cos. So let's go ahead and change this sine squared x into its identity. You know that sine squared x is equal to 1 minus cos squared x. So we're going to change it to that. So we have f of x is equal to 2, and we have cos x minus, now that becomes, we need to put brackets because we have two terms. So that's 1 minus cos squared x. Okay, so f of x is equal to, and we have 2 cos x, and that distributes and becomes a -1 and becomes a positive cos squared x. Okay, it's a trinomial. Clearly it's a trinomial. We can put the one with the squared first, so it's in the order of its exponents. So cos squared x, and we have positive 2 cos x and -1. So can we get it to look like this? I'll think about factorizing, but remember, this is like saying k squared plus 2k minus 1, okay? If you look at k as if it's cos x. If you're trying to factorize that, you see that with the 1, you can't actually factorize because you get k and k, but then what are the factors of 1 that can give you 2? That's not going to work, okay? Factors of 1 can't give you 2 because factors of 1 is just 1 and 1. So how else? And that's already negative, okay? So 1 has to be negative, 1 has to be positive. So either way, it's going to cancel and just give you 0. So what else can we do? How else can we simplify this to get it to look like this? When we're simplifying, we try to factorize because factorization helps you to simplify expressions. But we can't factorize that using trinomials. However, you remember that if you try to factorize something and it didn't work, you would usually try using, and it was a quadratic expression specifically, right? What you would usually do is go ahead and use the quadratic formula. Now, the quadratic formula comes from somewhere, okay? It comes from actually taking a quadratic expression and completing the square on it, well, a quadratic equation, and solving for this by completing the square. So what I'm saying here is when you complete the square on an expression, a quadratic expression, what you're actually doing is factorizing it. Let's go ahead and complete the square. Now it's going to be a bit different because you're kind of used to completing the square on expressions that just have like x. So let's just be careful as we do that. When we complete the square in an expression, you always ensure that the coefficient of x squared is 1. And in this case, we're going to be looking at this as the coefficient of cos x, right? And it is 1. So we don't have to divide it by anything. That's fine. We don't have to take out any common factor. So we'll leave that. Then the second thing we do is we look at the coefficient of b. In this case, our b value, let me just rewrite it like this. It's kind of like having k squared plus 2k minus 1. So our b value, right, like bx, but in this case bk, our b value is 2. You would take that value, the coefficient of b, and you would half it, so divide it by 2, and then square it. And that's going to give us 2 over 2 is 1. So that's 1 squared. So we're going to use this number. Because this is an expression, we are going to take this number and add and subtract it to the expression. So this is what we're doing. We have cos squared x still, and then we have plus 2 cos x. Then we're going to take this and we're going to add it to the expression 1 plus 1 all squared, and then subtract it minus 1 all squared. And the idea behind that is we're not tampering with the value of the expression, we're just tampering with the way it looks and changing the way it looks so that we can better simplify it. And then we still have our minus 1 at the end. Okay, let me leave that in black, minus 1. And then we're factorizing. So remember, when factorizing this, when completing the square, you see that cos squared has a squared. And it's always going to be the third term. This one also has a squared. So what we're going to do is rewrite them into the same bracket. So put them together like that. And so we're going to have the cos of x, and we have our positive 1. Now, it's not positive because of this positive outside. It's positive because the inside one is positive. That 1 is positive, right? And then we're going to put their squared outside. The idea behind that is that if you actually take this and you factorize that trinomial, you will end up with cos x plus 1 times cos x plus 1, which gives you cos x plus 1 all squared. So we're just completing the square here. Then we still have to just simplify that. You see that's negative and we have 1 squared. 1 squared is 1, so that's just negative 1 minus 1. And if you simplify, that gives you negative 2. So you see what they actually did. That's how they got that to look like this. So the big hint was the fact that you started seeing brackets and squared. It's like they factorized here clearly, but how did they factorize? How did they simplify this further? They did so by completing the square. Okay, so that is that question. And then we move on to the next question. The next question, 5.5.2 says, hence or otherwise find the maximum value of x. Okay, so after you have actually worked through this and gotten it to this point, you need to find the maximum value of f. Now, it looks scary because it's not our usual cos graph. However, you can look at it like this. Let's think about what the cos graph looks like. Okay, the cos graph looks like this, where it kind of just does something like that and then goes back up. So something like that, right? And naturally, the graph of cos x, let's speak about that graph, y equals cos x. That graph has a maximum. The highest point it can go to is what? Is 1, okay? And the lowest point, of course, is negative 1. So when we have this expression of f of x equal to, and we have all of this, all of the things that is going on here is really just what is being done to the cos graph. So just like you have a cos x plus 1, what that means is we take our original cos graph and we're going to shift it up by 1 unit, right? So that's really what is going on here. We have to look at it like that, because everything that we have going on here, the plus 1, the square, the minus 2, all of those, when applied to your cos graph, they will affect the y values of your cos graph. So I'm going to focus on specifically the maximum value. And the maximum value of y equals cos x is equal to 1. Now we're just going to go ahead and use the other things that's going on here, okay, to apply it into our cos graph and see what y value for our maximum we end up with. So this is the maximum. It was originally 1. Then what did they do to it? They took that cos graph and they moved it up by 1 unit. So it means that 1 of yours, because we're only focusing on the maximum right now. Our maximum used to be 1. We added 1 to it and it became 2. What else did they do? They took that cos x plus 1, which we've already dealt with. Our maximum is now 2. But then they took that and then they squared it. So we're going to take the number that we have now and square it, because all of these, they're affecting the y values of your graph. Okay, square that. It gives you 4. Then after they squared it, they subtracted 2. Then we're going to take that and subtract it by 2. And then that gives us 2. So it means that our new maximum is now going to be 2. Another way you could have seen this, or another way that I can think about explaining this is you could have focused on cos x, right? And ask yourself, where does the maximum happen if we just have y is equal to cos x? What is the x value belonging to the maximum? Okay, the x value, we know that the y value is 1. The x value belonging to the maximum is 0 degrees, right? What you could have done is, okay, I want to find out exactly what the maximum is. I know the maximum is not going to all of a sudden translate to something else. It's still going to be at 0 degrees, okay, because it's still the cos graph. It's just being shifted up and down. That's really what we're seeing over here. They did not affect the x, okay? Everything has an effect on the y. It's not a cos x minus, 20 degrees, for example. So we know where it still happens. So that x value is still the same, still happening at 0 degrees. So you could have just taken 0 degrees and substituted into this, and you would have found your maximum. So you could have said, oh, my maximum, since I know the original cos graph, its maximum occurs at 0 degrees. I could have just said, okay, let's just say cos of 0 degrees plus 1 all squared minus 2. And if you put that on your calculator, you will indeed get 2. And there you go. See, we get 2. So there, past exam papers are extremely important to work through because you're going to see questions that you would normally not see in a textbook. And the reason why is because they come up with new ways of asking questions. So past exam papers will really show you those new ways. Textbooks sometimes can be outdated. There are a lot of really amazing textbooks, like we've seen with the Kevin Smith textbook, we've seen with Answer series, we've seen with Mind Action series, even Platinum. There's so much helpful textbooks, but those textbooks help you to learn the content and they help you to practice. But past exam papers reflect what you're actually going to write in your exam. So it's very important to go through those. Okay, so that is it for question 5. And then we move on to question 6, which is on more trigonometry. Okay, so moving on to question 6. We are on question 6, and question 6 says, given the equation cos x minus 30 degrees plus 2 sine x is equal to 0, we need to show that the equation can be written as tan x is equal to negative root 3 over 5. Okay, so there's already a huge hint here. The fact that we have tan, but here we have cos and just sine, really just means that we need to make sure that we can somehow break this up so that we have things like cos x and sine x. Because you see, you have tan x here, not tan x minus 30 degrees. So we need to break that up. Okay, so this, let me just rewrite the equation that we have. And what we can do to break this one up, because we have 2 terms inside this bracket, we can just use the compound angle formula. So let's go ahead and expand this using the compound angle formula for cos. So that's going to be cos of our first angle, which is x, cos of the second angle, which is 30 degrees. And then because we have a minus, it changes to a plus. And then we have sine again of the first angle and sine of the second angle. Okay, then we have plus 2 sine x equals 0. And now let's see how we can simplify. Okay, so because we have things like cos 30 and sine 30, we can actually just use our special angles to simplify that. So with 30 degrees, it's not really an issue. You can actually just use your calculator. It'll be fine. So cos x, and then, so that gives us square root 3 over 2. So multiply by root 3 over 2. And then we have plus sine x multiplied by sine 30, which is a half. Okay, so multiply by a half. Then we have plus 2 sine x being equal to 0. Okay, because they are multiplying, you might as well put this as the coefficient. So we can just rewrite that as root 3 cos x over 2. Okay, so that's that root 3 over 2. And with this one, you can just say sine x times 1, which is just sine x over 2. So we're going to say sine x over 2. And then, of course, we have that over there. So we're really just trying to simplify these and then eventually form tan, okay, using that. So because they both have over 2 and we're adding here, we might as well just put them together. Actually, because we're just adding all through, let's just add all of these. So these ones are already over 2. To get this one to be over 2, you are going to have to multiply its numerator and the denominator by 2. The denominator here is a 1, okay, because it doesn't have a denominator, so it's automatically 1. And so when we are multiplying, because that is going to be over 2, and they will all be over 2, we can now rewrite it like this. It's the square root of 3 cos x plus sine x. And then when we multiply here, this is 2 times 2, which is 4. So plus 4 sine x. And remember, it is over 2 as well. So because they're all over 2 and we are adding, we can put them all under the same denominator. And this is equal to 0. Okay, so at this point, we have like terms here. Sine x plus 4 sine x are like terms, and they can become 5 sine x. So root 3 cos x plus 5 sine x over 2. Okay. I don't think we should put it together. And here's the reason why. Okay. The reason I'm saying so is because you see that here we just have a tan x. To form tan, right? Tan x, we form that by saying sine x over cos x. So because I need to actually take the sine x and divide it by the cos x, it's not really helpful to have this 2 here. So what we can do is just get rid of it by multiplying both sides by 2. That's fine. And then it's gone. So now that it's gone from here, we have root 3 cos x plus 5 sine x, and then that is equal to 0. Okay, so remember, to form tan, you need to say sine over cos. So what we can do is we're going to leave sine as the subject, and then we're going to have to take that cos over. So we have 5 sine x is equal to negative now root 3 cos x. And then we can go ahead and divide both sides by cos x. So first of all, I'm dividing by cos x just so that we can form tan. Okay, so divide both sides by cos x and cos x. But you do remember that here they had just tan x. There was no number in front here. So it means that once we have formed the tan x, we shouldn't have a number in front of it as well. So because this is the sine x over cos x, that's going to be your tan x. It means that this number 5 needs to also leave. So along with dividing both sides by cos x, we'll also divide both sides by 5 so that that 5 can leave the right-hand side. Okay, so now what we will have here is the 5's cancel. Sine x over cos x gives you tan x. And then this is equal to, you see that cos x and cos x cancels here. So you have negative root 3 over 5. And that's what happens. Okay, so that's actually how they did that. That's how they made this expression look like that. Okay, moving on to the next question. 6.2 says determine the solutions of the equation, and we have cos x minus 30 degrees plus sine 2x is equal to 0. Okay, so it's still the same equation they're referring to, but we just need to actually solve for x in these intervals. Okay, so let's go ahead and find that. It's really like general solution. Because we've already simplified this equation that we had here to this, we can just work on that. So we're really just trying to find, first of all, the general solution or this equation, and then we're going to go ahead and find those specific x values within this interval. Okay, so let's go ahead. We have tan x being equal to negative root 3 over 5. Okay, and at this point, I think I'm actually glad that this came in, and the reason I'm saying so is because, like I explained in this paper, right, in this particular video actually, because we worked on question 5 that had a tan x situation. It was tan 2x. Remember when I said that when the value, right, of tan x or tan whatever angle you have is negative, once you get your answer will be a negative angle. If you wanted to make it positive, remember I said you need to add 180 degrees, not 360 degrees. The video that I'm showing now, I said add 360. It's not 360 for tan. It's 360 only for sine and for cos. Okay, so let's go ahead and work on this. So what we're going to do is go ahead and find our reference angle. I am using the quick method here. You can go ahead and use the standard method, and you can refer back to that video to see how to use the standard method there. So we have our reference angle is equal to, and so to find the reference angle, we say shift tan of this that we have, negative, and this is a square root 3 over 5. Okay, so let's see. We get negative 19.11 degrees rounded off to 2 decimals. And I will round off to 2 decimals. It's not a problem because do you see that we're just trying to solve for x, not 2x or 3x or half x? Because we don't have to divide at the end. It's fine if you round off to 2 decimal places at this point. So this is our answer that we have for the reference angle. And then remember to solve for x with tan. It's very simple. All you just say is x is equal to whatever your reference angle is, then plus k, 180 degrees, where k is an element of integers. That's all. So to solve for x here, we just say x is equal to, our reference angle is negative 19.11 degrees plus k of 180 degrees, where k is an element of integers. Okay, so now we have to find those specific solutions. With the specific solutions, I like to use a number line just because it's neat and it's more ordered. It's easier to find your answers in a way that is already structured so that you don't miss anything. So the number line, the numbers that we're using here, remember that k is an element of integers. So we're only going to be using integer values and substituting it into this expression. So we can go ahead and start from 0. I always start from 0. If you substitute 0 into this, what do we get? You see that if we substitute 0, we get the same thing that we have already, okay? So I just said 180 and then that's k, okay? We get the same thing. So you're going to have to think about this now. Negative 19.11 degrees. Is that within the interval that we have? Well, yes, okay? From negative 180 to 180, so we can accept that answer. Then after trying 0 as an integer, I can go ahead and try negative 1. So I go from here, then to the left. So let's try negative 1. So if we substitute negative 1 into this, let's see what we get. We get negative 199.11. Do you see that that's just way too far? Okay, it's way too far, so I'm not even going to try using it. We can go ahead and say that negative 1 did not work. And that means you don't have to try negative 2 because it definitely will not work. Then we can go ahead and try 1 as an integer value. So if you substitute 1 there, you get 160.89. So that actually works out. You can go 160.89 degrees. That works. And it's already way too big. You know 2 will definitely not work. Okay, see, way beyond that. So we don't have to try that. So these will be our answers. We can go ahead and tell them. Therefore, x is equal to negative 19.11 degrees. Or x is equal to 160.89 degrees. If you had used the standard method with the diagram, you would still get the same answers because you have to move within intervals of 180 degrees. So you're just moving through like that. That's why we substitute integer values. The only difference is your answer would have been positive. So if we wanted to get that same answer, you could have just added 180 degrees to this and you'll see that it will be the exact same thing. Okay, lovely. We're done with that question and moving on to the next question. Okay, so we're on 6.3 and it says, in the diagram below, the graph of f of x is equal to negative 2 sine x is drawn for this interval where x is an element of negative 150 all the way to 210 degrees. Okay, the first question is write down the amplitude of f. Okay, so we're looking at the graph of f. And from the equation already, you can see the amplitude. Yes, we have a negative 2 over here. You just have to take the absolute value of whatever is here. So if it's negative 2, you're just going to take 2 because the amplitude is really just speaking about the height of the graph from the midline. So this would serve as the middle of the graph, right? The vertical middle. And so the height is 2 units. So we can go ahead and tell them that the amplitude is 2. Then the next question, 6.3.2 says, draw the graph of g of x is equal to cos x minus 30 degrees for the interval where x is an element of negative 150 to 210 degrees on the grid provided in the answer book clearly show all intercepts with the axes and the endpoints of the graph. Okay, so look at the graph we're drawing. It is g of x equals cos x minus 30 degrees. So do you see that the only thing that happened here, okay, from the original cos graph, cos x, is that we just have a minus 30. So we're subtracting from the x. When you subtract from the x, or when you affect the x, what you're really doing there is this is a shift. So it's a horizontal shift. It's either to the left or the right. If it is a minus, it's moving to the right. If it's a plus, it's moving to the left. Remember that this only works when we are subtracting or adding to the x. Okay, if it's on the outside, then it's a y, and plus would be up and minus would be down. Okay, so that's what we have to think about. So what we can do here is think about what the original function of cos looks like. And then based on that, we can actually draw what this cos graph would look like. So the normal cos graph, and I'll just draw a little diagram of it so that you can see what I'm working off of. The normal cos graph, right, looks like this. Okay. And it's really like a zigzag pattern, but it's just curved. So at 0 degrees, just remember that at 0 degrees, we would have 1, okay? And then at 90 degrees, so you'll notice there will be a difference, or there will be an important point every 90 degrees, okay? So after 0 degrees, 90 degrees later, your cos graph is going to have a y value of 0, so it's going to be on the x-axis. And then 90 degrees later from that, that is 180 degrees, your cos graph will have a value of -1. And then after that, 90 degrees later, at 270 degrees, you're going to have a y value of 0. And then 90 degrees later, at 360 degrees, you would have a value of 1. And that's why that cos graph ends up looking like that, okay? So what we're going to do is think about how it's going to look in our diagram since this graph has been shifted 30 degrees to the right. Okay, so everything that we had here is now going to move 30 degrees to the right. So in this one, the reason I'm going to just continue it is just so that you remember what it's going to look like, since we do have, you know, values beyond 0. We have negative values as well. So let me just go ahead and take this line and extend it. If we extend that line, trying to grab the line specifically. So if we extend that line, what's going to happen here is, you see the way this graph looks, it's going to take on the same form on that side as well. So it'll also do that, like that. Okay, and really just does the same thing. So from 0 degrees, 90 degrees later, at -90, it's going to be at 0. 90 degrees later, okay, it's at -180, it will be at -1, and so on. So how we can actually draw this graph down is based on that. Since we know that it's going to move 30 degrees to the right, every time we have a value, we're just going to keep moving that angle 30 degrees to the right. So this is what I mean by that. You see by -180, right? We should have had a y value of -1. Instead, this y value of -1 will not appear at -180. It will appear at -150 degrees, because the cos graph is being shifted 30 degrees to the right. So it should have been at -180, but because it moves 30 degrees to the right, it's going to now appear at -150. So that's where that y value of -1 will be. So that, and that's probably what they meant by the endpoints. So that, and then the next one, so we're done with the 180. The next one is that 90, -90, right? At -90, you see that you have a y value of 0. So what's going to happen here is, at -90, we're not going to have a y value of 0 anymore. This is going to happen 30 degrees later, okay? 30 degrees to the right. So that's going to be at -60 degrees, right? -60. Then here at 0 degrees, where we were supposed to have a y value of 1, it will not happen at 0 degrees anymore. It will happen at 30 degrees to the right of this, which is at 30. So now that's where you have 1. Okay, we're done with the 0. And then the 90 degrees was supposed to have a y value of 0. Instead, we are going to have this not happening at 90, but at 120. That's where you have your 0. And then at 180, you should have had a y value of -1. A y value of -1 will not happen at 180 anymore. It will happen 30 degrees later, which is at 210 degrees. Okay, so that's where you're going to have that. And then you're just going to draw your graph. So it's just a curve. So you're just going to connect them and make sure that it curves. Okay, so something like that. So that is our graph of G. We'll just label it G. And we know that this one is the graph of F. Okay, so there we have joined that graph. Okay, so the reason I did this and I didn't go ahead and just draw the cos graph and then move it to the right is because in an exam setting, that is not really what you would be able to do. So I just decided to explain it in a similar way that it would have been done if you were working on it in an exam. Okay, so that is that. We're done with that question and moving on to the next question. The next question, 6.3.3 says, use the graphs to determine the values of x in the interval where x is an element of -150 to 210 degrees. So it's still the same graph in that same interval for which g of x is greater than f of x. Okay, remember that these are referring to the y values. Okay, when you're looking at two graphs and you're concentrating on their y values appear on the y-axis. So if you have a graph like this and you have another graph like that, and we are looking at the y values of this graph, just remember it is for that same x value. Okay, so let's say this graph's name was f and this, well, let's just call it g, and this was f. Then if I'm asking for places where g of x is greater than f of x, I'm really just asking for places where the graph of g has a higher y value than the graph of f. So in a nutshell, what you're going to be looking for is the places where the graph of g lies above the graph of f. So that's the whole point behind that. So that's what we're going to do. Look for places where g is higher than f. Okay, so let's go ahead and see. So we have g and we have f. We need to look for places where g is higher than f. So as you can see, all through here, it's not working because g is below f. But then something happens at this point. They first intersect, right? And remember that when they intersect, they are exactly equal to each other. Then the graph of g is now higher than the graph of f. So this is where it's greater. And then they intersect again, and then the graph of g goes below the graph of f. So this is really what we're trying to focus on, this area over here. We're trying to find out what exactly are the x values for the graph over here. Okay, so let's find that. Do you see that two very important points here would be their points of intersection? Because if we knew exactly what number this was, and we knew exactly what number that was, we'd be able to see that the graph of g is greater than the graph of f for places that are greater than whatever that number is, but less than whatever this number is. All through this, all through these numbers here, that's where the graph of g lies above the graph of f. So we're going to have to find their points of intersection. In other words, what we're trying to find out is where is g of x equal to f of x. Okay, so let's look at what those two graphs look like. We know f of x is -2 sine x and g of x is that. Okay, so we're trying to see where is g of x equal to f of x. That is cos x minus 30 degrees. Where is it equal to -2 sine x? And now I see that this looks familiar. This is the first question. Okay, so they're continuing this. Do you remember that here in this question, we actually dealt with this already? We dealt with it here. They started off this question by giving us this equation. Do you recognize this now? They gave us this equation and they said that we had to basically simplify it, show them that it can be written like this. Now, the reason I'm saying it's the exact same thing is because do you remember that g of x is this cos x minus 30? But we have a plus here. We have a plus 2 sine x. If you take that over, what does it become? It becomes -2 sine x. So really, this is the equation that we just solved for already. We solved for x for where cos x minus 30 degrees was equal to -2 sine x. And we already know the solution to that. The solution to this is these two, okay, between this interval that they gave us. But if we think about that, look at those solutions that we have: negative 19.11 degrees and 160.89 degrees. Does that work for our interval? Is that actually solutions we can accept for our interval? Well, yes, because do you see, look at the interval that we have: negative 150 all the way to 210. That is within that interval. See, that is like greater than negative 150. And this is also within that interval. You can find these numbers in here. So that means we can accept these. These are the points of intersection of those two graphs. So now we don't have to guess anymore. We know exactly what those values are. So we're going to put that there. That's negative 19.11 degrees. And this one over here is that 160.89 degrees. Okay, so in a nutshell, the places or the values of x for which g of x will lie above the graph of f or be greater than the graph of f is where x is greater than all the values that are greater than negative 19.11 degrees, but smaller than 160.89 degrees, because you see it's all the values in between negative 19.11 and 160.89. So that would be our answer over there. Okay, so that is the answer to that question. And then we move on to the next question. Then the next question B, we need to solve for x, or really find the values of x within that interval for which f prime of 1 over 2x is equal to 0. Okay, so this is only for 1 mark. So it means it's a simple question. Let's understand what f prime means. If the question was f prime of x is equal to 0, you had to give them the values of x for which f prime of x is equal to 0. Let's think about what that would mean. So the graph of f is that sine graph, right? The black graph over there. Where f prime of x is equal to 0, f prime, you use f prime when you're trying to find the gradient of a curve. When you're trying to find the gradient. So it means this is where the gradient is equal to 0. You're going to have to think about that. In a curve, where's your gradient equal to 0? That happens at your turning points. The idea behind that is that a curve, right? It's made up of points that are increasing and points that are decreasing. But at the turning point, this is the point where it neither increases or decreases. It just stands still. That's why we call it a stationary point. Okay, so at this point, this is where our gradient is equal to 0. At these points, our gradient will be positive because do you see that this is increasing? You always read graphs from the left going to the right. Okay, here it's positive, here it's negative, and here it's equal to 0. So that's what we're looking for. We're looking for where the places where the graph has a gradient of 0, right? So if this was the question, our answer would be very simple to be, okay, we're trying to look for places where it curves, and you'd have to look for the turning points of this graph. Just like a parabola, the turning point happens at that point that we're turning, right? Here and here. Now, they're not just random places we're picking. We know the point that it starts to turn. Because it's a sine graph, it's really just that maximum and the minimum point. The maximum of a sine graph, because this graph hasn't been shifted to the left or the right, that maximum happens at negative 90 degrees. So that's how we know that is negative 90 degrees. And this one we know is 90 degrees. Okay, that's where the minimum happens. So that's the maximum and that's the minimum turning points, really. Okay, so we would know this answer. If the question was this, our answer would be very simple. It's x is equal to negative 90 degrees or x is equal to 90 degrees. Very simple. But the question here is a little different. It says f prime of 1 over 2x. So we're going to have to understand what exactly it means to put a coefficient in front of x. What does that mean? Well, this is a concept that you guys have already worked on in trigonometry, specifically in trig graphs. You see that if you have a graph y equals sine x, the minute you put a number in front of x, what does it do to the graph? It changes the period of the graph. So like a sine graph, right? It usually takes 360 degrees to complete one cycle. But the minute you put a 2 here, right, what is going to happen is that it makes your graph more narrower. So instead of it completing a cycle in 360 degrees, it would complete it in half the amount of degrees, really. It's going to complete the cycle in 180 degrees. Now, I know I just said that, but I want to show you how you would calculate that. How would you find out how fast is it going to complete a cycle? You find out by taking the old period and you divide it by that coefficient of x. So in this situation, the reason I know it completes the cycle in 180 degrees is because the old period of a sine graph is 360 degrees, but we know that the coefficient is 2. So that's why we know that the new period would be 180 degrees, and that's what makes the graph more narrow. Okay, so now that you understand the idea behind that, what happens when we put a half here? What's going to happen there? Okay, so we know that the normal sine graph completes a cycle in 360 degrees. What's going to happen with this one? Well, you can say 360 degrees divided by a half. What does that give you? Gives you 720 degrees. So this is going to take much longer to complete a cycle. Instead of it completing it in 360 degrees, it's going to take double that amount of degrees to actually complete. So what's going to happen is that this graph is actually going to get much wider, like that. And the thing about it is, just like what happened with the period, you see that what happened with the period is that the period ended up doubling, right? So if the period doubles, so does every other x value that you had. The normal sine graph, and I think I should just put 2 of them here. I should really just copy this and then put it here again. So here is the one that completes in 720. Right? So when we're looking at the normal sine graph, you know that I'm going to focus on the important points that we are referring to here. You knew that if you were just looking for f prime of x, like I showed you here, you knew that this was going to happen at negative 90 and positive 90, of course, right? So I'm saying that here we have a maximum turning point at 90 degrees. Well, if the period of this graph has been changed, because that's what happened to f prime 1 over 2x, they put a 1 over 2 in front of the x. What's going to happen now to that maximum? Where will it appear? It would appear in double of 90 degrees, because that's really what these angles are doing. The solutions that you used to have for this graph are going to happen in double the size of whatever angle they're at. So that maximum will not happen at 90 degrees anymore. It will happen at 180 degrees. Okay, so we know that now. So with our graph, when we're looking at the graph, because the maximum and the minimum used to be here and here, where are they going to be now? This one that was at negative 90 will happen at negative 180 degrees. And this one that was at 90 is going to happen at 180 degrees, positive 180. So our solution for that, where is f prime of 1 over 2x equal to 0, right? Where is the gradient of this graph that has been altered equal to 0? It's going to happen where x is equal to negative 180 degrees, or where x is equal to positive 180 degrees. Okay, I hope you guys understood that. Please do comment in the comment section if you still have questions on it. Okay, so that is it for question 6. That's not the end of this video though, because we still have 2 and 3D trigonometry in question 7. So moving on to question 7. We are on the last question for the trigonometry part of this paper, and that's question 7. Question 7 says, in the diagram below, P, Q, and T are 3 points on the same horizontal plane. So that's P, Q, and T. Okay, so they are on the ground. You can actually look at it like that. That's the floor of this diagram. Then they tell us that an MT is a vertical mast. So we have that over there, which is just a vertical line that we have. And then MP and MQ, MP and MQ. So these two, right? That those are 2 straight stay wires. And then the angle of elevation of M from Q is theta, so the angle of elevation of M, okay, from Q, so that angle that they're measuring over there. Lastly, PQ is equal to K meters, and PM is equal to 2 times PQ. Okay, so that's simple. If PQ is K and PM is 2PQ, so it's 2 times the size of PQ, meaning this is 2K. Okay, so we just put that down already so we know. And then they tell us that the area of triangle MPQ is this. So MPQ, this triangle over here. So this front part, the flat side here. So we have the area of that. Okay, first question. 7.1 says, show that MPQ is equal to 2 theta. So we need to find the angle MPQ, this angle over here. Okay, they just told us something about this triangle, okay, that this angle belongs to. This triangle MPQ, we have the area of it. So we can probably use that. Since we already have the area of this triangle, let's just see how they would have calculated the area of it. Well, as you can see, there is no perpendicular height here, so we can't really use that area half times the base times the perpendicular height. We can't really use this. So we can use the other area that we know. So I'm focusing on this triangle, right? So we're saying the area of triangle, so area of triangle MPQ, that's also what they called it, that to calculate this, the formula we would use is say a half. So I'm saying a half multiplied by the side next to the angle that is our focus angle. So a half times PQ, which we can see is K, right? Multiplied by PM, which we can see is 2K. And then we're going to say, so multiply by 2K. And then you're going to say sine of that center angle. So sine of angle MPQ, because we don't really have it right now. So sine angle MPQ. So this is the area formula. Okay, area of a triangle if you don't have a perpendicular height. But the good thing is that we have the area already. They told us the area is this. So I'm going to put that down. 2K squared sine theta cos theta. That's 2K squared sine theta cos theta. And then we still have this, but we can just simplify a bit. So you see that we have a half times, we have a 2 there, right? And then multiplying all through. If you say a half times 2, what happens is you have a 2 over 1 here, and your 2's will cancel diagonally. So they really just give you 1. Okay, so you can really say those cancel, they become 1, and they multiply in here, and they just really leave that the same. So we have K times K, which gives us K squared. And then we also have still our sine of angle MPQ. Okay, so this is what we have, and we're trying to find this angle. Because we're trying to find this angle, we just have to make this the subject first of all. So if we can make that the subject of the equation, we can then go into finding that. So to make that the subject of the equation, we have to get rid of the K squared because it's the only thing in the way right now. So we'll divide both sides by K squared since K squared is multiplying to sine angle MPQ. And let's go ahead and tell them that sine angle MPQ is equal to, and we're going to rewrite what we have here. But do you see that they're going to simplify? Since you have a K squared and a K squared, they cancel. And all we'll be left with is 2 sine theta cos theta. Okay, the goal is to still get angle MPQ. Now, the thing is, because this is sine of an angle, you can take sine over. And when you take sine over, it becomes the inverse of the sine function, okay, which we see as shift sine. And what shift sine does is that it will cancel out a sine. But then what are we going to do with the cos? And it doesn't really look right to do that because we have to say shift sine of this whole thing here. So when you look at that and look at the answer for MPQ, it doesn't include any cos or anything like that. So because it doesn't include that, clearly this cos has to go. Okay, so how can we actually get that cos to leave? Okay, do you see now that this is actually an expansion of one of the double angle formulas? The double angle formula that says sine 2a, if you expand it, it gives you 2 sine a cos a. So do you see that this would simplify to sine 2 theta? Okay, just like with that. So because it simplifies to sine 2 theta, we still have this over here, sine mpq. And now we can go ahead and take sine over. So when sine goes over, what actually happens, or you're going to really just see it as what we're doing on both sides is we are using the inverse of sine on both sides, okay? But I like to take things over. So what happens there is you're going to have the inverse of sine with the sine function. And because they're the inverse of each other, they would actually cancel each other out. And therefore, MPQ, that angle, is equal to just 2 theta. And that's how we get that. Okay, so that is the first question. That was 3 marks. Moving on to the next question. The next question, 7.2, says, hence, show that MQ is equal to K 1 plus 8 sine squared theta. Okay, so we're really just trying to solve for MQ and ensure that it looks like that. So let's actually fill in our diagram. Since we already found out that this is 2 theta, let's fill that in over there. So we know now this one over here is 2 theta. This is what we have so long, and we need to find MQ. So if you're trying to find MQ, what rule can we actually use to find this? So I can't really use this triangle over here because there's not much information. All you have is theta inside there. So we're not even going to bother trying to use that triangle. How about we use this triangle? But do you see which trigonometric formula you can actually use here? The trig formula you can use here, because we do not have MQ, is the cos formula, the cos rule. Okay, so because this is the side we're looking for, right, that we're going to say MQ squared is equal to, and then we're going to say the side next to it squared, that's PQ squared, plus the other side next to it, which is PM squared, then minus 2 multiplied by the PQ multiplied by the MP or PM, as I called it there. And then you're going to say cos of that center angle, which is that MPQ. Okay, but the main focus is really just getting these letters and these variables. So MQ is what we're looking for. We actually don't have that one, so we'll leave that as MQ. But as for PQ we have is K. That is K. So that's going to be K squared plus, and then PM. PM is 2K, so that's 2K that gets squared. And then minus 2 multiplied by the PQ. We know that that is K. Multiplied by the PM, we know that is 2K, and then cos of that center angle, which is 2 theta. Okay, and I'm just going to go ahead and write this down. So there this is, and all we're trying to do is solve for MQ. Okay, so to solve for MQ, we're going to go ahead and say MQ squared is equal to, and we have K squared, and then that's going to become, the 2 squared gives you positive 4, and then we have K squared. Then when we multiply through here, you see that you have a negative 2, and then along the line you also have a positive 2, so they multiply and give you negative 4. Then K times K is K squared, and then cos of 2 theta. Okay, so at this point, we're still looking for MQ, right? Because this is squared, we can go ahead and try to solve for MQ by getting rid of the squared. So you do that by square rooting, but this is an equation, so you have to square root both sides. Okay, so this means that MQ is equal to, and let's just say square root and simplify what is under the radical. So K squared plus 4K squared gives you 5K squared, and then you still have the minus 4K squared cos 2 theta. So remember what this looked like. That's a sine. So we're just going to have to simplify as far as possible. So with this MQ equals, well, do you see that under the radical you have 2 terms? This is the first term and the second term. And do you notice that in these 2 terms, we have K squared that is common. So we can actually take K squared out as a common factor. and then open a bracket, what is left in the first term when you take k squared out? It's like, say, this divided by the k squared, and that gives you 5. And then this divided by the k squared cancels, and only negative 4 cos 2 theta would be left. Okay, the good thing about this is, you see you have a k squared and then you have brackets protecting what is inside here. Because of that, the k squared can actually get square rooted. The idea behind this is, if you had, for example, let's say the square root of 4 multiplied by 2, because they're multiplying, you can actually split them up like this. This is actually the square root of 4 multiplied by the square root of 2. And the square root of 4 can get simplified to 2. And the square root of 2 can't, so it will stay square root 2. Okay, so that's the idea behind that. So that's what happens there. It gets square rooted, and we're going to have mq being equal to k. And this does not get square rooted. Unfortunately, it can't, because you have a minus here. You cannot square root through a minus sign. So that stays. And then we have 5 minus 4 cos 2 theta. So where does this sign come from? Where does that come from? Well, they probably changed this 2 cos theta to one of the double angles expansion for cos 2 theta, but one that only has sine. Let's think about the one that only has sine. That would be, okay, the cos 2a, that would be the one that says 1 minus 2 sine squared a. That would be that one. That's the only one that only has sine and no cos included. So it means we're going to change it to that. So we're actually just saying that to solve for mq, we say mq equals, and we'll say k square root of 5 minus 4, and we're going to change this. So remember, it changes to something that has 2 terms. So you need to protect it with brackets. So that changes to 1 minus 2 sine squared of theta. Okay, so that is what we have there. Then we're going to simplify further. So mq equals k square root of 5, and then we distribute. So that's going to give you negative 4, and then that's going to give you positive. And then you see it's negative 4 multiplied by negative 2, which gives you positive 8 sine squared theta. And as you can see, we're basically done at this point. mq is equal to k square root. And over here, because these have now been separated into terms, 5 minus 4 is 1 plus 8 sine squared theta. And that is exactly what they did. So always make sure you look at their solution, their answer, and just see how can you actually get yours to look like theirs. Okay, so that is what we have there. That's the second question in question 7. And then we move on to the last question in question 7. So the next question says, if k equals 139.5 meters and theta is equal to 42 degrees, determine the length of mt correct to the nearest meter. Okay, so no decimals, so just correct to the nearest meter. Let's go ahead and see how we can actually find mt. Remember, always use what you previously got. So we're going to have to fill that in. We have mq now in our diagram. So I have all of these things that we've already filled in and mq. mq is that number that they gave us. So that k square root 1 plus 8 sine squared theta. So that's what we have there. Now, how can we actually use this to find mt? Well, you see that we have a right angle triangle here. See, we have a right angle triangle. So you can use trig functions on it like sine, cos, and tan, okay? So with this, we have a reference angle theta. And let's just see how we can actually use this to find mt. Always focus on this when you're trying to work with trig functions, okay? When you have a right angle triangle, you ask yourself, what do I have and what do they ask me to find? What we have is this. We have mq, which is our hypotenuse. So we have h. What they asked us to find is mt. So you're going to have to look at that in reference to the angle that we have present here. They asked us to find mt, which is clearly the opposite side. So you see that you're working with the opposite side and the hypotenuse. So which function are you going to use? You're going to use sine. So we're going to use sine and go ahead and tell them that sine of our reference angle was theta is equal to the opposite side, which you saw was mt, over the hypotenuse, which is this whole thing, this mq, but I'll just write the expression that we have there. So that is mt over mq, which is that k square root 1 plus 8 sine squared theta. So all we have to do here is make mt the subject and then substitute these values. Okay, to make mt the subject, we can just cross multiply. So here the denominator we have is 1. 1 times mt stays mt, and then sine theta times all of that. I'll just leave the k in front. So it's k sine theta square root 1 plus 8 sine squared theta. So that's what happens because this is under the square root. It can't multiply with that one. Okay, so this is what we have, and we're just going to substitute. So finally, let me just put it like this. mt is equal to, we know what k is now. K is 139.5 meters. And we have sine theta is 42 degrees. And then we have square root of 1 plus 8 sine squared of 42 degrees. And you're just going to substitute that into your calculator and find out what exactly mt is, rounded off to the nearest meter. Okay, so just remember on your calculator, when you're putting that sine squared, you can't go sine and then squared. It's not going to work. You have to say sine 42 squared. So the answer that we get there, right, the number that we get is that 199.80. But they said round off to the nearest meter, meaning to the nearest whole number. Okay, so this is going to be approximately 200 meters. And that is the length of mt. Okay, so that is it for the trigonometry section of this paper, and I will see you guys in Euclidean geometry. All the best for prelims and keep practicing, guys. I'll see you guys in the next video. We are now on question 5, and 5.1 says, given sine beta is equal to 1 over 3, where beta is an element of 90 degrees to 270 degrees. Without using a calculator, determine each of the following. Okay, so this one is a little different to what they have been doing really. Remember, the types of trig diagrams they usually give us, well, that they have been giving us, is things like sine of maybe 27 degrees is equal to P, right? And then we'd have to construct that. And so these are really just trig diagrams that will always be in the first quadrant because 27 degrees is just measured like that. So this time they are actually just going back to the normal grade 11 types that we'll deal with. These ones are also in grade 12, of course, but we usually see them in grade 11. So let's go ahead and construct this diagram. So we have 4 quadrants as usual. And what they tell us is, first of all, sine beta is 1 over 3. Now notice that this is a positive 1 over 3. So what they're really trying to tell you is that sine is positive. So let us mark the quadrants in which sine is positive. When you have your cast diagram, which quadrants do we have sine being positive? That would be in the first quadrant, which is for all. Okay, all your functions are positive here. And in the second quadrant, where sine is positive. Okay, so that's what that tells us. But then they tell us where beta is an element of 90 degrees to 270 degrees. So you need to know how the angles as well go. So remember, we measure angles anti-clockwise. So it starts at 0 degrees, then 90 degrees, 180 degrees, 270 degrees, and then back at 360 degrees. So when we're marking the quadrants that are within this interval, we're going from 90 degrees to 270 degrees. So how that works is from 90 degrees, you see the quadrants we pass. We pass the second quadrant, and then we pass the third quadrant, and there's 270 degrees. It stops there. So only these that we take. So which quadrant would this diagram lie in? It would be in the second quadrant because, as you can see, it has the most ticks. We're going to go ahead and choose that quadrant. So in other words, you could actually see that as they're asking you to find the quadrant where sine is positive but this quadrant must lie between 90 to 270. Okay, so that's what we have over there. So we'll draw our terminal arm or our radius, and we have that down, and then draw a line down perpendicular to the x-axis. And now we can start interpreting this like this. So you see that you have sine beta is equal to 1 over 3. Well, SOHCAHTOA tells us that sine says opposite over hypotenuse. So it means this is your opposite, and that is your hypotenuse. Our opposite side is 1. So here's is our beta. We'll measure it from the x-axis going to that line. Okay, remember the reductions are meant to reduce these angles, these obtuse and reflex angles, really. Okay, so that is our beta, and we are saying the opposite is 1 and the hypotenuse is 3. So clearly the only thing we need to find is the adjacent side. So we can call this side, because you see it is on the x-axis, it is an x value, so we'll call it x. We can call this our radius, and this is a y value. That's why it's here. See, it's that y value of 1. So that is a y value. So let's go ahead and use Pythagoras to find exactly what x is. So using Pythagoras, you see that we're looking for x. So we're going to say x squared is equal to, and we're going to go ahead and start with r because it's Pythagoras, the longest side squared, which is 3. So 3 squared minus 1 squared. Okay, and then we can solve. So in order to solve, well, let's just go ahead and simplify this further. That's fine. We can do that. So this will become 9, and that's still 1. 9 minus 1 is 8. Then you have to square root both sides to solve for x. When you square root both sides in an equation, you have to include the plus and minus sign, because the positive and negative value will be a solution to this equation. So therefore, x is finally equal to, and if you square root this, please also just note which side it's on, okay? Do you see that this is on the negative part of your x-axis? So that becomes negative square root of 8. But if you simplify the square root of 8, you have to think about the fact that, well, you could use a calculator, but you have to think about the fact that there's a perfect square in 8. Okay, 4 times 2 gives you 8. So the 4 gets square rooted, it becomes 2, so it's outside the root, and then you have square root 2. So the answer here is actually negative 2 square root 2. That is our x value, negative 2 root 2 simplified. Now we can go ahead and answer these questions. So 5.1.1 says find cos of beta. So remember, SOHCAHTOA, cos is the car part, okay, adjacent over hypotenuse. So cos of beta will take the adjacent side, which is the x, it's next to that angle. So negative 2 root 2 over our hypotenuse, which is a 3. And there we go. And then 5.1.2 says sine of 2 beta. We can do that one here. So 5.1.2, since it's sine 2 beta would indicate that we are using double angles here. So the only expansion for sine 2 beta would be the expansion 2 sine of beta cos beta. And then we can go ahead and substitute with sine beta and cos beta are. So we have 2 multiplied by sine beta. Now, do you see that initially they already told us what sine beta was? They said sine beta is equal to 1 over 3. So you don't have to look for it in the diagram. We already have it. 1 over 3 multiplied by cos beta. Cos beta, we just found cos beta to be negative 2 square root 2 over 3. So negative 2 root 2 over 3. And then now we just have to simplify this. Okay, so you see this 2, you can actually rewrite that as a fraction. So its denominator is 1. Let's multiply all the numerators. So 2 times 1 is 2. And then at 2 times negative 2 root 2 is negative 4 root 2. That's what we have there. So negative 4 root 2, and then over 1 times 3 is 3 times 3 is 9. And that would be our answer for that question. Negative 4 square root 2 over 9. And then lastly, 5.1.3. 5.1.3, we have, so cos of, these are looking a lot like grade 11 types of questions here. So 450 minus beta. Do you see that this angle 450 degrees do you see that it is bigger than 360 degrees? Okay, in your Cartesian plane, the angles end at 360 degrees. So the rule is, if you have an angle greater than 360 degrees, what you must do is subtract 360 degrees from it. And so when you do that, what we will get is cos, and 450 minus 360 is 90 degrees. So that's 90 degrees minus beta. And now do you see that you have a cofunction? And the cofunction of this is going to be equal to, so we will get sine of beta, okay? Cos 90 minus beta is sine beta. And we already know what sine beta is from the beginning. They told us it was 1 over 3. So this is just equal to 1 over 3. And that is our answer over there. Okay, so we are now done with the trig diagram. Moving on to the next question. We are now on 5.2, and 5.2 says, given cos to the 4th power x plus sine squared x times cos squared x over 1 plus sine x, we have to prove that this same thing, right? That same expression is equal to 1 minus sine x. Okay, so this is just an identity. So when you're looking at this identity, which hand side can we work with? The left-hand side or the right-hand side? The left-hand side, because the right-hand side is not much you can actually do there. So we're going to go ahead and take the left-hand side, say is equal to, and rewrite the left-hand side first. So this is our left-hand side, and we say is equal to, and now what can we do to actually simplify it? Okay, so let's actually look at this side, right? And see what they simplified it to. Do you notice that there is no cos in what it was simplified to? There's only sine. So we already know the causes need to go. Okay, now looking at our numerator, we have two terms. So there's a plus sign, so that's the first term, and that's the second term that we have there. What do you notice about these two terms? Do you see that cos squared x is common in both terms? We have a cos squared x here and a cos squared x here as well. So we can take cos squared x out as a common factor, and then we'll be left with, in the first term, you say cos to the power of 4x divided by cos squared x gives you cos squared x. That's what's left there. We're done with the first term. Now looking at the second term, what do we have left? If you take this and divide it by cos squared x, you are left with only sine squared x. Remember the plus, so plus sine squared x. And you can already see that is the identity for 1. So we have over 1 plus sine x, and this is equal to, so that just becomes a 1. So it's cos squared x times 1, which stays the same, all over 1 plus sine x. Again, do you see that we don't have any cos in our final answer, but we still have a cos here? So this needs to change. Let's go ahead and change it to cos's identity. So cos squared x times 1 is still cos squared x, and this is equal to, it's equal to, we're going to change it to 1 minus sine squared x. That is the identity for cos squared x, since sine squared x plus cos squared x is equal to 1. So if you make cos squared x the subject so that you can substitute it in place of cos squared x, you have the 1 here and you take the sine squared x over. So that is why that is the identity. Okay, so we have that, and then it's all over 1 plus sine x. So we still need to get this to look like that right-hand side. What can we do here? Well, do you see now that on the denominator you have a 1 plus sine x, but the final answer is a 1 minus sine x. So it means that they factorize this numerator. Because you have a 1, which is a square number, and a sine squared x, which is also a square value, what we can do is factorize using difference of two squares. So we'll open up two brackets, and we'll say in the square root of 1 is 1. So that means we're going to have 1 and 1. That's what gave us the 1. And then sine squared x, the square root of sine squared x is sine x. So we have sine x, and then we're just going to put a plus and minus, and that is factorized. And this goes all over our denominator of 1 plus sine x. And now Do you see that on the numerator and the denominator? Those two cancel because we're multiplying all through. And our final answer is 1 minus sine x. And this is therefore equal to our right-hand side. Okay, that is proven. Moving on to the next question. 5.2.2 says, for what values of x in the interval where x is an element of 0 degrees to 360 is this same expression going to be undefined? Remember, for an expression to be undefined, if the denominator is equal to 0, then it's going to be undefined. So do you see that our denominator here is the 1 plus sine x? That was the denominator throughout. So we have, if 1 plus sine x, if we make that denominator equal to 0, then this is going to make this expression undefined. So this is what we need to solve for. 1 plus sine x equal to 0. Okay, this one is quite simple because it's linear. We don't have to factorize anything. We can just take the 1 over, and now we have sine x being equal to negative 1. We don't even need to use the general solution for this because this can be solved with a graph. Also look at the interval they asked us to find this within, where x is an element of 0 to 360. So you can actually look at this as a graph. I don't really see a need for using general solutions for this. So when we're looking at this, what we can do is this. We have a sine graph. They're saying sine of x is equal to negative 1. Your sine graph looks like this. So we have our sine graph. And where is our sine graph? Where does it have a y value of negative 1? Well, it has that at its minimum turning point over there. Okay, so that is where we have negative 1. But what is the x value that belongs to this? This is quite an easy point because you can just follow the way this goes, the trend of the original sine graph. It starts at 0 degrees, right? At 0, it's 0. At 90 degrees, it is 1. And then at 180 degrees, it has a y value of 0. Then here at 270 degrees, it has a y value of negative 1. And then, of course, at 360, it will have a value of 0. Okay, they move in intervals of 90. So you could have just used the graph to actually solve for this. So that's what we can just do. I can see clearly here that x is equal to 270 degrees. Okay, so that is the answer here. X is equal to 270 degrees. It's unnecessary to use the general solution method just because this is only going from 0 to 360. And we know that we have here at this minimum turning point, the y value is negative 1. And this will not repeat again in this interval. So it's unnecessary to use the general solution method. So I will stop here. And this is our answer. Okay, x is equal to 270 degrees. That would make this expression undefined. Okay, moving on to the next question. Okay, 5.2.3 says, write down the minimum value of the function defined by this. So do you see it's the same function? Okay, same thing. They just said y equals. So you need to find the minimum value. I think I've kind of already somewhat explained this minimum value. You see, I call this the minimum turning point. That would be the minimum value of this function right now, right? This one that we have there. But let's just look at this one. Do you see that this is the same expression they gave us initially? And we were able to prove to them that this expression was equal to 1 minus sine x. So we don't have to go start simplifying this and thinking how are we going to solve this and find that minimum value. We already simplified it. So in place of this, we can actually just say this actually means that y is simply equal to what it was simplified to, 1 minus sine x. 1 minus sine x. And now we have to find the minimum value of this function. Okay. I think I'm just going to use the graph to do this, to explain this, because I don't see any other reason to just go a long method. So now we have to be careful with the way this graph looks. It says 1 minus sine x. So note, the sine x is negative, meaning your sine graph is not going to look like this anymore. It's going to go the other way around. So instead of it going up and then down, it's going to go down and then up like that. Okay, so it is reflected in the x-axis. That's what happens when you put a negative in front of a function. Okay, so that's what it looks like now. And then you still have the 1. please note the 1 is positive. It's a positive 1. So it means you have this negative sine x graph and then a positive 1, meaning the graph shifts up by 1 unit because it's positive, right? That 1 is positive. So let's just look at what exactly the minimum was before. Here, when we just use the negative sine x, your minimum value would have been here. That was the minimum turning point of minimum value. That would have been negative 1 still. The maximum is still at 1. But then because of this positive 1 that we still have, this graph is going to shift up by 1 unit. So it moves up by 1 unit. So it goes, the minimum value used to be negative 1, but it moves up by 1 unit and it's now sitting on 0. So now your minimum value is 0 and your maximum value would be 2. So that's what happens there. So you can actually just say the minimum value would be, and the calculation is, when it was negative sine of x, it was initially negative 1, but because it shifted up by 1 unit because of this positive 1, okay, the minimum value is now 0. And that is our answer. Our minimum value is 0. Okay, so that is it for this particular function. And then we move on to 5.3. 5.3 says, given cos A minus B is equal to cos A cos B plus sine A sine B. 5.3.1 says, you need to use the identity above to deduce that sine A minus B is equal to sine A cos B minus cos A sine B. This question has shown up before. This is really a proof, okay? But they're not really asking you to prove the entire compound angle formula, just the ending parts of it. So you need to use the fact that you know if you have cos of, and I'm going to rewrite it just so that we can get the idea behind this, cos of an angle, and I'm going to refer to this angle as a first angle. Say cos of first angle, and then you have minus a second angle, that this should be equal to cos of the first angle times cos of the second angle. Then that sign would change to a plus. Okay, so if you have a minus here, it should change to a plus. Sine of the first angle, which was A, times sine of the second angle. And you'll understand why I am referring to it as first and second angle here, because they're really saying use the idea behind this, how this was expanded to now create an expansion for sine of A minus B. So let's go ahead and do that. So ultimately we need to expand sine of A minus B, but not just by saying, okay, it's equal to this. No, we're going to show them how it is equal to that using this idea. Okay, so we know that this is what we need to be working with, sine A minus B. So let me actually just leave all of this in blue so that we can actually just focus on this being our main goal. Okay, so we're trying to make this what we have right now, right? This to look like this. Do you see the first thing that we need to actually do is we have a problem here. This is sine A minus B. It's not cos A minus B. It's not cos of a first angle minus a second angle. It's sine right now. So our sine, first of all, needs to change to a cos for us to use this idea on this. So let's go ahead. How can we change sine to cos? Well, we can do that using cofunctions. So let's think about what our cofunction should be. We want to change a sine of an angle to cos. Sine of any angle, right? If you want to change that to cos, it will become cos of 90 degrees minus that angle. That's what we're going to do here. So we're changing the sine of A minus B. We're treating this as our angle, sort of like our theta. And we're going to change it to cos 90 minus that angle. So this is going to be equal to, we'll say this is cos of, and we're going to have 90 degrees minus our angle, our theta. But remember that the theta what we are referring to is this angle. So 90 minus A minus B. Okay, so good. We have changed this to cos. We just kind of need to create this idea using this. Okay, so we've changed it to cos. That's good. But are we done? Let's look at what this one says. It says cos of a first angle, then minus a second angle. Right now, what we have is cos, then 90 degrees minus a minus b. Okay, it is a first angle and a second angle, but the problem is your second angle has a and b in it, which is not very helpful. So what we can do there is distribute. Let's go ahead and distribute that negative into the a and the b, the negative b. So we will have cos of, and we have 90 degrees, and that becomes a minus a, and then when it multiplies, it becomes a plus b. Okay, now the idea should still be cos of a first angle, then minus a second angle. But right now we just have three angles just there like that. But what we can do to create those two angles is we can group 90 degrees and a together. Now that is one single angle, and that works perfectly because 90 degrees minus a, you know that this can become a trig expression that is going to be, well, is going to have the angle a. Okay, for example, we see like we have cos of 90 minus a. When you're expanding that, that's going to be cos 90 minus a, and then of course you're going to have your other things, but it's still cos 90 minus a. And you know that you can simplify this to sine a. So it's still going to be simplified to a single angle that just has a. Okay, so that's why we're grouping 90 and a together. Okay, so we're still always going to compare what we have with this because we need to use this idea on this. So in here, we have cos. Lovely. We also have cos. Then we have a first angle. We also have a first angle. And then we have a minus. And you see the issue here is we don't have a minus, we have a plus. We need to change that to a minus. So how can we actually do that here? Well, here we can say cos, and we have our first angle, which is now 90 degrees minus a. And we will change this plus into a minus and then bracket minus b because it's still positive b. You just removed a minus from it and then you're left with a negative b. If you distribute, you get back to positive b. Okay, so that is what we change it to. And now look at this. Do we have the same idea here? We've got the cos part that is done. We've got cos as well. We've got a first angle that is done. We also have a first angle. We've got minus in the middle. We also have minus in the middle. And we've got a second angle. We also have a second angle. And now we can use this idea on this expression. We can go ahead and expand it. Okay, let's go ahead and do that. So with this, it says if you have cos of your first angle minus your second angle, it should be equal to cos of your first angle first. And that's what we're going to do. We're going to say it's equal to cos of our first angle. Our first angle here is 90 minus a. So 90 minus a. And then they say you have to have multiplied by your cos of your second angle. So we're going to have the same thing here. Cos of our second angle. Our second angle here is negative b. So cos of minus b. Then you see that they change their sign to a plus. We also have the same idea, so we can follow it. We change it to a plus. Then they have sine of your first angle. So we'll say sine of our first angle, which is 90 degrees minus a. And then sine of the second angle, which is sine of our second angle, which is negative b. And there we go. We have expanded this using this idea. Okay, so that is actually what they're asking you to do. Use this principle, use that rule on this expression. Use it to expand that expression. Okay, so this is what we have, and let's go ahead and simplify now. Cos 90 degrees minus a will give you sine a. So that becomes sine a. And then we have cos negative b. Let's simplify this on screen. You see, if you have cos of a negative angle, what you do to make the angle positive is you add 360 degrees to it. So if you add 360 degrees and you still have minus b, You see that that creates that reduction 360 minus b, which lies here in the fourth quadrant. And you know the cos is positive in this quadrant. So this is just going to get reduced to positive cos of b. That's what happens there. See, cos 360 minus b is cos b. And then we have plus sine 90 minus a. Using your cofunctions, that gets reduced to, or simplified to, cos a. And then the sine negative b. Again, your angle is negative, so what should you do? Add 360 degrees to it. What is sine 360 minus b? Well, unfortunately, it's in cos's quadrant, and sine is not positive here, so this would be reduced to negative sine b. Okay, now we can go ahead and simplify further. So this is equal to, we still have the sine A cos B. But over here, do you see that you have positive cos A being multiplied by negative sine B? So they ultimately just give you negative cos A sine B. And that is our answer. Do you see how we were able to take sine A minus B and make it equal to its expansion using the idea of cos A minus B being equal to that? Okay, so we have finally done that. We have proven to them that sine A minus B is indeed equal to sine A cos B minus cos A sine B. And there we go. Okay, so it's part of the proof of the compound angle formula, but it's really just the ending part, not really the beginning where we find A and B and stuff. Okay, moving on to the next question. Okay, 5.3.2 says, hence or otherwise determine the general solution of the equation sine 48 cos x minus cos 48 sine x equals cos 2x. Okay, so they say hence or otherwise. Do you see now that here they are using the compound angle formula? Okay, hence or otherwise, because we just proved that compound angle, right? They want you to now use this on what we have here. Okay, now with this, because we have really weird looking numbers, and this is actually, if you reduce this, it simplifies to, if you simplify this, okay, using the compound angle rule, this is in the form of sine A, first angle, cos B, a second angle, minus cos of your first angle, which is 48, and then sine your second angle. As you can see, this is the sine compound angle rule. So we're going to have A minus B. That's what it simplifies to. But this looks terrible right now, because how are you going to actually find the general solution of this? You have sine and then you have cos. So we have to actually look at this from a different angle. And it's 5 marks. So clearly that's not all they wanted us to do. And we can't just find the answer like that. Let's just think about this. Okay, so here's the thing. The main problem here is the fact that if you simplify this, you have cos and you have sine. You don't want to have that. You can either have them just being an angle and sine, or an angle and cos, or at least them both being cos or both being sine. The problem right now is this is not working out. Even if I try to expand this to something that has sine, it's not very helpful, because if I expand it to 1 minus 2 sine squared x, well, I still can't solve, okay? I know this is not supposed to be A minus B. It's supposed to be first angle, 48 degrees, minus second angle x. Either ways, this is not helpful. This is really not helpful at all. I can't actually do anything with this. So here's the thing. The squares are going to complicate things a lot. So we're not going to change this, because it's always going to give us a square. The problem is not the cos 2x, clearly. The problem is how we're simplifying this part. So let's look at that. How can we simplify this? Well, if you look into what they're actually saying, they say hence or otherwise, meaning, you see what we just did now, before this? You're going to have to use that idea on this. So how can we use what we just learned from the previous question to help us here? Okay, let's think about this. To do this, instead of simplifying it to this, do you remember that they told us initially, use the fact that cos A minus B is equal to this to find the expansion for sine A minus B. That would mean that when we find that expansion for sine A minus B, we know that it's finally equal to this, right? It means we can get the sine A minus B to become a cos of something. We can get it back to cos. Okay, so if we were able to get it from this point to look like this, then that's exactly what we need to do here. So it's okay that we have sine 48 minus x, but having sine and cos is not helpful. So what we need to do is take this further. Instead of leaving it as sine, we're going to go ahead and change that sine to a cos like we did here. Okay. So do you remember that if you want to change a sine function to a cos, you use cofunctions? And that's what we're going to do here. So to change something that has sine of an angle to cos, it becomes cos 90 degrees minus that angle. Okay. So we're going to change this sine to become a cos. So change that by saying, okay, we'll change it to cos of 90 degrees minus the angle that we have. So here we call this theta, but our angle here, the sine of, right, that angle we have is 48 minus x. So we'll change that to 48 minus x. And remember, I put a bracket here because we have two terms. Okay, so let me just erase these because I don't really need that anymore. Is equal to cos 2x. See? Now we have cos and cos, which is really what we want. Okay, let's just go ahead and simplify. We've got numbers here. They can actually simplify. So this is cos. We have 90 minus 48 degrees. And when you distribute to the x, it becomes a positive x. Is equal to cos 2x. Okay, so this is what we have. And 90 minus 48, we can actually simplify that. So this becomes cos of, and we have 42 degrees plus x. And then this is equal to cos 2x. And this looks great. Now we can actually find the general solution of this expression, this equation, sorry. Okay, so this is what we have. Okay, we have cos on both sides. You can take one cos over, and then you can go ahead and find your reference angle. So the idea is once you take a cos over, you're really just trying to find the reference angle. So we're saying reference angle, but now because I'm taking this cos over, this is what we are solving for. So I'm highlighting that. That's what we're going to solve for. And then we're taking the cos over. And when cos goes over, it becomes the inverse of cos, which is the second function of cos. Shift cos on your calculator. When you have the second function of cos and the actual function of cos, because they're the inverse of each other, they will cancel. And then you'll be left with a 2x. So your reference angle here is 2x. But what you're trying to solve for, what your subject is going to be, is the 42 degrees plus x. So this is now finally, we'll say therefore, remember what our subject is the 42 degrees plus x since we took this cos over. So that is now 42 degrees plus x is equal to, and then we start solving for this function. So let's just establish how we're going to solve for this. For the sake of this video, because it is an end of the year paper and people are practicing, I know that most students use the table, the Cartesian plane method, the standard method. Okay, I do use the quick method, but I will just use that method for the sake of this video because it is a November paper. Because we have 2x, right, the x represents our acute angle. So cos is actually positive here. So we're going to go ahead and use the reductions in the first quadrant and in the fourth quadrant because these are the places that cos will be positive. In this, it's just going to be theta, meaning whatever your reference angle is. And here it's 360 minus theta. So that's what we're going to use. So we're saying our subject, which is the 42 degrees plus x, is equal to, and we'll first have the theta, our reference angle, which is 2x here. So 2x, then, because this is the cos function, it repeats every 360 degrees. So we'll say plus 360 degrees k. Now I like to say k 360 degrees. Okay, so I don't forget the k. Then we say or, And then again, our subject 42 degrees plus x is equal to, and we're going to use the fourth quadrant reduction on it. So we're saying 360 degrees minus our reference angle, and our reference angle is 2x, so minus 2x. Then we'll have plus k of 360 degrees, and don't forget to tell them that k is an element of integers. Now we can get into solving for x in each of these equations. So we have here, we can leave x here, and when you take 2x over, it becomes a negative 2x is equal to, the 42 degrees is positive. When it goes over, it becomes a negative 42 degrees, then plus k of 360 degrees, and then x minus 2x is negative x, and we have negative 42 degrees plus k 360 degrees. We need to solve for x, not negative x. So let's go ahead and divide both hand sides by -1, or multiply both hand sides by -1. And then x is equal to 42 degrees. And that becomes a minus k 360 degrees. Okay, and then here, let's go ahead and solve for x. We have, let's leave our x on this side here. And then we have a negative 2x, so we take it over and it becomes a positive 2x is equal to, we have 360 degrees still on the right hand side. On the left, we're taking the 42 degrees over and it becomes negative, then plus k of 360 degrees. This becomes 3x is equal to, then 360 minus 42. Okay, so it's 360 minus 42. 60 minus 40 is 20. 20 minus 2 is 18. So this is 318 degrees we'll have, then plus k 360 degrees. Not yet done. We need to solve for x, not 3x. So divide both hand sides by 3. And when we divide, we'll have, therefore, that x is equal to, what is 318 divided by 3? Okay, that is 106. So 106 degrees, and then 360 divided by 3 is 120. So that's plus k of 120 degrees. And there we go, where k is an element of integers. And they asked only for the general solution. So that is the general solution for this equation. Okay, now I actually think some students would have taken a different approach. So I'm just going to actually mention that here. So here, I'll still use this same idea of that quick method, but I just want to show you that you could have chosen a different subject. So instead of looking at it like this, you could have decided to rewrite it as cos 2x is equal to cos 42 degrees plus x. And then you can take this over, and then you have a reference angle, meaning this is now your subject that you have, is equal to, when you take cos over, becomes the second function and it cancels with that cos. So your reference angle now becomes 42 degrees plus x. Okay, doing the same thing again. Our subject 2x now is equal to, and we will take our reference angle, which is 42 degrees plus x, then say plus k 360 degrees. Or again, our subject 2x is equal to, then like we did here again, 360 degrees minus your reference angle. So 360 minus, but this time our reference angle has two terms, so you need to say 42 plus x in brackets, and then plus k 360 degrees, of course, where k is an element of integers. So we could have also done it like this. Okay, it's going to look a little different, but it still maintains the same idea. It will still find the exact same solutions. So here's what I mean by that. You see 2x, if you take the x over, it's 2x minus x, which is x. And so your answer here is 42 degrees plus k 360 degrees. Okay, and I think it was only that part really, because this part was still fine in a way. Okay, let's just distribute. 2x equals 360 degrees minus 42. We can just go ahead and just start putting these answers down. So 318 degrees, and then that distributes and becomes a minus x plus k 360. Okay, again, you take that over, it becomes a positive 3x, and we have 318 degrees and then plus k 360 degrees. So do you see that this one would still stay exactly the same? See, same thing, no difference there. The only one that is different is now this one. Now, you shouldn't panic and think, oh no, my answer is wrong. It's not really wrong. Okay. This will still get the same solutions. Just here you have a negative k and here you have a positive k. But remember, k is an element of integer values. Okay, here's an idea. Here's an explanation of this. If you had 42 degrees minus 3k of 360 degrees, right? And you have 42 degrees plus k 360 degrees. Okay, because that's what we have on both sides. K 360 degrees. I'll show you that it actually gives you the same answers. Let's give an example. Let's say k here was equal to 2, and let's also give where k is equal to negative 2. Okay, for these two solutions, do you see that if you substitute k, the values of k, you're still going to end up getting the same answer. They'll just be switched around, that's all. So 42 degrees minus, and in place of k, let's start with the 2. So you have minus and 2 and the 360 degrees, right? You can get that answer. You see that that answer gives you negative 678 degrees, right? Now, if you substituted, instead of the 2, you substituted negative 2. What you would get here, you get a different answer, but this is just for this solution, okay? So 42 degrees minus, and in place of k, we put negative 2 instead, and then times 360 degrees, okay? So in place of that, we're going to put negative 2. Do you see that here we get 762 degrees? Okay, so here is what I mean by this. If you substitute k being equal to 2 and k being equal to negative 2 here, you will still get these two values as your solutions. So here's what I mean by that. When we go ahead and substitute 42 degrees plus 2 and then 360 using that solution that we get 762 degrees, which we know we already had. And if you change that 2 to a negative 2, you get negative 678 degrees. You see that is the exact same solutions that you're going to get, okay? Because k is an element of integers. So if you wanted to deal with it like that, okay, where you make this 2x the subject instead, it would have still been fine, even if your answer looked a little different. So even if you wanted to use this, your answer would have looked different, but then it's still the same thing really because of that k being an element of integer values. Okay, so that is it. I just decided to put a little more explanation into that just in case. And then we move on to the last question in question 5. Okay, 5.4, we have to simplify this trig expression to a single trig ratio. Okay. So let's see what we have. We have, now immediately, it's weird though because you see sine 3x and sine x. Please, that does not become sine 4x. They're not like terms, okay? Because these are angles we're referring to. So 3x and x are just angles, okay? If you have something like 3 sine x and 2 sine x, then those are like terms, you see, because they're in terms of the same angle, sine and the same angle. Okay, so in this case, what we can do, because they're not like terms, you can't just add them together. We can actually just expand them. So let me rewrite what we have first. So when rewriting this, I'm also noticing now, you see with the 3x is quite simple to expand that. Normally, if you see something like 3x, you can expand it to 2x plus x. And these are good angles to expand it to, because you know that if you have sine 2x, you can expand that further. Sine 2x is a double angle. You can expand that further. But then now what do we do with the sine x? Now we can choose to just rewrite it there, but let's take advantage of the fact that they gave us sine and sine. Okay, they're the same function. So look at how we can manipulate this. So we have plus, and instead of writing it as just sine x, x can be formed by saying 2x minus x. So there we're using 2x and x because these are angles we can actually expand further using double angles. So let's call it 2x minus x. So please see this now as a key thing. If you ever see a situation where you have the same function and then you have sine of like 3x and x, you can actually do that. Okay, so let's go ahead and expand this. We're going to say this goes over, and we have this here. Now I notice that we have a plus. Okay, we can get rid of that plus 1 because of what cos 2x can expand to. Cos 2x can expand to 3 things. But the one that we can choose is this one that says 2 cos squared x minus 1. Because when you add that plus 1, they'll become a 0. Now, I'm looking at that. I'm like, I'm not really sure why I'm doing that yet. And it's not good to do things and not know why. So I'll hold on to this and then I'll see if that's necessary to actually deal with like that. Okay, let's go ahead and expand. So the reason why it is good to expand these two like this is because you see that it's the exact same function, but here you have 2x plus x and here you have 2x minus x. So eventually when you expand it, you're going to have a term that's just going to cancel because one is going to be the positive of it, the other is going to be the negative of it. Okay, so here is what we have. When we expand this using the compound angle formula, it's going to be sine, let me just start on a new line. So this is going to give you sine 2x, and then you're going to have cos x. Because it's a plus, it stays plus because this is sine, and then it says cos 2x and then sine x, right? That's what we have there. Now look at what happens when we expand this one. We have plus sine 2x cos x again, but instead of a plus, now we now have a minus, so that changes to minus, okay, minus cos 2x sine x. And do you see what will actually cancel through here? Okay, because this is negative, it's really the same thing that it expands to, just now this is now negative and this one is positive, so they will both cancel, okay, and become 0. Then on the denominator, yeah, I'm actually seeing a reason why I should change this now, because you see now that you have sine 2x cos x, right, and sine 2x cos x, which are like terms, they're going to go together. So it's actually very helpful to get this to a point where it just says 2 cos squared x, because a cos x can actually cancel there. So we can change that. That is fine. So let's change the cos 2x part to 2 cos squared x using the expansion of the double angle formula for this. And then we have minus 1, right? Then we still have that plus 1 outside. And so these two would cancel and become 0. Okay, let's rewrite what we have now. We just have the sine 2x cos x plus sine 2x cos x. It's two of the exact same thing. So it becomes 2 sine 2x cos x. And this goes all over 2 cos squared x. Okay, this has become very simple. So now we can cancel here. Those two will cancel. So cos x and one of the cos x cancels here. And then the 2 and the 2 would cancel. And we're left with sine 2x, which can be expanded. Should be expanded really, because it will help to cancel with what we have there. Sine 2x gets expanded to 2 sine x cos x. And then this goes all over cos x. Okay, so cos x. And you see that cos x and cos x will cancel on the top and the bottom. And our final answer is 2 sine of x. And that is the final answer. And that is the last question for question 5. And we finally move on to question 6. We are on question 6, and question 6 says, in the diagram, the graphs of f of x is equal to 2 sine 2x and g of x is equal to negative cos x plus 45 degrees are drawn for the interval where x is an element of 0 degrees going to 180. Please notice that they're using square brackets here, which means that you see these coordinates 0 degrees, this x value 0, and 180 degrees, they are actually included here, meaning we have a physical point on the graph that has an x value of 0 and another point on the graph that also has a x value of 180 degrees for both graphs. Okay. And then they tell us that A, which is 105 degrees and negative 1, lies on F. So that is that point over there. Okay, the first question is, write down the period of F. Okay, so remember, the period of a graph is really just how long the graph takes to complete a cycle. So if you look at the graph of f, that is our sine graph. So this is how we'll find the period of a sine graph. You have to think about a normal sine graph. How long does it take the normal sine graph that has not been manipulated in any way to complete one cycle? So this is one cycle, right? The normal sine graph completes a cycle in 360 degrees. So how you will find the new period of a graph that has been manipulated is like this. You would take the old period, okay, so the new period is equal to the old period, which we know is 360 degrees for the sine graph, and you will divide it by the value that they are using to manipulate that period. Now, here's where we find that value. Remember, the period has to do with the angles it takes to complete a cycle. So here in f of x, what number is manipulating the angles here? That would be this 2 over here. Do you see it in front of the x? The x is your angle. So that number is what's manipulating our period. So we're going to say divided by that 2 over there. So 360 divided by 2 gives us 180 degrees. And so what it means about this graph is that this graph is not completing a cycle in 360 degrees anymore. It's now completing a cycle within 180 degrees. So that would have been 360, but now your graph is going to complete in 180 degrees, making the graph look more narrow. So it's thinner now. Okay, so that is the first question. Moving on to the next question. We're now on 6.2, and 6.2 says, determine the range of g in the interval where x is an element of 0 to 180 degrees. So within that same interval, the same domain that they gave us. So we're looking at the range of g. Okay, so the graph of g, look at how it looks. It goes like that and then up like that. Now, the truth about this is we don't really need too much of this information. However, we will look at it. Please note that the range of a function is all the possible y values of this function. So when you're looking at this function, you see that it's a function that was translated. Okay, this cos graph was shifted, and as you can see, you have plus 45 degrees. So it really means that the function was shifted 45 degrees to the left. Okay, remember, if it's plus, it's left. If it's minus, it's right. And that is when it has to do with the x, okay, when it's a horizontal shift. So when we are looking at this function, we're looking at all the possible y values that it has, okay, the first or the lowest y value right now within this domain, 0 to 180 degrees, would be this over here. Do you see that the graph doesn't go anything lower than that? So we would have to find out what exactly this y value is. Now, this is not so difficult to find out. You don't have to overthink it, because the thing is, you can see that this is on the y-axis. So its x value is 0. So to find the y value, why don't you take that x value and substitute it into this equation? So that's what we're going to do to find the y value here. And what we get is, this is negative root 2 over 2. So that is our y value. That's the lowest y value right now within this interval. And then you see that you have other y values. You have y value here and here and here, and it keeps on going. And do you see that it has a y value that has the highest point? Okay, now that y value will not be difficult to find, because remember, this is still a cos graph. And this cos graph, yes, it has a negative in front of it, okay, meaning the normal cos graph that is supposed to look like this. Because it has a negative, it's now the other way around. Instead of going down, then up, it now goes up, then down, okay. But it would still mean that the highest it should reach is at 1. That is the y value of 1. That is the highest that that cos graph should go. As you can see, it goes up and then it hits the highest and then it begins to curve. So it indeed does have a maximum value of 1. And then, of course, it starts to go down. So all of these other y values, we already have them here. So what we will say for the range is that the range starts, okay, the smallest y value we have is negative root 2 over 2, and it goes all the way to 1. And those are the only y values that we will have for this graph. Here is how we can write that. So remember, there are two formats. that we can use to write this. So we can write it in interval notation or set builder notation. Okay, so with the set builder notation, that's actually inequality way of writing, inequality notation. We can write it like this. We can tell them that our y values are values that are, first of all, greater than or equal to. So you see that they start here. That's the lowest you can get. Greater than or equal to negative square root 2 over 2, negative root 2 over 2. But less than or equal to the highest one was 1. That was the highest that it can go. So less than or equal to 1. And that will be in the inequality notation, okay? Or set builder notation. Or you could write it like this, in that format, which is your interval notation. So we can say y is an element of, and we start at negative root 2 over 2, and then the highest it reaches is 1. Now, the brackets that you use here is very important. Do you see that in the domain, right? We have 0 as an actual x value on this graph, meaning this y value is also on the graph. That's why here we said greater than or equal to negative root 2 over 2. So here you have to use square brackets for them because these y values are actually included y values on our graph. Had your inequality look something like this, instead of just saying greater than negative root 2 over 2, then you would use a round bracket for that because it's not including negative root 2 over 2. Okay, so that is how that looks. Moving on to the next question. The next question, 6.3, says determine the values of x in the interval where x is an element of. Okay, so the same interval for which f of x multiplied by g of x is greater than 0. So this is something they always bring in. Remember, if we're saying something is greater than 0, another word for this is that this is positive. So we need to find the values of x for which when we take the y values of f and multiply it to the y values of g, they give us a value that is positive. The only way this is possible is if your graph of f has a positive y value and at the same time or for the same x values, your graph of g has positive y values as well. Then if you multiply them, they will also give you a positive y value. See, positive times positive is positive. The other way that this can actually happen is if your y values for your graph of f is negative and your y values for your graph of g are also negative, and then they would also give you a positive result. So this is what we're looking for. We're looking for places where the graph of f and g are both positive or where they are both negative. So let's go ahead and look for that in our diagram. Okay, so where is the graph of f and the graph of g, both positive and both negative? We're going to go ahead and use this vertical line. You can use a ruler. So you're going to go through it like this. So let's start here. You see, they said greater than 0. They didn't say equal to 0. So you can't include points like this. You see, this graph, the graph of f, here at this point of 0, it has a y value of 0. This one has a y value of that negative square root 2 over 2 that we found. If you multiply them, that's 0 times that negative root 2 over 2, that gives you 0. So we can't include the actual x value of 0 degrees. That's not going to work out here. But if we keep moving, do you see here now that look at this part of the graph over here? The part of this graph of f has a positive y value. And for the same x value, that's why we use a vertical line, the part of this graph of g, this point here has a negative. See, if you take that positive y value and multiply it by negative, you get a negative result. We're looking for positive results. So they need to either be both positive or both negative. Let's keep moving. As we keep moving, you see that's still positive and negative. We don't want that. Positive and negative. Then something happens here at 45 degrees. At 45 degrees, the graph of g hits the x-axis. So it has a value of 0 and a positive. So we won't take that physical point of 45 degrees. But when we go after 45 degrees, do you see now that this has a y value of a positive y value? I don't know what that is yet, but that's a positive y value. And then this also has a positive y value there. They're both positive. If you keep moving, also both positive. Again, they both have positive y values. Keep moving, even at the point of intersection, they both have positive y values. And as we keep moving, They have positive y values here until 90 degrees, because at 90 degrees, the graph of f hits the x-axis and it now has a y value of 0. We can't take this because this is 0 times a positive will give you 0. We're not looking for where it gives us 0. So you see that it worked all through there. Let's just highlight that. So with that, we're saying that it worked here. It started after 45 degrees and it started working here like that. So really, let's just mark it like this. At 45 degrees, after 45 degrees, we started seeing that these graphs both had positive y values, and they stopped at 90 degrees. They didn't have any more positive y values after 90 degrees. So they worked all through here, okay, for both graphs. There, they both have positive y values there. We will take those coordinates. And then let's go ahead and keep moving. Now you see that here, the graph of G has a positive y value. The graph of F has a negative y value. We can't take any of those. Okay, that's positive and negative. Can't take. And unfortunately, it doesn't happen anywhere else again because they just keep being positive and negative all through. And then here they are 0 and positive. Okay, so that's the only place that it works. And so we can go ahead and write down these coordinates, or really the values of x for which this happens. You see, it happens between 45 degrees all the way to 90 degrees. This can be written as x is greater than, but not equal to, okay, 45 degrees, but less than 90 degrees. And that would be our answer for that. Okay, again, this is the inequality notation. We can also write it in interval notation, which would be x is an element of, and then we'll say it's going from 45 degrees all the way to 90 degrees. But remember the kind of brackets you're going to use here, because 45 and 90 are not included x values. You will use round brackets. Okay, there we go. So that is our answer for that question. Moving on to the next question. The next question, 6.3.2, says we need to determine the values of x for which f of x plus 1 is less than or equal to 0. Okay, guys, they always do this. Remember, they just put in this plus 1 here. You don't have to put the plus 1 and start thinking about, like, if I shift the graph up, where is it less than or equal to 0? No, you can just take the 1 over. So this function is actually reading as f of x, this inequality, is less than or equal to negative 1. Okay, and now we can go ahead and find the places where the graph of f has a value that is less than or equal to negative 1. Do you remember they gave us a specific point that had that negative 1? Okay, the point they gave us was this, A. So when you're looking at the graph of f and you're looking for parts of the graph that are either less than or equal to negative 1, it means that at negative 1, we are only going to take parts of this graph that lie below negative 1 or that are equal to negative 1. So that is over here. See, all of these have y values that are less than negative 1. Okay, and we're also going to take the places that are specifically equal to negative 1. So at this point over here, your y value is negative 1. At this point, it's also negative 1. And we need to just tell them the values of x for which this is actually happening. Okay, so for the first part, it's simple because they already gave you the coordinates of A. They said it's 105 and negative 1. So it means that this x value over here is 105 degrees. But then we would need to find this one over here. Now, how you find this here is you're going to have to think about how the graph, right, works, the original function of the graph. So I'm going to give a brief explanation. I hope it's not going to take too long. I'm going to give a brief explanation as to how you can actually find the angles in your function when you know what the y value is. Let's take a look at what the graph of f of x looks like. You see, it says 2 sine 2x. So this graph has already been manipulated, okay? The period has been changed. The amplitude has been changed, okay? That all of these things have been altered already. But we're going to try to understand what the normal graph looks like and then understand how that relates to this and how we can actually get this value over here. So here is the thing about the sine graph. The normal sine graph, the original one, the mother graph, is y equals sine of x. And that graph is quite simple to draw. In fact, if you just have a calculator or you're using one of those special angle formulas, okay, like the OHA rule or even the triangles or the circle, you can actually figure out what these are. So the sine graph looks like that, right? And you just have to remember the key points on it. You know that at this point over here at 0, it has 0 degrees and 0. And then here, this is where it hits the y value of 1. And then here it has 180 degrees, 270 degrees, and the y value here is -1. And then 360 degrees. That's what the sine graph looks like. And if you look at our sine graphs, we're in luck because at least they didn't change the sign of that value there. Okay, it's still also going up and then down. See, like here. But we just have to understand exactly what this y value of -1 would be on the original sine graph. So let's think about it like this. Do you see that this graph, in front of sine, there is a 2. So instead of it having a maximum of 1 and a minimum of -1, it now has a maximum of 2 and a minimum of -2. So what would that mean for this -1? What is the y value of -1 on the original sine graph? Because this was changed to 2, it just means that all these key points here, this 0, the 1, the -1, they were just doubled. So a y value of -1 on the original sine graph would actually be half of this. It's not -1 here, it's actually -1/2. So if you found what the y value of -1/2 is, you'd be able to actually find out what these ones are. But also remember that the amplitude has also been altered, and we'll speak about that as well. So let's first of all focus on finding out what exactly the x values would be for this graph if our y value was -1/2, okay? And that's really the equivalent of -1 in this altered sine graph. So let's look at that. Now you see that it has actually 2 places where it's equal to -1/2. It's here and here. And here's how we can actually find this. So we're trying to find out where is y, at which value of x, or which values of x is y equal to -1/2. Here's how we can do that. So we're trying to find out where sine of x equal to -1/2, and we can actually use the method of solving for general solutions to do this. But remember, we're only trying to focus on from 0 degrees to 360 degrees right now here. So this is what we can do. We're going to find our reference angle. To find the reference angle, you take sine over, but I'm going to use the Cartesian plane method. So I'm not going to say shift sign of this negative. We will take the positive angle, but we're going to keep in mind that sine was negative, okay? We're not going to say -1/2, we're saying shift sine of 1/2, okay? So we just want to find the reference angle. That is 30 degrees. So because sine is negative, now to find exactly what angles these would belong to, you're going to have to think about on the Cartesian plane, where is sine negative? Sine is negative in the 3rd and the 4th quadrant. So that is tan and cos's quadrant. Now what are the reductions that you have here? You have 180 degrees plus theta, and you have 360 degrees minus theta. So to find exactly what these values are, we're going to use these reductions, and you will see that we will find those values. So here, first, when we're trying to solve for x is equal to 180 degrees plus theta, which is 30 degrees. And of course, you'll say plus k of 360, but we don't have to do that. We're not looking for general solutions. We're just looking for this in here. Okay, so x is equal to 210 degrees. Or the second value here, so we know what this one is 210 degrees. The one here, the one further, that is going to be where x is equal to 360 degrees minus 30 degrees, which gives you 330 degrees. You see how we're able to find that? Now we have to take into consideration that this graph that we have was altered. They changed the period of the graph. So you see how the period used to be 360 degrees and now is 180 degrees. It just means it was cut in half. So that's how all the angles on your graph will also behave. They will also be cut in half. They'll also be halved as well. So how we're going to look at this is like this. You see the 210 degrees, because remember, the equivalence of negative a half here is -1 because of that 2 that they put in front of this. So we had 210 degrees here, right? We know that at negative a half, the x value is 210 degrees. But you know that the function that we have has that 2 in front of the x. So what you're going to do is take this angle, this solution that you have here, and you're going to divide it by 2. You see that if you take 210 degrees and you divide it by 2, you get 105 degrees. That is the 105 degrees that appears here. And so to find that second one over here, because they have tampered with the period of the graph, okay, the period is now completing in 180 degrees. You're going to take that 330 degrees and also divide that by 2. Okay, all the angles here are going to be divided by 2. And we can actually see that because do you see that this graph completes a cycle, right? In 180 degrees. Here it completes in 360 degrees. Here's another thing. Do you see that at 90 degrees, your sine graph is touching the x-axis? Here at 180 degrees, it's touching the x-axis. All the angles here just get divided by 2, represented here. Okay, so 330 degrees divided by 2, we got what? 165 degrees. So we know exactly what angle is here. It's actually 165 degrees. So this took longer because I'm actually explaining it. Normally, you would learn these graphs and then you do these calculations really quickly and then you'll be able to write it down. Okay, so that was a little detailed explanation on it. I always apologize for making it too long, but I also just want to make sure that you guys actually do understand what's going on. And thank you to all the students who actually said it was fine to be explaining it in more detail because I really don't want to just rush through this paper. Okay, perfect. We now know what these two angles are. And now we can actually answer the question. So remember, we're just trying to find out the values of x for which this exists, okay? For which f of x is less than or equal to -1. So that starts at 105 degrees. And then you see it's values that are greater than 105 degrees, all these values, but less than or equal to 165 degrees. And so that would be our answer. We can write it as x is greater than or equal to 105 degrees, but less than or equal to 165 degrees. And there we go. And then you can also write it in interval notation, which is going to be x is an element of, and we're going from 105 degrees to 165 degrees. But then remember, we have is equal to, meaning 105 and 165 are included values. So you need to use square brackets. And there we go. So that is our final answer there. Moving on to the next question. Question 6.4 says, another graph P is defined as P of x is equal to negative f of x. Okay. And then we have D, which is k and -1, and that lies on P. Determine the values of k in the interval, again, in that interval above. So we have to actually find the values of k if we have a new graph called P, and P is found by saying negative f of x. Okay, so just put a negative in front of f of x to find the equation of P. And we have to find exactly what this coordinates, this x coordinate k is if the y value is -1. Okay, let's go ahead and do that. I feel like I should have left that diagram that I drew, but it's fine. We'll just work with it without it. So let's go ahead and rewrite this equation. Since it is negative f of x, it just means you're going to take the graph of f and put a negative in front of it. So the graph of f was that 2x, right? That sine 2x, 2 sine 2x. And so we put a negative in front of it, and now we have negative 2 sine 2x. So the k points they want us to find is this D, which is the D point they want us to find is k and -1. And with this point, do you see that the y value is -1, the x value is k? So solve for k if y is equal to -1 on this graph of P. So because y is -1, we're replacing, in place of P of x, that y value, we're going to replace that with -1 to find out exactly what this is. And so we have -2 sine of 2x. And we need to really solve for x because that's going to give us our k value. Now, you can do this using general solution, but it's going to take really long. So I'm going to actually deal with this thinking about what the original function looks like and what the translated one, the one that has been reflected, okay, across the x-axis. That's why it has a negative in front of f of x. So when we have this like this, do you see that they're just both negative? So you can just multiply them both by -1 to make them positive so that we can properly relate this with the graph we have, because the graph of f of x is 2 sine 2x. It doesn't have a negative, right? So that's what we can do. Or if you like, you can see this as taking this -2 sine 2x over, so it's now a positive 2 sine 2x, and then taking the -1 over and becomes a positive 1. So ultimately what they're asking you is, tell us the value of x for which 2 sine 2x is going to be equal to 1. You already have the graph 2 sine 2x. It's this function over here, the graph of f, that is 2 sine 2x, right? And we need to find out, where does it have a y value of 1? So do you see that it has a y value of 1 at 2 places, here and here? Again, if you know what the original function looks like, you know exactly what these two values should be. So you can think about the original function. I'm just going to redraw everything like I did before. So because this is the original sine graph, when we are looking for where 2 sine 2x is equal to 1, okay, what that means for your original sine graph is, because this, everything is doubled on the y-axis, okay, so the 1 here is actually referring to a half. Here's another way to actually see that. You see, you have 2 sine 2x is equal to 1. If you were just trying to get the sine 2x so that you can find out what exactly that is, you would try to get rid of the 2, and it's multiplying, so you have to divide both sides by 2. So we have sine 2x is equal to a half. You see that? That's why that 1 that we see here on the original sine graph, it's actually a half. So in other words, what you're trying to do here is, first of all, find out where is this sine graph going to have a y value of a half. It's here, clearly, this value over here and this value over here. And we can just go ahead and find out that. First of all, this is actually quite simple to find out because we're working with the positive y value. So sine is positive here. So we can just say, where is sine of x equal to a half? And go ahead and find that reference angle. So take sine over. If you say shift sine of a half, you get 30 degrees. So that's what we have here. Because sine is positive in the first and the second quadrant. Okay, so you would only use the reductions x is equal to 30 degrees, of course, plus k of 3 60 degrees, but we don't have to include that. We're not looking for general solutions. Or you say x is equal to 180 degrees minus your reference angle. That would be sine's reduction there, which gives us 150 degrees. Okay, so now do you see that here on the original sine graph, where the graph of sine x is equal to a half is at 30 degrees and at 150 degrees. So what would that be on this graph that has the period been changed? Okay, the period is changed here. So remember, all the angles, to find them from the original function, you would just divide these angles by 2, because what happened is we put 2 in front of the x. The same way the period of the graph changed from 360 to 180 degrees, you just halve all these from the original function to find the one from the function that has been manipulated. So that over here is going to be, we'll find that by saying 30 degrees divided by 2, which is 15 degrees. So this is 15 degrees here. And then we'll find this one by saying that 150 degrees divided by 2. 150 divided by 2 is 75 degrees. So there we go. You can work through these by thinking about how it relates to the original function. Okay, so those would be the x values at which your y value has that. So our values for k for this equation, where -1 is equal to -2 sine of x, you see we simplified it. The values for k is this, where k is equal to 15 degrees or k is equal to 75 degrees. Okay, so I put it like that because why would you want to work with a -2 sine of 2x graph? We don't even have that function there. You would have to draw it and then start thinking about where those values would lie. What we could have just done is, okay, we see that we have negative and negative. Just get rid of the negative so we can relate it to our function 2 sine 2x, which we actually have drawn in our diagram. Okay, so that is the answer for that question. K is equal to 15 degrees or K is equal to 75 degrees. You can also show those workings. Okay, done with that. Moving on to the next question. Then the last question for question 6 is 6.5, which says the graph of h is obtained when g is translated 45 degrees to the left. Determine the equation of h. Write your answer in its simplest form. Okay, so in its simplest form. They told us that the graph of h, this is a new graph they're introducing, is obtained when g is translated 45 degrees to the left. When you have left or right movements, these affect the x. Okay, now it's moving 45 degrees to the left. Remember, if the graph moves to the left, you add. If it moves to the right, you subtract, okay, from the x. So there we're going to have x plus 45 degrees. That's what's going to happen there. So in the notation format, we're saying that h of x, this new graph, we get that by taking the graph of g, right? And what we're doing to the x, because it's moving to the left, is we are going to add 45 degrees to the x. And that's really what we're doing. And we need to now just solve and find out what exactly the equation of h is going to be. Okay, so what is the equation of g? What is that graph? That was negative cos x plus 45 degrees that we already had. So let's go ahead and put that down. Okay, so this is h of x is equal to, and now in our graph of g, wherever you see x, you're going to add 45 degrees to it. Okay, so our graph of g is negative cos, and then you see x, then you can add the 45 degrees now if you want. So 45 degrees, but remember that it already had plus 45 degrees. So it already had plus 45 degrees. And so when you simplify this, h of x is equal to negative cos of x. 45 and 45 give you 90 degrees. And you see that we have a cofunction. Now this cofunction, cos x, so only this part, right? Cos x plus 90 degrees, that gives you negative sine of x. So it's one of those ones that actually becomes negative. It's the only one with the 4 cofunctions that actually becomes negative. So it means that this is now h of x is equal to, we still have that negative outside, but this becomes negative sine x, right? And because of that, when we distribute at the end, our final answer is positive sine x. And there we go. That is the answer for the last question in question 6. And then we move on to question 7, which is on 2 and 3D trigonometry. We are on question 7, and question 7 says, in the diagram, S, T, and K lie in the same horizontal plane. Okay, so in the same horizontal plane, and RS is a vertical tower. The angle of depression from R to K is beta, and they tell us that TSK is equal to alpha, and TS is equal to P meters, and the area of triangle STK is Q meters squared. Okay, so the first question is to determine the length of SK in terms of P, Q, and alpha. So really just find SK. Okay, so SK is over here. How does this relate to P, Q, and alpha? Well, it probably just goes back to what they said, because we're looking at P. Here's P. Q. Q is the area of this triangle. And then alpha is that center angle. So we can use the area that was given, the area of this triangle, because you see this triangle includes the dimensions that we're looking for. Okay, they mentioned that, and they mentioned this, and they mentioned alpha. So we can go ahead and use the area rule, because you saw the sides that they're taking, the side, and then the angle in the middle. So this is the area rule we're going to use. So the area of this triangle STK, triangle STK, is equal to, so how we would find the area of this triangle normally is like this. We would say a half multiplied by, since this is our center angle, we'll take the side next to the center angle, which is ST, but we already have a length for that, that's P. So multiply by P, then multiply by this side, which we're trying to look for, which is SK. And then you say sine of the center angle, which is alpha. Okay. And the thing is, we already know what the area of this triangle is. The area is Q, since it's Q. And then the meters cubed is just the unit of measurement it's in. So this is equal to, and we have, so when we're simplifying this, remember, we're just trying to solve for SK. So we just have to make that the subject. So when we're multiplying, you can see that we just have a half P SK. I'm just going to leave SK as the, in front. So it's SK, then we have multiplied by a half P sine of alpha, because I'm trying to just leave this on its own, because they are multiplied all through anyways. Now that SK is on its own, do you see that to leave this alone on the right hand side, you need to get rid of all of these. So we're going to divide both hand sides by a half P sine of alpha. And then we have, so now this is gone, and we have SK now as our subject. So leave SK here. SK is equal to, and this is what is left. So be careful with the half. Okay, half is a fraction already, and it's on the denominator of a fraction. So you can look at it like this. The coefficient of Q is actually an invisible one. So if you said 1 divided by a half, even if you use a calculator, it would give you 2. So what you have here is 2Q over, and then on the denominator we have P sine alpha. And that is our answer. 2Q over P sine alpha is our expression for SK. Moving on to the next question. Then we move on to 7.2, which says, show that RS is equal to 2Q tan beta over P sine alpha. So we have to find RS this time. So let's go ahead and see where RS is. RS is over here. Now remember, the previous question or the previous solution will help you with the next question. In the previous question, we found this. We found SK. So let's just keep in mind, we already know what this is. So RS is part of a right angle triangle. To find this, we can use, you don't have to use Pythagoras necessarily, but you can use the trig functions, because the trig functions have to do with a right angle triangle. So katoa, right? That's what we're going to use here. Let's see how we can work through this. You see, with your trig functions, you need a reference angle, an acute angle. We have the 90 degrees, but we don't really have any acute angle. But it just depends on how you look at it. Do you remember that they told you that the angle of depression from R to K was beta, the angle of depression? So what this means is, when you're thinking about an angle of depression, you have a flat plane, okay? You just have to kind of look at it like this. You see this line, if we extend it, even if it's not extended, it's actually parallel to this line. We really look at that angle of depression as if this is an eyeball, you're kind of like looking down, right? That angle that it creates is your angle of depression. So these two lines are actually parallel. So because they are parallel, do you see that we have alternate angles here? Now, those are alternate angles, meaning this is beta. So there, now we have an angle inside this triangle, and we can actually use that to find RS. So the thing is, we have our reference angle beta. We are looking for RS, right? And as you can see, RS is your opposite side. But the only thing we have in this right angle triangle is SK, which we found in the previous question. Okay, we found what SK is. So what we're working with is the opposite side, so beta, and the side here, SK, which is the adjacent side. So which function are we going to use to solve for beta? We would use tan because that is the OA, TOA. So we're going to use tan. So we're going to find tan beta. Let's just say tan beta is equal to, and it's going to be equal to the opposite over the adjacent, OA, TOA. Okay, so opposite over adjacent, which is RS, we're looking for that over SK. RS over SK, and now we can go ahead and simplify. So we already found SK, so let's substitute it in place. I can go ahead and call this, so tan beta is equal to, we can do the whole thing on dividing, but yeah, I guess it is necessary here in a way. So we'll say RS, and then we are dividing by this, okay, SK, which we found to be 2Q over P sine alpha. So we'll divided by that. Okay, now at this point, we don't really need to tip in times. Here's why. You see, we just want to solve for RS, that's all. So if we're trying to solve for RS, we just need to think about it like this. So we can think about it like this. What do we need to get rid of so that we can get RS on its own? We need to get rid of this. So think about what this is doing to RS. We are dividing by this. So in order to get rid of it, you would multiply, okay, by it. So even if I left it like this as RS over this, to get rid of that, you're really just going to take your equation and multiply both hand sides by that expression, 2Q over P sine alpha. But what you do on this side, you must do on that side. So as well, we'll also multiply here by 2Q over P sine alpha. Okay, so this would be gone now, because we really just did the opposite to get rid of it. And now we'll have RS on its own. So we can just leave it as RS is equal to, then rewrite what we have here. You see that you have a numerator and denominator will multiply. So the 2Q and the tan beta can multiply since they're both on the numerator to become 2Q tan beta. And then your denominator is the P sine alpha multiplied by the invisible denominator of 1, which is P sine alpha. And that will be our answer for that question, like they have already said. So there's our answer. Okay, moving on to 7.3. 7.3 says calculate the size of alpha. Okay, so they're not going to give us alpha if alpha is less than 90 degrees. Okay, so that's probably just a hint to help us to know, okay, yeah, this is alpha. Or it might be because maybe we have the ambiguous case here, but we don't really deal with that particular topic in the CAPS curriculum, I've noticed. But okay, calculate the size of alpha if alpha is less than 90 degrees. And RS, interesting, they're giving you things here. So RS is equal to 70 meters, P is equal to 80 meters, Q is equal to 2,500 meters squared, and beta is equal to 42 degrees. Yeah, so you can already see which equation we're going to use. We're going to go ahead and use RS's equation because it includes everything except for alpha. Okay, let's go ahead and take that equation. So let's substitute. They told us that RS was equal to 70, which is equal to, we have 2 Q, they said was 2,500, so 2,500, and then tan beta is 42 degrees, and then this goes all over P, which is 80 meters, so 80 multiplied by sine alpha, and what we're trying to just solve for is alpha, so we kind of have to just get that to be the subject. Okay, we can actually do this really quickly. Instead of trying to manipulate things and stuff like that, you know how when you have an equation for like x plus 2 is equal to 5, right? And you want to get to a way to solve for x. I know that we normally say we take it over, but what really happens is you subtract 2 from both sides of the equation, right? And when we work with multiplication and division, we've kind of been working with that idea. When we have things like x times 2, or let's say 2x is equal to 10, for example. So when we have equations like this, right, we normally say, okay, we'll just divide by 2 on both sides, right? Which is the same thing as saying, okay, here we'll subtract by 2 on both sides. But we could have also just said, since 2 is in front of x, it's multiplying by x. So to get rid of it, if we were taking the 2 over, the 2 that was multiplying by the x now starts to divide by the 10. So if it was a multiply by 2 on one side, when it goes over, it becomes a divide by 2. Okay? So it's still the same principle that we've been using. We've just been doing it in a different way. So that's what we can do here. We want sine of alpha to come over here. So do you notice that sine of alpha is being divided by everything here? When you take it over, it now moves from where it used to be. It was on the denominator before. When you take it over, it will move to the numerator. Okay, and it's now getting multiplied by that. But I actually don't want to leave that there. What I'm going to do is take the 70 this side as well. So do you see that the 70 was on the numerator initially? So the 70 is on the numerator. When we want to take it over, it's going to go to the denominator. So we already have the 80, and now we're going to have a multiply by 70 next to it. It just changes its position. If we don't do it this way, you can end up just like cross multiplying, which takes really long. That's why I'm just doing it this way. And so sine alpha is equal to, we already moved the 70 over to the denominator. And then on the numerator, we still have everything else that was there. So 2 times 2,500 is actually just 5,000. And then we have tan of 42 degrees. And do you see now we have numbers all through here? Don't mind the tan. The tan is still a number because it's tan of 42 degrees, okay? So we can actually solve for alpha. Let's just go ahead and simplify this on a calculator. Let's just simplify faster. Okay, so it gives us decimals. I don't really want decimals. So I'm actually just going to find out what exactly the 5,000 over that 80 times 70 is. So we have sine alpha is equal to, that gives us 25 over 28. But we're going to now leave our tan 42 on the numerator. So really you just have 25 over 28, tan 42 degrees. That's what we have. And now to solve for alpha, specifically just alpha, you can take your sine over. In other words, what you're doing is you're finding the inverse. You're using the inverse of sine on both hand sides of the equation. Okay, arc sine. So we're taking that over, and its alpha is equal to shift sine or arc sine of every number that we have here. So this is 25 over 28 tan of 42 degrees, and then we'll just find exactly what that is. So round off to 2 decimal places. Alpha is equal to 53 point, that rounds up to 51 degrees, and that is our answer in the last question for question 7. Okay, that concludes it for the trigonometry part of this paper. Hey grade 12s, and welcome to question 5 of this paper. So in this paper, we're going to be working on the trigonometry section. So that is question 5, 6, and 7. So we're also going to work on the 2 and 3D trigonometry as well. Okay, so question 5.1 says, if sine of 40 degrees is equal to P, write each of the following in terms of P. And then the first one that we have is sine of 220 degrees. Okay, so I hope you guys see the pattern that has been going on. You will notice that with your trig diagrams, they'll usually give you these ones. So you should make sure that you are prepared for these ones. Okay, so you see that it says sine of 40 degrees. If you think about 40 degrees on a Cartesian plane, that is an acute angle. And if we had to measure that angle, we'd really measure it like this. So 40 degrees will be measured from here, and then it's just 40 degrees. So it means that your line or your radius is like that, and then that's the angle that we have there. That's the 40 degrees. And they tell us sine of 40 degrees is equal to P. Well, when you think about the function of sine, sine is speaking about the opposite side over the hypotenuse. So since sine of 40 degrees is equal to p, right? It means that p is your opposite side. And so what's your hypotenuse? Well, the denominator of p would be 1 if you wanted to put a denominator of p. So it means that here in this, when we go ahead and draw a line perpendicular to our x-axis, where we have 40 degrees, the opposite side would be p, so there's p, and then the hypotenuse would be 1, and there's 1. So you see that the only thing we need to find is the adjacent side, or the value of x. Okay, so you can use Pythagoras to find that by saying x squared is equal to, so the hypotenuse squared, which is 1 squared, minus the opposite side squared, which is p squared. And then, of course, if you simplify this, 1 squared is just 1, so that's 1 minus p squared. Then if you want to solve for x, you'd square root both sides. Now, yes, it is going to be plus or minus normally, because when you square root both sides in an equation, you have a positive and a negative solution. But the thing is, as you can see, the x value, right, this number over here is positive. So we don't have to take the negative, we can just take the positive. Therefore, x is equal to the square root of 1 minus p squared. So that's what x is. That is root 1 minus p squared. Okay, now that that is complete, we can actually solve for what they asked for. Okay, so sine 220 degrees. Remember, the reference angle they gave you was 40 degrees. So you know that everything just needs to relate to 40 degrees. That's all, okay? Now we have an angle that is quite big. You can go ahead and reduce this angle. So use your reduction formula. If you think of 220 degrees, which quadrant would that lie in? That would lie in tangent quadrant, the third quadrant, where we're going to have 180 degrees plus theta. So if you were reducing that, that would be sine of 180 degrees plus what gives you 220 degrees. That would be 180 degrees plus 40 degrees, and there's our 40, okay? Then if you reduce this, of course, you're going to get negative sine 40 degrees, because sine is negative in tangent quadrant. Then what is negative sine 40 degrees? Well, if sine 40 is p, negative sine 40 would be negative p, and that's our answer there. Okay, moving on to the next question. In the next question, we have to find the size of cos squared of 50 degrees. Remember how I said everything needs to relate to 40 degrees? If you think about it, if you take 50 degrees, right, you only have to add 40 degrees extra to get 90 degrees. And you know that when we are speaking about angles that add up to 90 degrees, okay, we're going to have cofunctions. So it means that we can actually change this, okay, to the cofunction of cos of 50 degrees. So we have cos squared 50 degrees. And to make this more understandable, I'm going to rewrite it like this: cos of 50 degrees all squared. Okay, it's not usually like that, but I just want you to see what's going on there. So we're going to change the cos of 50 degrees. The cofunction for cos of 50 degrees, we would just change it like this. You'd say cos of 90 degrees minus what angle gives you 50 degrees? That would be 90 degrees minus 40 degrees. So here's the thing about that. The reason I knew I had to use this one is because we have an angle that is less than 90 degrees. So you have to use the 90 minus theta. If you had an angle that was greater than 90 degrees, okay, but that didn't pass, of course, 180, then you'd use the 90 plus theta. So that's how I knew I had to say 90 minus something. Okay, so now that we have this, if you change this to its cofunction, that would be positive sine of 40 degrees, okay, to stay positive. So that is equal to sine 40 degrees, and that is squared. Now we know what sine 40 degrees is. We saw that in the beginning. That is p. So that means that this is actually just p all squared, which is of course just equal to p squared. And that's our answer for that one. Okay, moving on to the next one. Okay, so now we're on 5.1.3 and we have cos of negative 80 degrees. So the angle is negative. When your angle is negative, what should you do? You can add 360 degrees to that. So I'm not even going to just add it and change the number. Look at what we can just do. This is cos 360 degrees minus 80 degrees. Just like you would reduce cos 360 minus theta, this will be reduced to positive cos theta, since this is in cos quadrant, is the same way this would also be reduced to positive cos 80 degrees. Okay, so remember how I said that all the angles that you have, you should always relate it to 40 degrees because our reference angle is 40 degrees. So how do we relate 80 degrees to 40 degrees? Well, 80 degrees is double of 40, so it means that they're using double angles here. So we can change this to cos of 2 times 40 degrees. And then just change it to one of the double angle formulas that would help you find your answer. I would rather change it to one that has a sine of 40 degrees or sine theta. So I would change it into this one. Remember, cos of 2a can be equal to 1 minus 2 sine squared of a. Okay, and I'll change it to that because I already know what sine a is. So that means this is equal to 1 minus 2 sine squared of 40 degrees. And so this is equal to 1 minus 2. Now I know what sine of 40 degrees is. It's p. And that needs to be squared. So that is just 1 minus 2p squared. And that's your answer in that question. Okay, so that is it for our trig diagram. Then we move on to 5.2. Okay, so now we're on 5.2 and it says given tan x times 1 minus cos squared x plus cos squared x is equal to, and it's equal to this. We have to prove the above identity. Okay, so with trigonometric identities, you have two hand sides that you're really looking at, right? You have to either work with the left or the right hand side. So when you look at this identity, which hand side do you think you can actually simplify further? That would be the left hand side. Because you see, we have things like tan, you have squared, cos squared, and cos squared. These are things that can actually be expanded to something else. So we're going to work with those ones. Okay. With that being said, I'm going to go ahead and start off by just saying my left-hand side is equal to, just so that at the end, I don't really need to say right-hand side equals left-hand side. Okay, so I'm just going to rewrite the left-hand side first. Okay, so now that we have this, you see we're trying to get the left-hand side to look like the right-hand side. The first thing I see is that the right-hand side has a denominator of cos x. So that's they probably got that because of this tan x. So let's go ahead and expand the tan x. So that is going to be, tan x is sine x over cos x. But the thing is that this is one term on its own. You see that in this expression, you have 1 and 2 terms. So I can just write this as sine x times 1 minus cos squared x. I won't change that yet because I'm not really sure what to do with it yet. And then say over cos x. Okay, so now that we have that, we're going to go to that and say plus, and we have cos squared x. Okay. Now at this point, we have cos x and we want to keep that denominator. So why don't we just try to make the denominators the same and make this one also have a denominator of cos x. But there's one thing I see here. I don't really want this to become cos cubed x, okay? Because there's nothing like that here on our right hand side. So what we can do is, I also noticed something here. You see this looks like a result of grouping, right? You must have grouped things together. And the only way you could have gotten this by grouping is if you had 4 terms. So I see that here we don't have 4 terms. Even if I distribute that, right? Even if that denominator wasn't there, if I had to start from here and distribute, we would have had 3 terms, right? Because you see tan x times 1 is just tan x, and then tan x times that would be, negative tan x cos squared x, and then you have that. So you'd have had 3 terms. So I noticed that we would have had 3 terms here, but here clearly we had 4 terms. So we need to change something so that it can have, we can have 4 terms. So instead of leaving this as cos x, we can go ahead and change it to its identity. The identity for cos x is 1 minus sine squared x. And I don't have to think about putting a comma because we have a plus here. So the plus is not really going to change anything. Okay, so we can do that. And then let's just put that over 1. And now we can focus on trying to make the denominators the same. Okay, so this is already a cos x. We need to make that denominator the same. So you can multiply the numerator and the denominator by cos x. So we're going to have this. This is sine x times 1 minus cos squared x, and then over cos x. And then here, you see that we have two terms and we have one term. When you have two terms and one term, you can actually rewrite it like this. So I'll put the cos x first, and I'm saying it's been multiplied by 1 minus sine squared x, and then all over cos x. Okay, now that the denominators are the same, we can finally now put them together. So that is equal to, and we're going to say, so we have sine x, and then 1 minus cos squared x, and plus cos x, 1 minus sine squared x, and this goes all over cos x. Okay, so here's the thing. Right now, you see those two brackets, they're not the same. So we can't even use any taking out a common factor here. So since they're not even working out like this in the way that they are, there's no use of leaving them like that. We need it to look like this. Okay, and you see that you have 4 terms here. So why don't we just, right now we have 2 terms on the numerator. Why don't we just expand this? And then we'll group it differently since it's already not working out in this order that it is in. Okay, grade 12, sometimes this is a trial and error. You just have to try again and just make sure never to try the same thing over and over. If you keep using the same method over and over again and it's not working, then, it's still not going to work. Okay, so sine x times 1, that's sine x. And then sine x times negative cos squared x is negative sine x cos squared x. Then here we get positive cos x, and then when that multiplies you get negative cos x sine squared x. Okay, so we have 4 terms now. That's a good thing, like they have 4 terms as well. We knew that when we had them like this, they didn't work out. They didn't really look like that. So I'm going to group them differently now. All I have to do is just change the way it was grouped. At first, these two were grouped together clearly. That's why they look like that. So instead, I'm just going to change that. How about we just group this with the last one? Because I see that they do have like terms or really common factors. They have common factors. So I'm going to group those two together. I'll say, let's go ahead and say sine x, and then put that minus cos x sine squared x. And then here, I don't want to put this one in front because it has a negative. And I see that that doesn't really happen here. You see, they both start with a positive number, okay, or positive value. So I'm going to start with this one. Okay, so we say plus cos x, and then we have the minus sine x, and then cos squared x, all over cos x. Okay, so you see, it's really just constantly looking at the expression you have and comparing it to this, okay, and trying to see what we should do next. If you just work through it by just simplifying, most of the time it doesn't always work out. Okay, so here's the groups that we're now creating. We're going to group these two together and these two together. Okay, so you're going to take out a common factor in each. The common factor in these two terms would be sine x. So sine x is common, and then open a bracket. What is left? Well, sine x divided by sine x is 1, and this divided by sine x, you see you have a squared there. One of it would cancel. You just be left with negative cos x, and then the remaining sine x. Okay, so that's done. Then here, what is common? Well, we have a cos. So let's take out positive cos x, and then what's left, we're going to have 1. And then what's left there, we'll have negative sine x and cos x. Okay, and that goes all over cos x. Okay, this actually looks good because do you notice that these are the exact same thing? Okay, so we can actually say these brackets are exactly the same. So we're really taking these brackets out as a common factor. So the bracket comes out as a common factor. And so we're going to have the 1 minus, let me just stick to one name of it. Well, here, you see that it's called sine x cos x. So let's just stick with that. So 1 minus sine x cos x, because cos x, sine x, the same thing. And then open bracket, we have what's left in this term. Okay, since we're taking out the bracket as a common factor in these two terms, we now have two terms in the numerator. So what's left in the first term? You just have the sine x when you take out the bracket as a common factor. And what's left in the second term when you take out the bracket as a common factor? You're left with the cos x. So it's positive cos x left. Okay, so that looks good. All over cos x. Now, if you look at the identity, you see it's exactly the same thing. It's just obviously those ones are switched around. So sine x plus cos x, 1 minus sine x cos x over cos x. And that's what we have as well. It's just switched around. So it's finally equal to the right-hand side. And we've proven the identity. Okay, so that's 5.2.1. And we move on to 5.2.2. So we're on 5.2.2 and it says, for which values of x in the interval where x is an element of negative 180 all the way to 180 degrees will the identity be undefined? Well, to make an identity undefined or an expression to be undefined, if the denominator is equal to 0, so regardless of whatever the numerator is, as long as the denominator is equal to 0, the expression will be undefined. So let's go ahead and look at what the denominator of our expression was all through. You see that the only denominator we had was cos x. So if that is equal to 0, then our expression will be undefined. So that's the equation that we have to find the solution to, okay, for that interval, of course. So we're looking at cos of x being equal to 0. Okay, so I posted a video on 2 ways to find the general solution of a trigonometric equation. You can go ahead and check that video out. Okay, the link is in the description so that you can follow along with the quick method that I'm going to use here. So I'm going to go ahead and just find the reference angle, and we find that by taking cos over. So that's shift cos of the value we have there. Now, if you say shift cos of 0, you're going to get 90 degrees. Okay, so with the way I showed you the quick method to solve for x, all you're going to say is x is equal to positive or negative 90 degrees. And then plus k of 360 degrees, where k is an element of integers. And now we're just going to find the values of x within this interval. So we can separate it, of course. You can say x is finally equal to, you have either positive 90 degrees plus k 360 degrees, or x is equal to negative 90 degrees plus k of 360 degrees. And we don't have to say that again. We already said it once. Now, if you want to make your angle positive, that's fine. You can go ahead and make it positive. When an angle is negative, you add 360 degrees to make it positive. So x is equal to 360 minus 90 gives you 270 degrees plus k 360 degrees. So this is the general solution so long. We need to find specific solutions for this interval. So how we're going to find that is you can use a number line. I just feel like it's neater to use a number line. So I'm going to start with the first one where x is equal to 90 degrees plus, and in place of k, we'll put our integer value. Then we have 360 degrees. So using a number line just to have a bit of structure here, you can try substituting 0. If you substitute 0 into here, you see that you're going to get 90 degrees. Okay, now check, look at your range, the range of answers you're supposed to accept. Numbers that are greater than negative 180 but less than 180, right? So it means that that does work out. We get 90 degrees when we substitute 0. That is a solution. It is within our domain of the restriction that they asked us to stick with. Okay, let's go ahead and try another integer value. You can choose to go to the right or the left. Let's just go to the left. So let's try negative 1. You can only substitute integer values. When you substitute negative 1, let's see what we get. We get negative 270 degrees. Okay, so negative 270 degrees, is that within range? No, okay, it's a bit too far. So negative 180, it has to be greater than negative 180, but less than 180. So this is not going to work. As you can see, you can just put an X here. We will not go further here since this doesn't work. And let's try 1, which is clearly not going to work. If you try 1, you see, you're just going to have where 360 gets added to 90, which is 450. It's too big. It's way out of range, so we're not even going to try 1. So the only solution we get for this one is 90 degrees. Okay, hold on to that. Then we're going to try this 1. Okay, again, I'm using a number line. If we substitute 0, you know that that's going to multiply. You're just going to have 270. 270 is too high. It's way out of range. So that's not going to work. Our 270 degrees does not work. Okay, we can try negative numbers. Let's try -1, because you see, if you go positive, you're just going to make your angle way too big, and it's just not going to be within the answers that you're looking for. So let's try -1. If you substitute -1, you get -90 degrees, which is good. So we get -90 degrees, which works out. Okay, so that is within range. It is greater than -180, but less than 180. Okay, so that works. And then since -1 worked, you can try -2 just to see if it works. Probably not going to, but you see, it's way too far. So -2 doesn't work. We don't have to try anything else. So the only solutions for x within that interval is where x is equal to positive 90 degrees or where x is equal to negative 90 degrees. And that's just your answer. Okay, so that would just be another way to find it. Okay, so that is it for that question. And we move on to 5.3. Okay, so we have 5.3, and 5.3 says, given the expression sine 150 plus cos squared x minus 1 over 2. We have 5.3.1 says, without using a calculator, simplify the expression given above to a single trigonometric term in terms of cos 2x. So that seems like the only challenge they're now putting in this expression, where you have to simplify it in terms of cos 2x. So cos 2x has to be in your answer, the simplified answer for this. Okay, let's go ahead and just rewrite this here. Okay, so first thing we can do here is, well, we have sine 150. And sine 150 simplifies to, you can go ahead and simplify it using your reduction. It will simplify to sine of 30 degrees. Then we have plus cos squared x minus 1 all over 2. Okay, what else can we simplify further? Well, the thing is, you have to try and include cos 2x. So the only thing with the variable right now is this. But I see this 1 as a distraction. So you see that we have cos squared x minus 1. Which identity does that remind you of? Do you remember that the identity for sine squared x is equal to 1 minus cos squared x? And of course, we get this from this identity, right? When you say this is equal to 1. So if you make sine squared x the subject and you take cos squared x over, that's how we get that. Okay, so the thing about this right now is that this is cos squared x minus 1, not 1 minus cos squared x. So it's just switched around. So what we can do is put it in this format, right? By putting the 1 first, but the 1 is negative. So we still have sine 30, which simplifies to a half because it's a special angle. Then instead of putting the cos squared, I'll put the minus 1 first, then say plus cos squared x. Now they're in the same order. The 1 is first and then the cos is second. So over 2. Then what we can do to get it to look like that is notice that here your 1 is negative, here it's positive. Here your cos squared x is positive, here it's negative. So it means there's just a common factor of -1 here, and you just have to take that out. So I'm going to take that negative out as a common factor in these two terms. And what we're left with is, now that the negative is out, you have a positive 1. And here you're going to have a negative cos squared x. Okay, and that goes all over to, now that we have that, 1 minus cos squared x is equal to sine squared x. Okay, so I'm just trying to simplify it in a way that I don't have any numbers that may be a distraction. So that is sine squared x. Okay, so that looks more simple. But now we need to remember that we need to simplify this in a way that it is in terms of cos 2x. Well, for us to include cos 2x, you're going to have to think about what cos 2x is equal to. See, cos 2x is equal to various things. It's a double angle, and so you have your double angle formulas in your formula sheet. So it's equal to these three things. So this is the identities for cos 2x, right? That's what cos 2x is equal to. But you see that here, the variable that we have is sine squared x. So you're going to have to choose one that has sine squared x. So that means you can either choose this one or this one. And honestly, this one looks easier to use because it's just cos squared x minus sine squared x. Okay, so at this point, I'm starting to see that this is not working out. And the reason why is because I didn't consider that we have a half here. See, if we have a half here, we have to find a way to actually simplify that half. And the best way to simplify it is by taking something that has 2 in it. So it has sine squared, but it should have 2 because at some point you're going to divide both sides by 2. So you will have a half. So let's rethink that. Instead of using what we used there, I'm going to just use that. Okay, 1 minus 2 sine squared x. Okay, so this is what we're going for now. So with this, I'm going to try and make sine squared x the subject. So we can take negative 2 sine squared x over, and that would become positive 2 sine squared x. And then you see we still have a 1 here, and we can take the cos 2x over. So it's minus cos 2x. Okay, trying to make sine squared x the subject. So you need to get rid of the 2. So divide both sides by 2, and we need that 2. That 2 is going to be very helpful. So sine squared x is equal to 1 minus cos 2x over 2. Okay, so that's going to be very helpful. So now what we have is a half minus, and we're going to subtract by that. So we're subtracting by, on this, we're going to have 1 minus cos 2x over 2. And then remember, everything is being divided by 2. So let me actually put that divided by 2 in blue. So we have over 2. Okay, so let's work with that numerator quickly. So because we are dividing by 2, what I'm going to just write this at is a half minus, and we're subtracting by, I'll let this minus affect the numerator. So what I'm going to do here is 1 minus cos 2x and then over 2, right? And I'm going to say we're just dividing by 2. Since we have fractions here, let's just call it 2 over 1 so we can tip and times in the next line. So we'll have a half, and when you distribute this negative, it becomes, well, let's just put it together since the denominators are the same and we're subtracting, right? Let's just put it together. So the common denominator is now 2, and we have on the numerator 1, then a minus, then you see what happens. You have 1 minus cos 2x, which if you distribute, you're going to get minus 1 and then plus cos 2x. And there you see we actually got rid of that 1. Okay, and of course we're still dividing by the 2, but now you can change that. Since you're dividing by a fraction, you tip and times. So you tip the fraction, swap the numerator and denominator, and times, change the division to a multiplication. Okay, so now we have, this is equal to, well, we're going to have here cos 2x, and so it's cos 2x over 2, and we're multiplying by 1 over 2. So numerator times numerator, denominator times denominator. So that's going to give you cos 2x over 4. That's what that actually simplifies to. So that expression in terms of cos 2x is just cos 2x over 4. Okay, moving on to the next question, 5.3.2. Okay, question 5.3.2 says, hence determine the general solution for the same thing we had here, right? And that is now being equated, or it's equal to 1 over 25. Okay, since we already solved for this, we now know it's cos 2x over 4. We're just going to say that this therefore means that we're actually working with this equation, cos 2x over 4 being equal to 1 over 25. Okay, so I have to solve for x here, or find the general solution. So not specific solutions, we're not really just doing that, we're just general solution. So with this, I will go ahead and cross multiply since we have fractions and an equal to sign. So that's going to be 25 cos 2x is equal to 4 times 1 is just 4. We're going to go ahead and just divide both sides by 25. Okay, so that's cos 2x is equal to 4 over 25. Okay, so at this point now you can go ahead and use the method that you want to use based on that video that I made on general solutions, the two methods you can use. I'm going to use the quick method. So first going to find the reference angle. The reference angle we find by taking cos over. So that's shift cos of 4 over 25. And this is what we get. Now, the thing about this is because you have 2x here, eventually when you're solving for x, you're going to have to divide by 2. So don't round off yet. So I'm going to leave it as 80.7931 and just show them that I haven't rounded off yet. Then to solve for this, I know that my solution for the reference angle, which is 2x, I'll just say that 2x is equal to, and actually let me just put it here in the middle first. So I'm saying 2x is finally going to be equal to positive or negative of whatever my reference angle is, which is 80.7931. And it keeps going. Then I have to tell them plus k of the amount of degrees that it takes for a cos function to repeat itself, which is 360 degrees. Then I can go ahead and say where k is an element of integers. And now we can go into solving for the general solution. So I like using this method because it's much quicker and it still gets you to the exact same answer. Again, you can watch this video to find out how to work through that, okay? I compare the standard method to this method and show you why this one just is much more simple to use. So we're going to have 2x is either equal to positive of that angle, so 80.7931, keeps going, plus k of 360 degrees, or 2x is equal to the negative of that, so negative 80 degrees, 0.7931, and that keeps going, plus k of 360 degrees. Then remember this angle is negative, so to make it positive, you can go ahead and add 360 degrees. And once you do this, you'll see that it looks exactly like the solutions you would have gotten if you dealt with it using the method where you have to use the reduction, okay? So I'm going to add 360 degrees to that angle, and no problem, I can still get it back if I need it. So when you're adding 360 degrees to this on the calculator, you see here when you add 360 degrees, it makes this sum to be 360 minus 80 degrees, right? 0.7931. So how you can get that answer is simply just on your calculator, you'd press AC, then just say 360 degrees. So I have to say equal to first. 360 degrees minus your answer. So which gives you that, as you can see. So we're just going to say that 2x, our other solution is 2x is equal to 279.2068, and that keeps going, okay? So you will see that you get the exact same solution if you use the other method. Now we just need to solve for x. Here, to solve for x, you need to divide both sides by 2 to get rid of the 2 there. So divide both sides by 2. Don't forget to divide that by 2 as well. So x would be equal to, and now just to get that answer back, you can just go ahead and say shift and cos of 4 over 25 because I just don't want to round off yet. I'm taking that, right? That's this 80 points, that, and I'm going to divide it by 2. So you see that it gives us 40 points, and now I can round off to 2 decimal places because this is the final answer. So 40 points, you see, if we round the 6 up, it adds a 1 to the 9, but the 9 will become a 10 and add a 1 to the 3. So you have that 4 degrees. Then we'll have plus. If you say k 360 degrees divided by 2, you're going to get k of 180 degrees. Okay, so that's our first solution. Second solution, you need to get that back. So you can just get it back by saying your 360 degrees minus this 80 point to that. But you know you got that by saying shift cos of 4 over 25. So you can just do that. That is back again. Now that you have that answer, you can say is equal to, and then just say divide by 2, because you need to solve for x by dividing both sides by 2. So divide by 2, and so it means that x is equal to 139 point, and it's just going to be 6 or 60 degrees. We can leave it like that. And then we're going to go ahead and say plus k of 180 degrees because that also divides by 2 as well. Let me leave it as 60. Okay, so 60 here, just add a 0, and here I'll just leave it as 40 as well, so 40. Okay, so those would be our general solutions, of course, where k is an element of integers, but we already have that though. So that is the answer for 5.3.2. That's the last question in question 5. And then we move on to question 6. Okay, so we're on question 6, and question 6 says, in the diagram, the graphs of f of x is equal to cos of x plus a and g of x is equal to sine 2x are drawn for the interval where x is an element of negative 180 to 180. Okay, so the graphs intersect at n here, at n, and p, okay, p and q. So p and q, those are the points of intersection of the graphs. So you see that they include the x values, right? Just not the y values for that, okay? Because the k value is really the same thing. They have the same y value. And so we have p is also turning point of both graphs. Okay. So let's actually just try to figure out what kind of graphs, which is which, and what's actually going on with the graphs. First of all, you see that this is f, right? Cos of x plus a. Now, even if they didn't label it, you can already see that with this one, it has not been the period, right, has not been tampered with. They didn't change the period, meaning it should behave like a normal cos graph. It's just been shifted in some way, either to the left or to the right. So if you look at the intervals that we have, right, 0, we have 180 degrees. The cos graph, right, if you're going from 0 degrees to 360 degrees, it should look like this. So because of that, you should know that the one that is wider, more spread out, is going to be your cos graph, because that one, the period has not been tampered with. This one, the period has, yes, because it's sine 2x, so it would be more narrow. That kind of graph would be more narrow. So you can see that that's the sine graph and that's the cos graph. Okay, so the first question is, write down the period of f. So the period of the cos graph. Like I said, the period was not tampered with. It's still x. You don't have a 2x or a half x or anything like that. It's just x. It's just been shifted only. So the period is the normal period of a cos graph. A cos graph completes a cycle every 360 degrees. So the period is just 360 degrees. Moving on to the next question. The next question is, write down the amplitude of g. Okay. So amplitude of g, we can actually look at the amplitude of g by just looking at the equation. The amplitude is going to be the absolute value of whatever your coefficient of that function is. So in front of sine 2x, there's an invisible 1. I say absolute value because sometimes it can be negative, but you don't have to really consider that. You just have to consider that number there. So the amplitude would be 1. That's what it is. So the amplitude is really just the height from the midline, okay, from the middle to the highest point of the graph. And we can even see that in the sine graph. Yes, that is 1. From the middle to the highest point is 1. So that's our amplitude. Okay, so we're just going to tell them it is 1. Moving on to the next question. Then question 6.3 says, write down the value of a. Okay, so the value of a. So now they want to know how that graph is being shifted. Let's just establish something quickly. You see, if the graph was shifted to the left, I want you to know that by that x, right, instead of having a minus, you're going to have a plus. So x plus whatever a is, right? Or x plus whatever that number will be. And if it was moving to the right, it should say x minus whatever that number is. So in that case, negative whatever your number is would be a. And in this case, positive of whatever that number is would be your a. Okay, so let's look at that. How was that graph shifted? What we can do is look at the points that they gave us. We know that this is a cos graph, and you need to remember what a normal cos graph looks like. A normal cos graph, like I already drew before, it looks like this. So till 360 degrees, right? Meaning at 0 degrees, originally the y value is supposed to be 1. So now why don't we just find out where the y value is 1 in our cos graph now? Do you see that your y value is 1 at 45 degrees? This is what this means. So let me highlight that graph. If that y value is 1, and the original one is supposed to actually look like this, where the y value is 1 like that, it means that if this was the original, but now it looks like that, you moved it in which direction? You moved it to the right. By how much degrees? By 45 degrees. Because now you have 45 degrees and 1. It's supposed to be 0 degrees and 1. Okay, so that's actually what that is. So it's moving to the right by 45 degrees. It was moved, shifted to the right by 45 degrees. So it means that here, what we should have, if it moves to the right, you have a minus, right? So it's x minus the 45 degrees. I can erase those now. And so that would mean that the value of a is negative 45 degrees. Okay, so that is the value of a. A is equal to negative 45 degrees. Okay, moving on to the next question. 6.4 says, calculate the value of k, the y coordinates of n and q without the use of a calculator. Okay, so it's for 2 marks. If you use a calculator, they'll probably only give you 1 mark for your answer. So without the use of a calculator, let's look at that. So you see k appears here and here. It's always easier to work with it where it is positive, okay, or where the angle is positive, because it'll just be easier to work with. And it's really especially because from here, right, this is within the range of 0 to 180 degrees, or let me rather say 0 to 360 degrees. It's within that range. So it's easier to find angles like that rather than angles that are going like, behind those ones. So with this one, you're going to have to just consider what the graph looked like. You can either look at the sine graph or the cos graph. Honestly, in this case, I feel like because this is such a weird angle they gave 165 degrees, because I know this one moved, the cos graph moved 45 degrees to the right, I think I would rather use the cos graph because it has a 165 degrees, which has a 45 degrees in there. So it's easier to work with. So let's look at this, right? And just to figure out what k is, you have to think about, because we're not using a calculator, you have to think about what the original graph looked like. Again, the original graph actually looked like this. It was shifted 45 degrees to the right. So let's think about what the y value for 165 degrees would have been. But think about it like this. This graph originally looked like this. It's going to go 45 degrees like that. So if you have 165 degrees and k, you see this value of k, the original function would have had this same value at 45 degrees before this. Okay, since your graph was shifted 45 degrees to the right, if you want to find out where that value of k is, you're going to have to take 165 and go 45 degrees before this, and then you find that. So if we go 45 degrees behind, we end up here and we'll find out what that is. Okay, so 165 minus 45, because we're going 45 degrees backwards, that would be 120. So you have to now think about what the original function would have had at 120 degrees. In other words, what is cos 120 degrees? But remember, they said don't use a calculator. So let's work that out. So now we know to find that, we just need to find cos 120 degrees. Let's go ahead and reduce, because that's all we have to do now to actually find that without using a calculator. So to reduce that, you see that 120 degrees would lie in sine quadrant because it's greater than 90 but less than 180. So you have to use this reduction for it. So that is cos of 180 degrees minus what gives you 120? That's cos 180 minus 60 degrees. And so if you reduce that, because it's not in cos's quadrant but in sine's quadrant, it's going to get reduced to negative cos of 60 degrees. Okay, so now that we have negative cos of 60 degrees, use special angles to find cos 60. So it's going to be negative, this is the value of k, of course, right? K is equal to this. Okay, so with cos 60, you can use a calculator, but I'm also going to just show you the method that I use to calculate this. I don't use the circle. I use something called the OHA rule. So the OHA rule, the O is for opposite, hypotenuse, adjacent. Okay, then we're going to put 30 degrees, 60 degrees, and 45 degrees. I'm just including this so that you can have a way to find special angles. So I'll tell you the ones that you need to watch out for and the ones that you can actually just use the calculator and to still give you the same solution here. So OHA rule, you say OHA 30, 60, 45. Then you say 1, 2, 3, square root the biggest number. Then 3, 2, 1, square root the biggest number in this row. And then 1, 2, 1, square root the biggest number. Okay, so if you're looking for cos of 60 degrees, you know that cos speaks about adjacent over hypotenuse. So we'll go to the 60 degrees and we're going to take the adjacent, which is 1, over the hypotenuse, which is 2. So you see cos of 60 degrees is equal to 1 over 2. Okay, so that's just how to use the OHA rule if you didn't want to use the triangles or the circle. So the ones you should watch out for, you should watch out for this one. The one with 45 degrees, okay? Cos of 45 degrees and sine of 45 degrees. Because those ones, they become 1 over square root of 2, okay? Which if you use the calculator, they would have known you used it because the calculator will rationalize the denominator and make your answer root 2 over 2. So they would know that you used the calculator, okay? So I have seen one case where if you use the calculator, you would have thought you were wrong in your solution. It was a 2 and 3D trigonometry question. I forgot what year that was though. So that's the value of k. K is equal to negative a half. You could have used the calculator for this one. It's not a problem. It wouldn't really affect it. But the OHA rule is good to know as a backup, okay? Okay, that is 6.4. K is equal to negative a half. Moving on to the next question. Okay, so 6.5 we have calculate the value of x if g of x plus 60 degrees is equal to f of x plus 60 degrees and x is an element of negative 45 to 0. So this is one of those questions that is not as complicated as it seems. It's just because they decided to add these. You see, the thing is, they are moving, true. They're moving, it's plus 60, right, by the x, meaning it's moving to the left, okay? If you have plus 60 or plus by the x, it's moving to the left. If it's minus, it's moving to the right. So the thing about it is they're both moving by the exact same thing, okay? So all we have to do is, since they're moving by the exact same thing and they're equal, why don't we just find out where g of x is already, first of all, equal to f of x? Then we can consider the shift. So let's look for where that happens. So where is, now I have to erase that. Where is g of x equal to f of x? Well, it happens at 3 places. It happens here, here, and here, right? So those are the places that they are equal. But now we have to consider the shift. So they said plus 60 degrees, meaning it's moving to what direction? It's 60 degrees to the left because it has plus. So it's taking both graphs and shifting them to the left. So to make this easy, I'm going to highlight both graphs and then we will move them to the left by 60 degrees. Okay, so here are our graphs. We know all the places they intersect. We're going to move them to the left by 60 degrees. Okay, so let's take a spot that we can actually just focus on and actually nicely move it by 60 degrees. Focus on P, because if you are by P and you're moving 60 degrees to the left, you just have to say the angle at P is 45 degrees. Just go 60 degrees to the left of 45 degrees. So that's 45 degrees minus 60 degrees. So if I pick that, those two graphs only, okay, it's just going to try and select both. So I'm just going to have to show you what's going on. If they both move, right, for each place 60 degrees to the left, this at 45 degrees will not happen here anymore. It will happen 60 degrees to the left, which will land at negative 15 degrees. Okay, 45 minus 60 is negative 15. So it means that they will intersect again at negative 15. Let's keep that in mind. That's where they're going. That's where P is going to be. And the place they intersected before was here at negative 75. They're going to move 60 degrees to the left. So they're going to intersect at, you say, negative 75 minus 60 degrees, which gives us negative 135. So here, that's where they will intersect. That's a new place they would intersect. I just have to do it like this because I can't really move the graphs right now. I thought I was going to be able to, but I can't. So they would move and both of them would intersect here at negative 135 degrees. And then the other point of intersection that we had was this one at 165 degrees. If this moves 60 degrees to the left, you're going to intersect again at 105 degrees. So 165 minus 60, right? 105 is somewhere like here. So they will just both move and like intersect somewhere here again. Now, the question is this. You still have to answer them for this interval. We know the places they're still going to intersect after they shift, but we need to solve for x specifically between negative 45 to 0 degrees. So which of these angles where they intersect is within negative 45 to 0 degrees? That would only be the negative 15. So when they shift and then they, of course, intersect at negative 15 degrees, that's the only one that is within that domain. That's the only one there. So that's our answer, where x is equal to negative 15. We can't take that because negative 35 is way beyond that, and that is still way above that, even if it's 105. Okay, so that's our answer. X is equal to negative 15 degrees. It's really just about moving it. So you need to take a pencil, make sure you're drawing the shifts, and you can see those and you'll be able to answer it. So x is equal to negative 15 degrees. Okay, moving on to the next question. Okay, 6.6. So 6.6 says, without using a calculator, determine the number of solutions the equation square root of sine 2x is equal to sine x plus cos x has in the interval where x is an element of negative 90 to 90 degrees. Clearly show all workings. It's interesting how they don't tell you to solve just for x. They're saying determine the number of solutions. Okay, let's just keep that in mind so that we don't forget when we finish solving, to actually count the amount of solutions and tell them that. Okay, so you can see the equation that they gave is one of those ones that they keep bringing up. The grade 12s learn to see the patterns that keep coming up. That's why it's good to do recent papers, like 2022, 2023, 24. Okay, it's good to work on this type of papers so that you can see the kind of things they may decide to bring back. So when we look at this equation, yeah, it looks weird. It does look weird. And one of the reasons it looks weird is because of this part. You look at that and you kind of expect them to put some sort of identity so that you can work with it. But we know there's no identity for sine x plus cos x. It's not 1, okay? The one that gives you 1 is sine squared x plus cos squared x. That's the one that gives you 1. So it's clearly not that identity. It's not any identity, really. And this will probably lead people to think, is this a trick question? Is there something that we didn't learn? The thing is, the minute I see square root 2, I know they're trying to form something here. They're trying to form, and I see one term and another term, they're probably trying to form a compound angle. So what I'm going to do here is think about square root 2 and just think about what I can do with this number. What can it become? What kind of trig function can it become? What I mean by that is, for example, if you see a half, you can change a half to two things. You can change it to sine of 30 degrees. And you can also change it to cos of 60 degrees because they're both equal to a half. I see square root 2, and I think this type of question has shown up before. I'm not sure if it's in the November paper, it was in the June paper, but there was something like this as well. But they had like a 2. And so the minute you see 2, you're like, okay, maybe it's a half that we have to form from this. But this time they put a square root of 2. So this is where your special angles are going to come in, right? You need to know your special angles well. And again, I've shown you the OHA rule. I'm going to put down the OHA rule here, and we're going to look at which functions have square roots of 2 and try to figure out what they're trying to do here. So here's the OHA rule again. So remember, you say OHA, then you say 30, 60, 45. And you can say 1, 2, 3, 3, 2, 1, 1, 2, 1. And then square root the biggest numbers, okay, not the angles, number in the row, in each row. So that will be the 3 here, and the 2 here. So you see that we have square root of 2, and it appears by the 45 degrees. Okay, so it means that, well, it's not just square root of 2. We have to think about what we can form from this. You can only use cos, sine, or tan. I would not recommend you use tan. Tan is not going to help you here. It's just going to confuse things right now because you see patterns of sine and cos. So let's try what is cos of 45 degrees. We'll also try sine, of course. Cos of 45 degrees, cos is adjacent over hypotenuse. So by the 45 degrees, we take the adjacent, which is a 1, over hypotenuse, which is square root 2. And if you try it with sine as well, sine 45 degrees is 1 as well, the opposite, over hypotenuse, square root 2. So it's the same thing. Okay, so that's probably what they're trying to do. And that makes sense that it's working for cos and sine. So here is the thing. Because we have sine x here plus cos x, this square root 2, it's probably going to form a compound angle over here. So we need it to come here. So we can get it to this side by dividing both sides by the square root of 2. And then what we will have is sine 2x is equal to, now let's be careful how we work with this. Let's take the sine x and divide by square root 2, leaving you with sine x over root 2. And do the same with the cos, leaving you with cos x over root 2. Now, we can actually form compound angle here using these. Because root 2 is the denominator, you can actually see it like this. You actually have an invisible 1 in front of the sine x and an invisible 1 in front of the cos x, meaning we have sine 2x being equal to 1. How about we let the 1 take the denominator of root 2? So 1 over root 2, then sine x. Then plus, also do the same thing there, 1 over root 2 cos x. Okay, we're almost there. The 1 over root 2, we can change them so that we can form compound angle formula here. So because we have a sine here, I don't want to change it to sine, sine, cos, cos. How about we leave this sine here and change this one to cos? You know that 1 over root 2 can be changed to cos 45 degrees. So that's what I'm going to do there. Let me just write it in the next line. So here, I'm going to go ahead and say that becomes, well, let me put the sine first so that it's in the right order. So sine x, then the 1 over root 2 is now going to be the cos 45 degrees. And this is perfect because they're the same angle. So it's going to work perfectly for compound angle. So sine cos, then you need to have cos sine. So plus, I'll leave the cos here, cos x, and then the 1 over root 2, I will change that to the sine so that it follows the compound angle for sine. Okay, so that's sine 45 degrees. Okay, so do you see now that that looks like sine A cos B plus cos A sine B. And because it follows that rule, the same way this simplifies to sine of A plus B is the same way that on top is going to now simplify to, so we still have sine 2x here. That is now going to simplify to sine x plus 45 degrees. There we go. And that's how we get it to look like that. So the reason we know immediately that there was something to do with compound angles because of this. There's no identity for this. The minute you see a number like root 2 or root 3, you know that they have used, or even 2, right? You know that they've used special angles. So this is what we have. Okay, so let's not lose track of what we're trying to do. What we're trying to do is determine the number of solutions. So we just need to solve for x, find out how many solutions we have within this interval, of course. Okay. So this is a general solution. You just have to solve for x in this general solution. Let's go ahead. We have sine on both sides. This is one of those ones that is taught in grade 11. So the thing is that A textbook, and let me just recommend a textbook that is very, very helpful. The Kevin Smith textbook, that textbook is extremely helpful. It actually has questions like this in the grade 11 one. So if you're in matric, if you have access to that textbook, that's very helpful, the grade 11 and 12 one. So I would honestly encourage you to really self-study, because the thing about matric is that there's a lot of work. Many a times teachers don't actually finish the whole curriculum. Okay, so with this, let's actually just go ahead and solve for x. Let's not change this, because if you change this, okay, you're going to have a cos x, and then that just complicates things more. Let's go ahead and try and start solving for this. So with equations like this, right, I know that you have sine and sine. That's not a problem. We are actually just going to find the reference angle first. So this is what I'm going to do. I'm saying reference angle is equal to, right? Then I'm going to take this sine over, and it's going to become shift sine. But the thing about this is it's the inverse of sine. So what it will do to this is that it's going to cancel out this sine, and you will just be left with your angle. So now do you see why our reference angle is going to be x plus 45 degrees? Okay, so reference angle is equal to x plus 45 degrees. Now when we're solving for x, we're going to do this. When you're solving for x, you see the angle, right? The angle that you took the sine over for, right? 2x. That is what you're going to say here. That's what you're going to put as your x, right? Like when we used to say x is equal to, then we go ahead and start solving. That is your x there. So in this case, I say 2x is equal to, and then I'm going to put down my reference angle. Okay, so remember that I'm using the quick way of working this out. Remember, here is that video again, just to remind you about it. You can go ahead and look at that and work on that, because I want to make this as simple as possible. I don't want to use long methods because I want to avoid making mistakes. So what I'm going to say here is, I know that this is my reference angle, but remember that with the function sine, you're only going to use two things, okay? When you're solving for your angle, whatever it is, theta or x, you say your reference angle, then just plus k 360 degrees, or theta is equal to 180 degrees minus your reference angle, okay, plus k 360 degrees, where k is an element of integers. That's what you're going to do. So that's what we're going to do here. Our reference angle is the x plus 45 degrees. So I'll take it like that. X plus 45 degrees. And then I'm saying plus k of 360 degrees. K 360 degrees. Or, hey, my second solution, remember, this is like your x that you're working with, okay? So it's 2x is equal to, and then we're going to take 180 degrees and subtract by our reference angle. Our reference angle has two terms, so you need to use brackets to protect it. So x plus 45 degrees, then plus k 360 degrees, where k is an element of integers, okay? So that was just how to do that. You can check out that video to work on that. I just use that method instead. Now we're just solving. Okay, so the first one, you see that you can take x over. If you take x over, it becomes a negative x. 2x minus x is just x. Okay, then we have 45 degrees plus k 360 degrees. That's all we have there. Okay, then, or in this case, this one is just going to take longer, but it's fine. We're going to have 2x is equal to 180 degrees. Let's go ahead and distribute. So you have minus x, and distribute minus 45 degrees, then plus k of 360 degrees. Okay, 2x is equal to, so 180 degrees minus 45 degrees gives you 135 degrees, and you still have that minus x, which we can take over. So we still have the 2x here, and we're taking the negative x over and becomes a positive x. Okay, and then we have plus k of 360 degrees. Okay, then that becomes a 3x is equal to 135 degrees, that's k, of 360 degrees. So you see here, to solve for x, you need to divide both sides of the equation by 3. So this would mean that x is equal to, what's the 135 divided by? It's actually, I think it's 45. 135 divided by 3. Yeah, 45. Okay, so we have 45 degrees. And you must also divide the K360 by 3, which is K120 degrees. Okay, so there, these are our two solutions. But we're not done because they said, oh, this is such a long question. They said determine the number of solutions. So we still need to find the solutions we will have within this interval. So I've done this already in this trigonometry section, okay, where we're just substituting integer values for k. Okay, so we're starting off with this one, and we need to only accept answers that are greater than negative 90, but less than 90 degrees. So here we go. So 45 plus, and we're going to substitute k value. So again, I like to use a number line because it's just neater. So let's try 0. So you substitute 0, you see that you get 45 degrees. Does that lie within that interval? Let me actually just push this here so we can always check it. Does that lie within that interval? Yes, 45 degrees does work out for that. So 45 degrees is one of the solutions we have. I'll put a check mark on it so I know that it's our answer. Then let's go negative. Let's try negative 1. So minus 1, you get negative 315. It's way too far. Because negative 1 doesn't work, don't try negative 2. Then you can try positive 1. Okay, so I'm just trying to show you a clean method of working through it if you didn't want to like think the answers through like that. Okay, it's better to just be careful. Then if I try positive 1, it's obviously too big, so we're not even going to try that. So right now for this one, this is the only solution we have. Okay, let's go ahead and work with this one where we have x is equal to 45 degrees again, but this time k of 120 degrees. So I'm just going to change that to 120 degrees. So that's just 1, 2. Okay, so let's go ahead and try 0. Would of course work. So again, you're going to have an answer of 45 degrees. I'm not going to repeat that answer. Well, I can, it's fine. 45 degrees worked. Then let's try negative 1. If you say minus 1, you get negative 75 degrees. Does that fall within your domain that they gave you? Yes, it does. Okay, it is greater than negative 90, but less than 90. So negative 1 works, negative 75 degrees. That is a solution. Of course, if you try negative 2, it's not going to work. It's too far. You see, negative 195, negative 2 does not work. Then we can try 1. I actually did try 1. It didn't work. It's too far. Okay, it's too big. So it must be less than 90. So you see that we have, our solutions are x is equal to 45 degrees, or you don't have to repeat the 45 degrees again, or x is equal to negative 75 degrees. So our solution is, the question is, how many? Determine the number of solutions. We will have 2 solutions. So I'll just conclude. We will have 2 solutions, or there will be 2 solutions. Okay, so that is the answer to that one. Hopefully there weren't mistakes. If there are mistakes, grade 12s, please do let me know. Okay, so that is it for that question. And that is it for question 6. And we move on to the final part of trigonometry, which is question 7. Okay, so we are finally on question 7, which is the last question for trigonometry. So question 7.1 says, in the diagram, triangle ABC is drawn. We have AD is drawn such that AD is perpendicular to BC. So that is our perpendicular height for our triangle there. Okay, so they want us to use the diagram above to determine AD in terms of sine of angle B. Okay, so determine AD. Now, the good thing about this is if you're determining AB in terms of sine of angle B, you're really just working with this right angle, which is nice. So you're working with the right angle and you're trying to include sine of B, right? You're trying to solve for sine of B, make that the subject, and it should include AD. So what we can do here is, why don't we, because they already told us sine of angle B, they're already solving it for us, honestly. They're making this very simple. They told us, say sine of angle B. So sine angle B is equal to, now you know sine is opposite over hypotenuse. So just use that. This is a right angle triangle. The opposite is AD. So that's AD over the hypotenuse, which is AB. AB. That's what they want us to do. And so the question is really just, use the diagram above to determine AD in terms of sine of angle B. Okay, so now we have to just simplify by making AD the subject, because they say determine AD in terms of sine of angle B, meaning that should be part of your answer, but that's your subject. Okay, we can do that by cross multiplying. So sine of angle B as a fraction is sine of angle B over 1. Then cross multiply. 1 times AD is AD. Here, AD is already your subject. And then multiply across like that. Sine of angle B times AB is AB sine angle B. Done. And that is our answer. Okay, moving on to the next question. The next question, 7.1.2, says, hence prove that the area of triangle ABC is equal to a half times BC times AB times sine of angle B. Prove that it looks like they're using the area rule. If you look at that, because it's a half times BC, which is this side, times AB, that side, and the sine of the center angle. But they say prove though. So it has to do with, if it's only for 1 mark, there's no way they want us to use the area rule. Because if you're using the area rule, then this is it. No, there's nothing to prove. So let me think about this. Oh, okay. So I see they're really just asking us to use what we had used here. If this is a perpendicular height, AD, which is what we just found, right? How would you find the area of a triangle? You find the area of a triangle by saying area of a triangle is naturally going to be equal to a half multiplied by the base multiplied by the height. Okay, I guess this is the proof of the area rule. Okay, the one without a perpendicular height. And then we're specifically looking for the area of triangle ABC. And that is a half multiplied by, what's our base there? Our base of this triangle is BC. So multiply by BC, multiply by our perpendicular height, which was AD, which is AD. But you remember that they told us to solve for AD in terms of sine of angle B. So let's use that. Okay, I will say times AD first. Okay, then I'll substitute. So it's equal to a half. Since they use brackets, we might as well just do that as well. Half bracket BC times AD. But now we know what AD is. AD is AB sine angle B. So that's AB, right? Sine angle B. Yeah, that's really what they're saying. And there. So that's actually really the proof. We just substituted AD, okay, with what it was equal to. And we got exactly what they asked for. Okay, that is for 1 mark. Moving on to the next question. Okay, now we're on 7.2 and it says, in the diagram, points B, C, and D lie in the same horizontal plane. Okay, B, C, and D. I don't like that this is so dark, but okay. Then they tell us that ADB, that angle is equal to ACB, and they both equal to alpha. Then CDB, so angle CDB is equal to theta, and DC is equal to K, okay? It's K units. So DB is equal to BC. DB equal to BC. I'm going to mark that in red because, it's quite dark to see. Okay, the first question is for us to prove that AD is equal to AC. To prove AD equals AC. Thing is, we just have a big triangle if you look at it because it's a 3D shape, right? There's the face of it, which is the big triangle, ADC, right? This is like a triangular prism sort of shape. There's that big shape in front. Then there's this right angle here and that right angle. So I see that AD is part of the triangle ABD and AC is part of the triangle ABC. Do you see that those triangles, they both have alpha and alpha, 90 and 90, and the same angle? So it means they're congruent. So how we can prove that these two lines are equal is to prove that these two triangles are congruent. So it would mean that these two lines are equal. So I'll just, well, this is not Euclid. I don't know if I need reasons, but okay. In triangle ABD and triangle I want to name it in the same way, ABD. So ABC. Okay, so what we have there is let's start with the fact that we have a side, right, that is being shared. AB is a shared side between these two triangles, that one and that one. Okay, so AB is equal to AB. I'll just put reasons. So it's because it's a shared or common side, shared side. Then we have equal angles as well. So alpha and alpha. So ADB, angle ADB is equal to angle ACB, ACB, and they both equal to alpha. Okay, that is a given angle. We didn't find that. That was already there. What else is equal in these two triangles? Well, they both have 90 degrees. So we have 90 degrees there. So let's just go ahead and tell them that. I guess we can call it angle ABD. So ABD is equal to angle ABC. Angle ABC. And that's both equal to 90 degrees. And that is given as well because they showed us the sign of 90 degrees there. So given angle. So that would mean that these two triangles are congruent. So it means triangle ABD is, I feel like I didn't need to do this is 2 marks. I feel like I was just supposed to tell them they're congruent. So I'm wasting a lot of time here. So congruent to triangle ABC. I don't have to do this. There's no proving stuff, but maybe they still give a mark for it. I guess so. Because they did say prove. So because they're congruent, it means all their corresponding sides and angles are equal. So AD must be equal to AC now. They're both equal. Let me give it different markings. Okay, so that therefore means that, okay, I have to give the reason for them here. So they are congruent because of side, angle, angle. Okay, so it's side, I'll just say angle, angle. That's the reason. And so because they're congruent, all their corresponding sides and angles are equal, therefore AD must be equal to AC because of congruent triangles. Okay, there. So proven that those two are equal. Moving on to the next question. The next question is prove that BD is equal to K over 2 cos theta. So theta is included in this story now. So these two are equal already. They want us to find BD. BD is this line here. So find that line. I have to really just find that it's equal to that K over 2 cos theta. Okay, let's look at that. How can we find that? So I don't want to find it using this triangle. And the reason why is because if I use this triangle, it's going to be in terms of alpha. Here's in terms of theta. So clearly they didn't use that. If we try to use this triangle like this, we're only going to, I can only think about using the sine rule. And if we're using the sine rule, we have to get this. Because with the sine rule, you need the angle and the side opposite it. The angle and the side opposite it. I don't know where BC comes into the story. But BC is also the same length as BD. So, let me look at this again for a while. Okay, so I see a way to find this. What we can do is, because I noticed that there's a 2. And I was like, where's this 2 coming from? Why do we have theta? So I kept focusing on the dark triangle because it's the only one with theta, right? So because of that, I was wondering, where is this 2 coming from? And I decided the only way I can have, a cos theta safely is if I have a right angle triangle, because then I can just use trig functions on it. For example, if I was looking at alpha and I wanted to maybe include AB, I could just say something like sine of alpha is equal to, so I'll take the opposite over the hypotenuse, you see? So it's like AB over AD. See? That's how you can get a single term like that when you have a right angle triangle. So what I decided to do is, let's look at this triangle. This is an isosceles triangle, meaning we can cut it in half. And if we cut it in half, you will only be able to do so with a perpendicular bisector. So we're going to use that. That line will be perpendicular to the base, and we've cut this triangle in half. Now we're going to use it like that. Now I know we don't know what this is called. We don't know what this is. However, if you cut it in half, remember this full length was k. It means that half of it would just be a half k, which we can actually call k over 2. Okay, see, a half k is k over 2 because the half is just 1 over 2. The k is really k over 1. If you multiply, 1 times k is k, 2 times 1 is 2. So that's why it's k over 2. Okay, so I decided, since we have k over 2, you see that there, let's include this length of this, okay, that length, and let's include alpha and use that to find dB. So if you look at the sides we're using, so alpha is here, right? That's your reference angle. And then you're using this side here, which is the side that is adjacent alpha. So that's the adjacent side. And you're using this dB because they want you to solve for BD or dB, right? That is your hypotenuse. So if you're using your adjacent and your hypotenuse, you have to use the function cos, because cos is adjacent over hypotenuse. So we can just say, to find that, let's go ahead and say BD. No, now I have to say cos of theta, right? Because I'm using cos theta is equal to the adjacent over the hypotenuse. Okay, so that is going to be, my adjacent side is k over 2. So cos theta is equal to k over 2, okay, over your hypotenuse. Your hypotenuse is the dB, so over hypotenuse. So with that, I can just say over hypotenuse dB or BD. Keep calling it dB. Okay, now the over is really a divided by, or dividing. So we can simplify this further, and we just have to make BD the subject. When we're simplifying, this is a fraction. You can make this one a fraction by putting it over 1. So it means that cos theta is equal to k over 2. Then the division, and we're going to tip in times since we're dividing by a fraction. So you tip the fraction, is 1 over BD, and then you times. Okay, so that means we have cos theta being equal to k times 1 is k, 2 times BD is BD, 2BD, right? And now you just have to make that the subject. So you can make that the subject by cross multiplying. So put cos theta over 1 to make them both fractions. Then cross multiply. 1 times k is k. I'll leave that k there. And then we have cos theta times 2BD, which is 2BD cos theta. Okay. Then we need to make BD the subject. So clearly we need to divide both sides by 2 cos theta to get rid of that. So 2 cos theta. And so therefore BD is equal to k over 2 cos theta. And there we go. So this one we just had to do some construction. Just cutting that triangle in half. Okay, there we go. So that is that question. Then we move on to the last question in question 7. Okay, so now we're on the last question, 7.2.3, and it says, determine the area of triangle BCD in terms of k and a single trigonometric ratio of theta. Okay, so they wanted in terms of k first of all, and it just needs to have a single trigonometric ratio of theta. Okay, so let's go ahead and look at our triangle. They said triangle BCD, this triangle here. So how we can find the area? Okay, we can just use the area rule. Since this is what we have, they want it as a single trig ratio of theta and in terms of k. In the previous question, they asked us to find dB. So we know what dB is now. So we're going to use that. And then you can use this as your center angle. You can use theta as your center angle and then this as the other. So remember that rule works like this. If you have a triangle and you have the middle angle, you have 2 sides next to that angle, then you're going to use that area rule, half times the one side times the other side and sine of that center angle. Okay, so that's what we're going to use. So remember the one side that we have is DC C, right? Not this little thing, because this is just K over 2. We're getting the area of this entire shape. So we'll use that, the full length of K, and then that center angle, theta. Okay, so let's go ahead. We're just going to say that this is going to be equal to, so the area of triangle BCD should be equal to a half multiplied by the one side, which was DB, remember, and or BD, right, which is K over 2 cos theta. So that's the K over 2 cos theta, and then multiplied by the other side. So that was BD that we just did. So BD, and then multiply by the other side of the triangle, which is this full length, which is K, right? So multiply by K, and then the center angle, of course, which is sine theta. Okay, so that's the middle angle that we have there. So that's the whole calculation, really. So now we just have to simplify this. So to simplify this, we've got fractions. So we might as well put this as a fraction by putting it over 1. Then we're just going to multiply all through. So 1 times K sine theta would give you K squared sine theta. Then over, let me just use the space. So over, and then 2 times cos theta times 1 is just going to give you 4 cos theta. Okay, then I see here that sine theta and cos theta here as a fraction, and we know that that can become tan theta. So our answer is really just K squared over 4 tan theta. And that is the area of triangle BCD in terms of K and as a single trig ratio of theta. Okay, so that is it for this paper. And I'm still working on the Euclidean geometry. Well, let me just be honest, I've not been working on it because I've been really busy at work. So this weekend, I think I'll be able to get it done. So I'll just go ahead and record it, edit it, and I'll do my best to post it so that you guys can use it to practice before Monday in case there are any grade 12s that are writing on Monday. It will also help a lot if you guys can comment in the comment section the dates that you are writing. You don't have to write the schools, you just have to write the date that you're going to write so that I can also just kind of have a deadline. Okay, I hope you guys enjoyed this video and I will see you guys in the future videos. Bye for now. Hey grade 12s, and welcome to the trigonometry section of the November 2024 paper 2 exam. And we're on question 5. Question 5 says, in the diagram, line OP is given with P being -3 and -4, and then we're given the size of KOP, well, that angle, which is equal to A. And the first question is to determine, without using a calculator, the value of cos A. Okay, so this is our typical trig diagram that we have. So we're going to draw a vertical line to the x-axis, and remember it is perpendicular to that x-axis. So where these go, remember that -3 is your x value, -4 is your y value. So where we're going to put them down is like this. So from the center to this side, you see that is an x value we're measuring. So that's going to be the x value, -3. And then if we were looking at the y value from the origin down, okay, so that, you see that? So that is the -4 that we have. Okay, so that is -4. So the only thing missing is your hypotenuse or your radius. And we can go ahead and find that using Pythagoras. So it's the radius, the longest side. So r squared is equal to, and we'll take one shorter side squared plus the other shorter side squared. Okay, so what does that give us? That's going to be 9, that's going to be 16, so 25. So r squared equals 25. And then square root both sides. You know, it's positive and negative, but a radius is a length, so it's always going to be positive. So r is equal to 5 units. And now we know what r is. We can find cos A. Okay, so since this is 5 units, then remember that cos in saw katoa, cos is the ka part. So that is adjacent over hypotenuse. So the adjacent side to that angle, that reference angle, is the negative 3 over the hypotenuse, which is 5. So cos A, therefore, cos A is equal to negative 3 over 5. And there we go. That is 2 marks. Moving on to the next question. The next question, 5.1.2, says we need to find the value of cos 2A. Okay, so cos 2A is a double angle. Just expand it to another double angle. It'll be easier to expand it to something that has just cos because you already have cos. So I'm going to go ahead and expand that to 2 cos squared A minus 1. Okay, because it'll be easier to work with. So 2, and then what is cos A? It's negative 3 over 5. So that's times negative 3 over 5. But this is squared, so you need to square that. Squared minus 1. And you can punch that into the calculator and actually just get your answer. That's fine. And we get an answer of negative 7 over 25. Okay, it's best to just save time. And anyways, the mark allocation is just 2 marks. So done with that. Moving on to the next question. The next question, 5.1.3, says we are given sine A minus B, right? We need to find sine A minus B if it is further given that sine B is 4 over 5 and that B is greater than 90 degrees but less than 360. Okay, so just expand this. You see that this is a compound angle. It has a compound angle expansion. So we just need to expand that. Now, you know it's going to include things like sine A, cos B, and things like that. So you just need to get the second diagram, the diagram that has B as the angle. Okay, so it's just what we didn't do there, we're going to do here. Okay, so we'll just draw down a Cartesian plane first. And you can label your angles. And do you see what they tell us here? Sine B is equal to 4 over 5. 4 over 5 is a positive number. So they're telling us the sine is positive first of all. So we're going to mark all the quadrants where we see sine being positive. So you know that this is where everything is positive. This is where sine is positive. This is tan and cos. So all the quadrants where sine is positive is in the first and the second quadrant. And then you see what they tell us about B, that B is greater than 90 degrees but less than 360 degrees. You're going to mark all the columns that are greater than 90 but less than 360. So greater than 90, this is everything greater than 90 and less than 360. So that is the second, the third, and the fourth. Okay, and then the column or the quadrant with the most ticks would be your quadrant, which is of course the second quadrant. So that is what we are going to have. Okay, we just have that in the second quadrant and that's it. Okay, so our terminal arm goes here and we have B. Okay, so B is always measure from 0 degrees, which is here in the first quadrant. So like that, and that is our B. Okay, so all we're really just doing is completing this diagram. Okay, so first of all, you see that they told us that sine B is equal to 4 over 5. So this also means something else. 4, remember, as saw Katoa, right? Opposite over hypotenuse. So 4 is the opposite side, H is the hypotenuse side. So we're going to drop a vertical line down to the x-axis, and this is perpendicular. And then this is our 4 over here, and the hypotenuse is 5. So it means that we need to find the adjacent side, which we can see is an x value. So we're going to find this by saying x squared. Now, because it's a shorter side, you're going to take the longest side, the hypotenuse squared, minus the other shorter side squared. And so that's x squared is equal to, okay, so 25, that's going to be 25, and that's minus 16. 25 minus 16 is 9. And then we're going to square root both hand sides, make that positive or negative. So this is x squared is equal to, now, do you see the part of the x-axis we are on? This is the negative part of the x-axis, so you need to make this negative. So x is equal to negative 3. And this is our diagram completed. Okay, so now we have everything to complete this sine A minus B. Okay, so this is sine A minus B. And then we expand this to sine A cos B minus cos A sine B. Okay, I like to remember it as sine cos sine. Okay, and I see that as the sine song, and then it's still A B A B. Okay, so now that we have this, we can actually get all of these values because both diagrams are complete. So what is sine A? Okay, so in our diagram, sine A, because this is our diagram, is opposite over hypotenuse. So this is for the angle A. It's going to be the opposite side, -4 over 5. So we know the value of sine A is -4 over 5. And this is being multiplied by cos B. And we already know what cos B here is. Well, we can find it. Cos is adjacent over hypotenuse. So that's -3 over 5. So put that down as well. -3 over 5 minus cos A. So cos A is in the A diagram. So cos, that is adjacent over hypotenuse, -3 over 5, which we already had, but okay, minus -3 over 5, which has been multiplied by sine B, okay? So they already told us that was 4 over 5, but you can also look at it here, opposite over hypotenuse, which is 4 over 5. And this is all we have. So you just have to multiply it and get your answer. Okay, just for explanation, because sometimes, you have variables here. Just remember, when you're looking at these, right, multiplication joins terms together. You always simplify expressions term by term. So this makes one term on its own. Then you have a minus sign, which is separating the term. And then this will be your second term, okay? So if you deal with, you see the first term, you just deal with that. And then the second term, you deal with that. And then it's perfectly fine, okay? So it's equal to, this is going to give you positive 12 over 25. And then here, instead of just putting the minus immediately, what I'll look at is the fact that there's a negative bracket, a negative times a positive, okay? So it's just that negative times the positive times the negative. So do you see that this will end up becoming a positive value? So just multiply. 3 times 4 is 12 as well. So that's going to be positive 12 over 25. Okay, so we didn't need a calculator for that. And it's good to deal with these because sometimes they have variables and you can't use a calculator. So you need to know how to just work it out on your own. It's equal to, and that is 24 over 25. And that is our answer. Okay, so they are being very lenient. And we'll just see if the rest of the trig section is like that. Okay, but that is the answer to that question. And that is it for 5.1 questions. And we move on to 5.2. We are now on 5.2, and 5.2 says, if cos of alpha is equal to P, express the following in terms of P. Okay, so this is what we've been given. So do you see there is an angle being repeated here? Okay, alpha over 2 minus 45 degrees is being repeated. So what they tell us is that cos alpha is equal to P. So we're really just taking this and somehow relating it to P. Okay, so I'm just going to rewrite this first and then let's get simplifying. Okay, so this is what we have. So with this, you should already be able to spot, you see the cos, same angle, sine, same angle, okay? This comes from double angles. So you see the double angle sine 2a, and how this angle is equal to, I need more space, so sine 2a is equal to 2 sine a cos a. Do you see a repetition of that sine a cos a here? Okay, sine a cos a is happening here. Okay, that's like sine a cos a because it's the same angle. Okay, so what we can actually do here is make sine a cos a the subject so that we can see what is equal to and we can replace that here. So here the 2 would be what needs to leave. So if you divide both sides by 2 to get rid of the 2, you see now that sine a cos a is going to be equal to sine 2a over 2. So we just need to understand what is our a, okay? So the sine a cos a is the same thing here. You could have just switched these around, okay, to make it easier for yourself. If you put this one in front of this one. So let's put the cos this side and the sine this side. This is still sine a cos a as well. It's in that same form. So it's going to simplify to the same way this simplified to sine 2a. It's going to simplify to sine 2 and then our angle. So this represents our a here. It's what's being repeated. Sine that angle, cos that angle. Okay, sine a cos a. Same thing. So sine 2 times our a is that alpha over 2 minus 45 degrees. Okay, so with that, right, we're allowed to write the 2 and then times that, because the 2 is part of the angle. It's the coefficient of that angle. Okay, it stands for double. Okay, so it's going to multiply into the angle. So we have alpha over 2 and then minus 45 degrees. Okay, so this is what we have. And we can just, okay, so don't forget the 2. That's the one thing. Okay, so this one, right, that's the sine 2a over 2. So this one itself has an over 2. But remember that the main expression also has a denominator of 2. Okay, so this just stands for this part. That's our sine 2a over 2. But we still have a divided by 2. So let's not forget that. Divided by 2. Okay, we can actually sort that out. With divided by 2, you can actually just use it as a number. This is one term, and we can just say divided by 2, and then we'll tip in times. Okay, so this is equal to, we'll sort that division out. Let's simplify here. The 2 is going to multiply into the 2 terms in that angle. So sine, and we have 2 times this. Remember, this 2 cannot divide with this. This is a number 2, like a unit value of 2. This is the coefficient of an angle. They're not the same thing, so they can't cancel. And then so we have here alpha. So that's going to be alpha. And then minus, when it multiplies there, it's minus 90 degrees. Okay, and then it's still over 2 divided by 2. But here's the thing with dividing by 2. 2 as a whole number is 2 over 1. When you need to divide, what you're going to do is keep the first fraction the same, and we're going to do something called tip and times. So you're going to tip this number, and so you swap the numerator and denominator, and you change your division to a multiplication. So tip and times. Okay, so this is what we have right now. If we multiply, this times 1 stays exactly the same. So it's sine alpha minus 90 degrees, and 2 times 2 is 4. So over 4. Okay, so this is what we have. And now we have to simplify this. Okay, you see 90 degrees, you see an angle. So this screams cofunctions. But the thing about this cofunction is you see that the angle is negative. Remember how alpha represents an acute angle. So for example, like 30 degrees, right? So you have like 30 degrees minus 90 degrees, for example. And that would give you negative 60 degrees. So ultimately, your entire angle here is still negative. What do you do when your angle is negative? You add 360 degrees, okay, so that it becomes positive and we can actually simplify it better. So this is equal to, when we have sine, and when you add 360 degrees to negative 90, you get to 70 degrees plus alpha, still over 4, okay, is equal to, now the thing is, it's still cofunctions. We're still looking at it as cofunctions. However, you need to make it look like cofunctions. So we're going to separate the 90 degrees from this. So we're going to rewrite this as sine 90 degrees plus what gives you to 70. That's plus 180 degrees. And then we still have our positive alpha, which was positive from the beginning, as you saw here. Okay, all over 4. Let's not forget that 4. And then what we're going to do here is we're going to group these two together so that this reads as sine 90 degrees plus an angle. Just the same way we have sine 90 degrees plus a. And you know that the cofunction for this is cos a, positive cos a, right? So the same way we are looking at this a, right, as this 180 degrees plus alpha is the same way we're going to simplify this to cos of our a. And our a is the 180 degrees plus alpha. So that's 180 degrees plus alpha all over 4. Okay, so that's what we have then. That's how you simplify that. It's 90 plus that angle. That's our a. Okay, so now that we have this, we're just going to have to simplify or reduce that. Cos 180 plus alpha. As you can see, that is not cos's quadrant. That is tan's quadrant. So that simplifies to negative cos alpha. See, we have a cos alpha now. So what did they tell us about cos alpha in the beginning? They told us that cos alpha is equal to p. So wherever we see cos alpha, we're going to replace it with p. So this means that this is finally equal to negative p over 4. And that is our answer. Okay, so that is the answer to that question, 5.2. And that is the end of question 5. Moving on to question 6. Okay, we're on question 6, and question 6 says 6.1, given the identity cos x minus y is equal to cos x cos y plus sin x sin y, you need to use the compound angle identity given above. Okay, use this compound angle identity to derive a formula for cos x plus y. Okay, as you can see in our grade 12s, they keep bringing this proof question in. Okay, so they never really ask you to prove the entire compound angle formula, but they ask you to prove part of it, and this is a part of it. So how we're working with this is they're saying using this idea, okay, using the fact that cos of x minus y, in other words, cos of a first angle minus a second angle, gives you cos of that first angle, cos of the second angle, okay, plus, so wherever you see that minus, you're going to change it to a plus. Okay, so plus that gives you sine of, again, the first angle, and then sine of the second angle. Okay, so that's really what they are saying. And I'm saying first angle and second angle for a reason, because you're going to have to think about it like that for you to be able to derive a formula for cos x plus y. So this is what they want you to find. Find the expansion of this using this idea. Okay, so let's rewrite what we have to expand. This is cos x plus y. Okay, so look at this. If we have to use this idea on this, what is the one thing that is a challenge right now? That would be, so you just compare them, right? You see that you have cos x, okay? That's great. But then you have a minus here and you have a plus. This needs to be a minus. So how can we change that positive to a minus? It's not just by changing it, because then you're going to change the value of it. What we're going to do is rewrite that positive. So cos x, and how do you rewrite a positive so that it includes a negative? Well, you know that a negative multiplied by a negative gives you a positive. So we're going to change that to minus, and we're changing this positive y to negative y. See, we're not changing the value, we're just changing the way it looks, because if you multiply back, it's still positive y. Okay, so now that it is in this format, cos of your first angle, okay, minus your second angle. Now that it's in that format, we're going to expand just like they did here. So we're going to expand this just like they did. Okay, so they said cos of their first angle, and we're going to also put that down. Cos of our first angle is x as well. So we're going to say cos x. And then they said cos of their second angle, which is y. But our second angle is negative y, as you can see. So we're saying cos negative y. And then because they had the minus in the middle, they changed it to a plus. We will do the same. Then sine of the first angle. So sine of our first angle is still x. Okay, so sine x. And then sine of the second angle, our second angle is negative y. Okay, and once you've got this part, all you have to do is simplify now. Okay, so we're saying this is equal to cos x, and then we have cos negative y. So when your angle is negative, what do? You add 360 degrees to it. You don't have to show them this. As long as you simplify it correctly, then it's fine. Same thing here, that angle is negative, add 360 degrees to it. So when you have cos 360 degrees minus y, what does that simplify to? Well, that is in cos quadrant, so it's going to stay positive. So that stays positive cos y. Continue, plus sine x. And when you have sine 360 degrees minus y, what does that simplify to? Well, that is in cos's quadrant, and sine is negative in cos's quadrant, so that becomes negative sine y. Okay, and all we have to do is simplify. You see, this is our first term and our second term. These two will multiply and become negative. So our answer is cos x, cos y. Those multiply and become negative. Sine x, sine y. And there is the expansion. Okay, so we do know that cos x plus y is really equal to this. And that is our answer. Okay, moving on to the next question. 6.1.2 says, hence or otherwise show that all of this is equal to tan x plus y. Okay, just take it as it is, simplify as far as you can, and you'll just see things simplify and cancel. Okay, if there's things that we need to really think about deeply, we will do so. Okay, so as you can see, the left hand side is what we are working with here, because that's actually where we have to simplify things. So we just rewrite the left hand side first. Okay, so this is what we have. Let's get simplifying. Okay, so first we have cofunctions, cos 90 degrees minus x, and that gives you positive sine x. Okay, and then we have cos y, which is just cos y. Then we have sine negative y. You know now that that simplifies to negative sine y. Okay, so it is really just a negative. You can change it from there. It's fine already because it's like it multiplies. Okay, negative sine y. And then cos 180 degrees plus x, that is not in cos's quadrant. That's in tan's quadrant. So it gets reduced to negative. Okay, so it's being multiplied by negative cos x. Okay, and then we'll multiply that. And this goes all over, and we have cos x and then 360 degrees plus y. Okay, so this is the one that they like to trick you with a lot. When the angle, okay, remember that y represents an acute angle. So right now you have 360 degrees plus an acute angle. So the angle ultimately is going to be over 360 degrees. You need it to be within 0 to 360 degrees. So you would subtract 360 degrees from it. If you minus 360 degrees from that, that just gives you cos y. Simple. Done, okay? Because that was a plus. And then we have sine 360 degrees minus x. You can see that one is a reduction. 360 degrees minus x, that lies in the fourth quadrant. And sine is negative in that quadrant. So that simplifies to negative sine x. And then we still have times sine y. Okay, I don't want to be doing the whole thing like positive. Oh, okay, then it becomes negative sign because we're still going to multiply at the end of the day. So it's fine. You can just change it from there. So it's equal to, and we're just going to simplify. Okay, so on the numerator, we just have sine x, cos y, and negative times negative is positive. Okay, so that becomes positive sine y cos x. You just have to remember that this is separating, okay, those two terms. Over, and on the denominator you see that we have cos x cos y minus sin x sin y. Okay, they're being very lenient here. Okay, so you see with the numerator using cofunctions, that simplifies to sin x plus y. Okay, all over, and using that denominator, and that's probably why they said hence or otherwise. Okay, so you see how that was that cofunction, okay, cos x plus y. That simplifies to cos x plus y, because that is the cos rule, the cos song, really. And now because they are both exactly the same, it's like having sine a over cos a. You know that that's going to be equal to tan a. So like that, that's going to be equal to tan x plus y, okay, which is equal to the right hand side. So we can just tell them it is equal to the right hand side. So at the end of the day, the left hand side really is equal to the right hand side. Okay, moving on to the next question. The next question is 6.2. Let me just make space. The next question, 6.2, says, given f of x is equal to, and we have the square root of 6 sine squared x. Okay. So we have this. Don't get afraid because you see square root, it's fine. They just say solve for x in the interval where x is an element of 0 degrees to 360 degrees. Very simple interval, okay? If f of x is equal to 2. Okay, so let's just make f of x equal to 2. That's all we have to do. So I'm already going to straight away say f of x is equal to 2, so I'll replace that there. 2 is equal to, and we have the square root of 6 sine squared x minus 11 cos 90 degrees plus x plus 7. Okay, so yeah, it looks like it's going to become a trinomial. So let's just simplify like the way we're supposed to. First of all, we've got a square root. It's not nice to work with square roots because then you can't really get into what is inside there. So we're going to get rid of the square root by squaring both sides. So square that and square that. So that gives you 4 is equal to, and now the root is gone. And you now have, and we're just going to take advantage and start simplifying. So 6 sine squared x minus 11. Now you see a cofunction here. What does that simplify to? So remember, that's the cos 90 plus. That's the one that becomes negative. So that becomes negative sine x, okay, and then plus 7. Simplify again. We can take that 4 over. So we have a 0 is equal to 6 sine squared x. That becomes positive 11 sine x. And then 7 minus 4 gives you, because the 4 comes over, gives you positive 3. And yes, we have a trinomial. You see that this is sine squared x and then sine x and then a constant. Just like you could actually, if you wanted to factorize this properly without getting too intimidated by the sine x, you can replace sine x with k. So you're just going to call it 6k squared. You don't have to tell them this. You can just do it on the side. So plus 11k plus 3 and then factorize this. Okay, grade 12s, I have a video on factorization. You can use that. You can also use the factor method. That's also fine. But I'm just going to use the cross method here because I think it's quicker. So factors of 6k squared, that's going to be, I'll separate it, 3k times 2k, okay? And then factors of 3 is the prime number, so it's really simple. You can put it as 3 and 1, but you need to check if it's going to work out. So like this as 3 and 1, that's going to be 3k, and that's going to be 6k. I don't see that ever creating 11. So I'm going to rewrite that 3 as 1 and 3. Okay, and it's all positive throughout, so all factors are positive. Now let's test out if it really does give us the middle coefficient. So 3k times 3 is 9k, and 2k times 1 is positive 2k, which is indeed 11k. So that works out perfectly. So you see how this is going to simplify to 3k plus 1 multiplied by k plus 3. The same way with the sine, it's going to simplify to, so we have 0 is equal to, and we have 3. Now remember, our k is our sine x. So that's 3 times sine x plus 1, and then multiply by sine x plus 3. And those are your factors. Done. Okay, so just do that on the side. And so since we have this, now we can finally just solve for x. So something multiplied by something equals 0 is either the first thing is equal to 0 or the second thing is equal to 0. So let's simplify. If you take the 1 over, we just have 3 sine x is equal to negative 1, and then you will divide both sides by 3, which leaves you with sine x being equal to negative 1 over 3. Okay, here we would have sine x is equal to negative 3. Okay, so what did they want us to do again? They want us to solve for x, okay, within that interval. So let's solve for x. You need to first find the general solution before you can find specific solutions. So let's find the general solution of this. So you can use that method where you use the quadrants and you ask yourself, where is sine negative? And then you use those reductions. You can do that. Or you can use this method that I'm using, which I showed in this video. So you can watch that video to learn this method if it confuses you. But you can also use your method. You will get to the same answer. So first of all, I'm going to find the reference angle. Okay, and I'll just do that by taking sine over, or really just the second function of sine. So shift sine negative 1 over 3, and I still use it as negative. That's why I use this method, because I don't have to consider whether something is negative or positive. Okay, so the reference angle is just negative 19.47 degrees, and I'll just round it off right now because this is not saying 2x or anything like that. I don't have to divide or multiply at the end of the day, so I'll round off already. Okay, so negative 19.47 degrees, and we just need to find the general solution of this. What you're first going to do is say x is equal to, and you're going to put down your reference angle, which is negative 19.47 degrees, and then you say plus k of 360 degrees, because the sine graph repeats itself every 360 degrees, okay? Or the next x value that we have is where we have 180 degrees minus our reference angle. Our reference angle is negative 19 point that. So negative times negative becomes positive. So it's positive 19.47 degrees plus k 360 degrees, where k is an element of integers. Okay, we're going to find the specific solutions now. Now, so that my answer looks like yours, what I'm going to do here is I'm going to add 360 degrees because my angle is just negative. Now, I can just make it look positive. So if you work through this using the method where you ask yourself which quadrants is sine negative in, this is probably the answer you're going to get. When I add 360 degrees to that, okay, so if you take this and you add 360 degrees, you see that you're going to get, and this probably looks like your answer now. So 340.53 degrees. Okay, that's our answer there. Or here, x is equal to, sorry, I keep forgetting, plus k 360 degrees. Okay, or, and then we have, I don't have to rewrite that again, is equal to, and then just add that angle, right? Add that to 180 degrees. So, okay, we can just say 180 minus that angle. And that becomes, as you can see, 199.47 degrees. Okay, plus k 360 degrees. And now they want us to specifically find answers within this interval, which is a very simple interval. Okay, so we don't have to go too far. So k is an element of integers, meaning you can only substitute integer values for k. So you can try integer values like number line values. Now there are values that are obviously not going to work here. Okay, you should already be able to spot them so that you can save more time. So I'm already going to start by saying the only integer value that is going to work is 0. Okay, 0 will work, everything else will not work. Okay, -1 will not work, +1 will not work, 2 obviously, and -2 will not work. You can test it out for yourself because it's just going to make it too big, and then it's not going to be within 0 degrees to 360 degrees. It must be greater than 0 but less than 360. Okay, so if you substitute 0 into the first one, that's just going to become 0 and your x value will stay exactly that. Okay, so x will be equal to 340.53 degrees, or x would be equal to, if you substitute 0, that becomes 0, so 119.47 degrees. You can try substituting other values and you'll see that it's not going to work. It's going to either make it negative or over 360. Okay, so those are our answers, and those are the specific solution to this. Okay, grade 12s, while editing, I noticed that I completely neglected this. Now, remember how this is supposed to actually be 2, sine x is equal to -3, and then we'll divide both sides by 2. And then this is sine x equals to -3/2. The thing about this is this equation doesn't really have any solutions, and it's because of the way the sine graph goes. You see, with the sine graph, it's a graph where it's just sine of x, right? You can see that the coefficient of sine x here is 1, meaning the highest point that the sine graph is going to reach is 1. It's going to go like that and like that. The lowest point it will reach is -1. Because of that, a number like -3/2 will not lie on this graph. This number is really -1.5. Okay, it's not going to lie on this. Since the lowest it can go is -1, it will not go anything beyond -1. And so because of that, this does not have any solutions here. So x has no solutions. Okay, so that is what I should have said over there. So moving on to the next question. Okay, the next question, 6.3, says, consider the function g of x is equal to 4 minus 8 sine squared x over 3. Okay, so it looks like the expansion for it. So 6.3.1 says, calculate the maximum value of g. Okay, so all you have to look at this like is, this is a single trig function. Okay, you know how we have like sine x, cos x. Okay, it's a single trig function. It just looks funny right now. We just have to simplify it further, and then we'll be able to see that. So step 1, let's simplify that. Okay, so let's take that and simplify it. So g of x is equal to 4 minus 8 sine squared x over 3. Do you see that the numerator has 2 terms? And in those 2 terms, we have a common factor. So you can take out your common factor. The common factor is 4. So we take 4 out as a common factor. And what you have left in the first term? You have 1. And then what you have left in the next term? It's minus 2 sine squared x. Okay, do you see the double angle now? 1 minus 2 sine squared x, okay, is a double angle expansion for cos 2a. Okay, that's 1 minus 2 sine squared a. So that's going to change to, we say this is equal to 4 multiplied by, and then that becomes cos 2x. It's really just multiplied, so like that, over 3. So what we just have here is 4 over 3 cos 2x. That's what g of x is, okay? And all they want us to find is the maximum value. So you can do that by simply seeing what this looks like. Okay, it's a very simple trig function. It's not shifted up or down or left or right or anything like that. If it's left or right, it's still fine. But it's not shifted up or down. So however this looks, okay, we can see that they have tampered with the period of it, okay? So it's not going to go like to 360 like that, okay? It's going to be more narrow. But regardless of that, what's happening is you have a coefficient of 4 over 3, okay? An amplitude of 4 over 3. So it means that the highest it will go is 4 over 3, and the lowest it will go is negative 4 over 3. And then it'll do that, like the normal cos graph that it is. So what is the maximum value? The maximum value, or the highest value, is 4 over 3. And that will be our answer. So we'll just tell them the maximum value is 4 over 3. And that is it for that question. Okay, moving on to 6.3.2, which says, okay, 1 mark. I already see it shouldn't be complicated. Let's hope. They say write down the smallest possible value of x for which g will have a maximum value in the interval this. Okay, translation. They're really just saying, what is the smallest possible value of x, okay, where this g will have a maximum value. We know where g has a maximum value. We know the maximum value of g. We don't know where yet. Okay, so the maximum is here at 4 over 3. This will not happen at one place. It will happen in multiple places. You see here where I just drew a single cos graph, okay? So one cycle of the cos graph. You see that it appears here. Here's a maximum. Here's another maximum, okay? So just in a single cycle, we're seeing this happening in 2 places. But we need to actually draw it according to, yeah, the interval that they give us, okay? So think about it like this. You don't have to draw the full graph like to make it pretty or anything like that. You just have to understand how that graph looks. So you know that the normal cos graph, right? Normal cos graph would have just, if it was going from 0 to 360 degrees, right? Normal cos graph would have just done this, like I drew this, like down and then back up, done. Okay, at 360 degrees, and it will be done. But the thing about this cos graph is that its period has been tampered with. We put a 2 in front of x, meaning the graph, right? It used to complete one cycle in 360 degrees. But because there's a 2 here, how you find out the amount of degrees it completes a cycle in is by saying the old period divided by the number that we have there. See how they're making you find the period without actually asking you for it, which is 180 degrees, okay? So now you know that this new graph is going to complete this. You see how that looks up, down, up. It's going to complete that within 180 degrees. Okay, so in a graph where we're drawing from 0 to 360 degrees, what is that going to look like? It means that from 0 to 180 degrees, you're going to have a cos graph. So you're going to have one cos graph. Again, from 180 degrees to 360 degrees, because that is a length of 180 degrees again, you're going to have another cos graph like that. So that's basically what's going to happen. Okay, and again, yes, the maximum is 4 over 3, minimum is negative 4 over 3. That's what's going to happen. So the question is, we need to find the smallest possible value of x. I don't even see a reason for drawing all of this. It's really unnecessary. The answer is very simple. It's actually something that you'll just see straight away. Okay, the smallest possible value for x where you're going to have that maximum. Where does this maximum appear? Here. Okay, first place it appears at what degrees? 0 degrees. You can already see that's the smallest. Okay, the other places it appears is going to be here at 180 degrees. That's at maximum again. And lastly at 360 degrees. Okay, now I'm thinking about it again. The 0, it looks like 0, but if you look at what they're saying here, let's look at this. Yeah, almost caught me there. So you see, you need to interpret this the way they spoke about it. They said x is an element of 0 degrees to 360 degrees, but they put a round bracket here. Round bracket means not including 0 degrees. So they're really saying x is greater than 0 degrees, but not equal to 0 degrees. So 0 degrees itself is not part of our interval. Okay? And then it goes to 360. So it's less than. Now look at the bracket they use here, a square bracket. So less than or equal to 360 degrees. So within this interval, because 0 degrees as an actual exact point, right? As an actual x value is not included here. The smallest one after 0 would be what? The smallest value that we have after 0. It would be 180 degrees. So the smallest x value, as they asked for, the smallest possible x value for which g will have a maximum value in this interval would be 180 degrees. Okay, so x is equal to 180 degrees. It would have been 0, but 0 is not specifically included. Values greater than 0 are included, yes, but not 0 degrees exactly. Okay, so that is the answer to that question. Moving on to the next question. Okay, question 7. Question 7 says, in the diagram below, the graph g of x is equal to tan x is drawn for the interval where x is going from negative 180 to positive 180 degrees. Okay, we need to write down the equation of the asymptote of f in the interval where x is going from 0 to 180 degrees. Okay, so the asymptote is showing right there. Okay, so from 0 to 180 degrees, what is the asymptote we have there? We have an asymptote of 90 degrees. Remember, an asymptote, okay, because it's a vertical line, just like, the asymptotes you have in hyperbolas, the vertical ones, they start with x is equal to. So the equation of this asymptote would be x is equal to, and it passes 90 degrees, okay, within that interval. So x is equal to 90 degrees is our answer there. Moving on to 7.2. 7.2 says, write down the values of x in the interval where we have x going from negative 180 to 0 degrees, for which f of x is less than or equal to 0. Okay, so from negative 180 to 0 within this interval, where is this graph less than or equal to 0? Where does it have a y value less than or equal to 0? So here it has y values greater than 0. Over here, do you see that all of these have y values less than 0? So less than or equal to, so we also need to include 0 here as well. So do you see that this goes from negative 90 degrees all the way to 0 degrees? Okay, so how we can write that is, it's not going to be exactly at negative 90 degrees because we have an asymptote there, but it is going to be at exactly 0 as well. So it's all of these values greater than negative 90, but less than or equal to 0. So we can, there's two ways of writing it. You can write it in set builder and interval notation. So x is greater than negative 90 degrees, but less than or equal to 0 degrees. Okay, like that. Or you can write it like this. You can say that x is an element of, and it's going from negative 90 degrees all the way to 0 degrees. But now the type of brackets you use are important. Because it's just less than negative 90 but not equal to negative 90, you use a round bracket. And here, because it is equal to 0, you use a square bracket. And that would be our answer. Okay, so two different ways of writing it. Moving on to the next question. Okay, the next question says, given g of x is equal to cos 2x plus 1. Okay, it's a simple looking graph, 2x then plus 1. So it just shifts up. The first question is, write the period of the g. Okay, we spoke about period in the 7.2 questions. The period is where you see that this graph's angles have been tampered with, okay? Has it been made wider or more narrow? And we can see that by the coefficient of x. So you see there's a 2 there. You're just going to take the old period of the graph. The cos graph, the old period is 360 degrees because the cos graph repeats every 360 degrees. And then you just divide it by the number that you see there, 2. So the period of this graph is 180 degrees. Okay, so that is our answer, 180 degrees. Okay, 7.2.3 says, on the grid given in the answer book, draw the graph of g of x. Okay, so draw the graph of g for the interval. Okay, clearly show the intercepts with the axes as well as the coordinates of the turning points. Okay, so let's just remember to also just put those points down, intercepts and turning points. Okay, so I don't really know what the answer book looked like, but we can draw it on here since this goes from negative 180 to 180, and they're probably going to just give us a situation where we have to compare these graphs. So do something when both of them are there. Okay, so let's go ahead and draw this graph. So it's this graph, we've already drawn it, kind of. Okay, you see how that went? That was that cos 2x. Just this one had a coefficient of 4/3. So you can already see how this one would be drawn. Okay, so this goes from negative 180 to 180, right? Because the period is now 180 degrees, the cos graph is going to complete one cycle every 180 degrees. So within 180 degrees, you will see one cycle. But you just need to remember here, you see what is in front of cos? It's an invisible one. So here, the coefficient, okay, or the coefficient of cos, yes, is 1, meaning the highest point is 1, the lowest point would be negative 1. So your graph is just going to look like this, okay? At 1, it's going to start like the way the cos graph goes, like that, and it's just going to complete a cycle. But we just need to make sure to draw it decently. It doesn't have to be perfect, but at least, readable. Okay, so let's just see where things would happen. First of all, naturally, you would have had at 0 degrees, your cos graph will start at 1. Okay, then at 90 degrees, it was supposed to be at 0. But because that period has been changed, okay, it's now 180 degrees, everything gets divided by 2. Okay, so it would have ended at 360, but it's ending at 180 now. So what's going to happen is what should have happened at 90, you see where this should have been at 0 at 90, it's not going to happen at 90 anymore. It's going to happen at half of 90, which is 45 degrees, which is going to be here. Okay, so that's what we'll put down there. So really the easy way to do this is just cut everything, okay, because it's really just like the normal cos graph. Just everything is going to happen at half the degrees it was supposed to happen. So cut everything in half. This is 45 degrees. This is 90. And then cut that also in half. Okay. So this was supposed to be 270's angle, right? Like this one was supposed to be 360's. Okay, but it divided by 2 and now it's 180. So 270 divided by 2, that's going to be your 135. Okay, so that's really all we can just do there. Okay, so it goes from 1, 0, then at 90 degrees, it's going to be at negative 1, and then at 3, 135 is going to be at 0, and then at 180 degrees, it's going to go back at 1. And that's going to be our graph. We'll just draw it out. Same thing on this side, okay? So you're going to have your negative 45 degrees here. You have your negative 90 and your negative 135 degrees. Okay, so then we'll just put everything down as well. So it's just like a zigzag pattern, okay? 1, 0, negative 1, 0, 1. Same thing. So 1, 0, negative 1, 0, and 1. Okay, back there at 1. And now we're just going to draw it and make sure that it's curved and all. And there we go, okay? So that's the cos 2x part. Remember that the graph of g is cos 2x plus 1. Okay, so imagining what that looks like, you would actually just use a pencil. Then you know that this is going to shift up by 1 unit because we have plus 1 at the end. So that is a y value shift up really. Okay, it's moving up by 1 unit. So instead of the maximum being 1, it's now going to be 2. And the minimum is not going to be negative 1, it's going to be 0. So from this, it just shifts 1 unit up and looks like that. Okay, So let's just point out the things they told us to point out. They said clearly show the intercept with the axes and then the turning points. Okay, so let's tackle all the intercepts. So the intercepts that we're going to have, we know where it intersects the x-axis here. Okay, so we're going to tell them this happens at the x value of 90 degrees and the y value of 0. This one happens, that x-intercept is going to be at negative 90 degrees and y value of 0. And then the y-intercept, you see that the y-intercept, okay, where that maximum was going to be, is now at 0 degrees and 2. So we've pointed that out. Okay, I just changed it to red so we can see it better. And then the turning point, which we've kind of already pointed out. Okay, this is a turning point, another turning point, another turning point. The only ones you can actually just mention are the 180s and the negative 180. Also just point that out because it will be a turning point as well. So negative 180 degrees and the y value here would be 2. Okay, that's the highest, 2. And then again here, that's positive 180 degrees and 2. And there is our graph, okay? Not really missing anything. That is it. Okay, so that is it for that question. Moving on to the next question. The next question and the last question for question 7 says, use the graphs to determine the general solution of 2 cos. Okay, here's the thing. They will never introduce a brand new graph. That is one thing. Okay, they're not going to just at last minute just bring a new graph. So it probably has something to do with this. Okay, but let's just take that down and see how we can simplify that further. So we have 2 cos cubed x minus sine x is equal to 0. Okay, so looking at this straight away, I'm already seeing that first of all, it's very good that we have single angles here, okay? It's not saying 2x or, 3x or anything like that. It's saying x. So it means that because you have a sine and you have a cos, we can probably create tan. Okay, so why is it important to create tan? Because above the two graphs we have is cos 2x plus 1, and we have the tan of x graph as well, like they mentioned in the beginning. F of x equals tan x. That's the graph that we have here, this tan graph. Okay, so how about we try to create tan and then the other graph will kind of like form itself, or we'll manipulate it so that we can actually get that, because it's definitely those two graphs, or one of it at least. So let's go. We have 2 cos cubed x, and then we can take that over so that we can form tan is equal to sine x. Now, you know that tan is formed by saying sine x over cos x. So we are going to have to divide both hand sides by cos. So just to form that tan, I'm trying to get that f of x graph. Okay, so this gives us tan x, and here this was cos cubed x. Okay, so divided by a cos x is going to be 2 cos squared x. Okay, this is looking good. Now, so we have tan x, we have f of x, good, but we have 2 cos squared x. That's not this graph. This is cos 2x. Okay, so let's try to manipulate this so that it can look like that. What is missing? Cos 2x. We know an identity, right? For this, that has a 2 cos squared x. It's the one 2 cos squared x minus 1. So you see the difference? To get this to be 2x, we have a minus 1. So we need it to be 2x so that it can relate to g, because that's probably what they want you to do here. So let us subtract 1 on both sides so that we can have that situation, and we can change this to cos 2x. Okay, so let's say it's equal to, and I'm going to say minus 1, minus 1. And so this now becomes cos 2x, okay? Because that is the double angle expansion really for cos 2x. Is equal to tan x, minus 1. This is actually starting to work out now. Remember how g is this, cos 2x plus 1. So what happens when you take that negative 1 over? It becomes cos 2x plus 1 is equal to tan x. There we go. That's what they're actually speaking about. So the general solution they want us to find is use the graphs to determine the general solution for this, which is this, right? The general solution for where these two graphs are equal. What are the general solutions, or really, when these two graphs are equal, what are the x values at which they are equal? And you just have to give your answer as a general solution, not specific solutions. Okay, so they're really just asking us, where is g of x equal to f of x? Okay, drawing these graphs like this would help us see the places they are equal. So where the graphs are equal is where they intersect. So where do they intersect? Okay, first point of intersection here. Yeah, I can see it's negative 135 degrees, but we won't assume, don't worry. We'll still like verify to check whether it's true or not, okay? And then here at 45 degrees, okay? That's the only place that these two graphs actually intersect, here and here. Now, because they already deliberately point out 45 degrees and negative 135 degrees from the way we constructed this, I'm just going to go ahead and test it out like that. So let's try first of all, right, where x is equal to negative 135 degrees. Does this make these two equations equal? So cos 2, and if we replace this with negative 135 degrees, okay, will it be equal to the tan of x? So tan also negative 135 degrees. If it is equal, then you know, yes, that is a point of intersection. I'm just double checking, okay? Okay, so if we say tan negative 135 is 1, then, oh yeah, that makes sense. Okay, so if you say cos 2 times negative 135, that gives you 0. Then if you say plus 1, it also gives you 1. 0 plus 1. Sorry, bracket plus 1. There we go. Okay, so it really is equal. 1 is equal to 1. So this is a point of intersection, definitely. The other point of intersection we got was at 45 degrees. You can also do this here. Now, with the 45 degrees one, I think it's relatively simple, because we know here 2 times 45 degrees is 90. Cos 90 is 0, plus 1 is 1. Tan 45 degrees is 1. So this is also going to work out. See, if you change that to 45, it gives you 1. And you know that tan 45 is 1. So x equals 45 degrees is also a solution. Okay, so you would test that out on your calculator. You wouldn't need to write it down. I just wrote it down so that we can see what's going on. But how do you represent these as a general solution? Okay, we know the answers already. It's x equals negative 135 degrees. Okay, or I guess we can leave it negative, it's fine. X equals 45 degrees. We can leave it negative because they specifically said you need to use the graphs to determine the general solution. Okay, so they know that that solution will come about because of that graph. You're going to have to add k of something. Now, depending on what your graphs look like, you'd be able to add k of whatever we're supposed to add. These two graphs, let's think about how they repeat, okay? How many degrees do they repeat in? The cos 2x plus 1, because that 2 is now there, the new period is 180 degrees, meaning this graph will repeat itself every 180 degrees. The tan x, the tan graph always repeats itself every 180 degrees. So do you see that both graphs repeat every 180 degrees? So your answer here would be x is equal to negative 135 plus k of 180 degrees. Or x is equal to 45 plus k of 180 degrees. They both repeat every 180 degrees, where k is an element of integers. And that's our answer. Okay, so that is it for that question. And we move on to 2 and 3D trigonometry in question 8. Okay, question 8 says, in the diagram, C is the foot of a vertical building. And yeah, let's just read this looking at the diagram. So C is the foot of a vertical building and D is the top of the same building. Okay, so the height of the building, CD, is 16 meters. Okay, so that's CD's length. Then they tell us that two observers are standing 19 meters apart at points A and B. Okay, where A, B, and C lie in the same horizontal plane. So this is like the flat ground. These two are there, okay? C is on the same ground as them. It's just further away from them. And then we have a painter is working at the top, E. The painter's over here on the building. The angle of elevation of D from A is 46.85 degrees. Okay, the angle of elevation is over there like that. And then we have DEB is 122 degrees and BCA, okay, so DBE 122 there. And then BCA is just 105. Okay, so they've given us everything. And they want us to first of all calculate the length of AC, which is the distance between the observer A and the foot of the building. Okay, they just want you to find AC, that's all. So how would we find AC? So you're going to look at the triangles that can help you find AC. You see that you have the bottom triangle, but do you have enough information here to help you? Not really. Okay, this is not a 90-degree angle. All you have is an angle and the side opposite it. That's it. So now we can look at the second triangle, okay, where we have AC being a part of, which is this one. Okay, so this triangle, you have an angle. It's a 90-degree triangle. Great. And you have the length of CD. So that is more than enough information. We can use trig functions to find this. So how we use trig functions is you first identify the acute angle. The acute angle is this. So everything is going to be in reference to the acute angle. The side we're looking for is AC. Do you see that that is adjacent? Okay, is the adjacent side. So that acute angle is next to it. And then you're going to look at what side we have. Okay, so the side you are given to find versus the side you have. So the side we have is right opposite, okay, which is CD. So you have an opposite and an adjacent side. What function are you going to use? You're going to use tan. So I'm going to say tan of the angle that we have, 46.85 degrees, is equal to, and you know that tan is TOA, so opposite over adjacent. So that's going to be that 16 over the adjacent side, which is what we're looking for, AC. Okay, now we're just going to make AC the subject of the formula. That's all. Let's make AC the subject. So you can do so by cross multiplying both sides by AC. Okay, if you cross multiply, that just gives you AC tan 46 point. We don't have to do it like this. We can actually just transpose things, but it's fine. Okay, and 1 times 16, which is 16. And then to get AC on its own, you have to get rid of this tan 46.85. So you do that by dividing both sides by that angle. And once you do that, AC is simply just going to be equal to 16 over tan 46.85 degrees. And you would just have to find that answer. Okay, so let's just find that. And you see here, if we were trying to round off to 2 decimals, that 8 rounds up and becomes 1. That 9 becomes a 1, adds to the next 9, and that will add to the first digit. So AC is 15 units. Okay, I'll just say it here. AC is equal to 15 units because of the roundings. Okay, and that's our answer there. So that's 8.1. Moving on to 8.2. The last question for trigonometry. Okay, this paper has been relatively, well, the trig section, other sections also were fine. This paper has been, they were being really nice here, to be honest, because I know that there are November papers that were not like this. Okay, so that's a good thing. You guys just make sure you keep practicing with other exam papers as well. It's going to be very helpful. First, learn the concepts, learn everything on your own, really. Don't always wait for your teacher to teach it to you before you learn it. If you have access to a textbook, even online textbooks, learn the work first and then immediately start working on past exam papers, because that's where most of the work is really. Okay, those are the type of questions they will ask you in an exam setting. Okay, 8.2. Calculate how far the painter at E is from the top of the building. How far painter E is from the top of the building. So they just want you to find the length of ED. That's really what they want you to find, okay? How far the painter is from the top of the building. Okay. How do we find the length of ED? Well, the only way we can find ED right now, because we know what DC is, okay? That's 16 units. We can only find ED if we find out what EC is. Okay, so this is that whole Euclid thing. To find this, you must find that. To find that, you must find that. But you must not lose track or focus of what your final goal was. So let's look at this. How can we find EC? Okay, now already you know you can't use this. We're just going to have to remember that this is 15 units now. How can we use everything we know and what we found here to find EC? So there are two triangles, well, one triangle that EC is a part of. It's this, right? It's a 90-degree triangle, which is great. And there's something else they told us about that triangle. You see that they're giving you this angle over here. If this is 122 degrees, if you tilt your head this way, do you see that this is an exterior angle? Okay, the exterior angle of a triangle is equal to the sum of the opposite interior angles. But we're not just going to start finding things. We need a reason to find it. Okay, don't just start finding random things. That is one way to get lost within, these numbers. So to find this, the easiest way to find EC, okay, is because this is a right angle triangle, we can use trig functions. But here's the thing we would need to know. To use trig functions, or even the sine rule, well, trig functions really, the things we would need to know are the following. You would just need at least one angle and one available side, and you'd be able to find this. So the easiest angle here would be, we'd use this angle, the acute angle. Obviously, that's the angle you have to use if you're using trig functions. So you can relate it to EC, and then we need one available side. So I guess the side we can focus on finding can be AC. Okay. If you have this angle and you have AC and you need to find EC, you can just use trig, okay, trig functions like we did here. We had this angle, we had that side, we needed to find AC. And we were able to find that. Okay, I notice I called that side AC. It's BC that we need to find. Okay, how can we find BC? Let's look at this. The only triangle that can help us to find BC right now is this bottom triangle. So let us look for a way to find BC using this bottom triangle. Okay, so how do we find BC in this triangle? ABC. Okay, so with ABC, we can use, you see that they gave us an angle and a side opposite the angle. Okay, that is already hinting sine rule. Okay, it could also be cos rule, but honestly speaking, I just try to avoid using the cos rule. I don't like the way the formula looks. It's necessary, yes, but if we can avoid it, I just try to avoid it. Okay, the sine rule is just easier to work with. So with that, because we have this and the side opposite it, in order to find BC, what we would need is, we would need the angle A. If we have the angle A, right, BC is the side opposite the angle A, this angle in this bottom triangle, okay? Okay, so we've now jumped to finding BC to finding angle A. How can we find angle A there? The only way to find angle A is if we know, because we don't have much information here, we just have this and we have 15 units here. Okay, we can use this to our advantage. We can find angle B, this angle. If we find angle B, we can use the sine rule to help us to find angle B because we have the side opposite it. It's 15 units here. We have angle C and the side opposite it. So let's find angle B. Then using the sum of angles in the triangle, find angle A. Then use that to find BC. At that point, we can even use the cos rule if we want. Okay. And then finally, we can use that to find EC. And if we find EC, we can find DE. Okay, so it's just the whole road. That's why it's 7 marks. Makes sense. Okay, let's start. First thing we need to find is angle B. So how do we find angle B? We need to find an angle. We're using the sine rule. So in this triangle, because this is missing and we have the side opposite it, you're focusing on finding an angle. So put the sine of that angle first. So sine angle, I shouldn't call it angle B, it's not really angle B, it's angle ABC. Okay, let's be specific. ABC, right? Over, and the side is 15, is equal to, and then we are saying, here we are using these two, okay, this angle and this side. So we need to say sine 105.61 degrees over the side is 19. Okay, so let's just write this down and first find that angle ABC. Okay, so we wrote that down, and now we need to get rid of the 15 to get that, okay, as a subject. So you'd multiply both sides by 15, and so sine ABC would be equal to, when you multiply, that 15 goes to the numerator. So it's sine 105.61 degrees over 19, okay? And then to find that angle, you're going to use the second function of sine, really. Okay, so this is equal to shift sine or arc sine, and you're going to say 15 sine 105.61 degrees all over 19. Okay, how about I just leave it like that? I don't like to round off. I'm going to leave it like that for now, but I will just get like an angle just so that we can see what it is. Okay, so that angle is roughly, rounds up. Okay, so it's 49.50 degrees. Okay, 49.50 degrees roughly, but I'm also just going to remember that I have that. Okay, so now that we found this, right, it's just to put it here so that we know what it is. And about 49.50 degrees, check. What do we have to find in order to be able to get the value of BC? We would have to find this angle over here, and you can just use the sum of interior angles in a triangle to do that. So it's this angle BAC. So BAC is equal to 180 degrees minus 105.61 degrees minus 49.50 degrees. Okay, so just get that answer. And there we have our answer. Okay, so I just said minus ounce. Doesn't really matter, but it's fine. 24.89. I'm just going to keep holding on to that ounce button. Okay, so that's what we have for BAC. Okay, we'll hold on to that and let's just see. Now that we know that angle, we'll just put down, a value for it. What do we have to find next? Remember, the end goal is DE. So to find EC, we need one extra side, one additional side in this triangle over here. So let's go ahead and find BC. So we can use the sine rule to find BC. We're going to take this angle, okay, with this side, because it's the side we're looking for. And then you can take one that is already available. This angle with this side. Okay, let's go. So still going to write down what we're doing here. We are trying to focus on finding the side BC. So let's make the side the subject. So we'll put that as the numerator. BC this time over, and the angle that is paired with it is, I'm going to say sine 24.89 degrees. Okay, and that is equal to, and then again it's side over the angle this time. So sine of that angle, 19, and then sine 105.61 degrees. And then we will solve for BC. Okay, so this is what we have. And remember that we already have a recorded answer for this. But now look at what we're going to do. We're going to say to get rid of, or to leave BC on its own, you need to get rid of this. So you would multiply both sides by this number, sine 24.89 degrees. Now, because you're doing that, what happens is that's going to go to the numerator here. Of course, it will cancel here because if you multiply by it, it's going to cancel numerator and denominator. So it's going to go here. So it's going to be 19 sine that. Okay, so BC is therefore equal to 19 sine 24.89 degrees. Remember, we already have an answer we're holding on to for that, over sine 105.61 degrees. Okay, let's find BC. So now calculator, I'll be very careful with this. You guys can just use that ans button. Okay, I have to press equal to first. And then I'm going to put down my answer here. So it's a fraction and I'm saying 19 sine, and instead of saying 24 point that, I'm just going to say ans, okay, so that it uses that, over sine of 105.61 degrees. Okay, my calculator has to load now because the number is really long, okay. Okay, so that is 8.30. Okay, I'm just still leaving it like that, but I'm still holding on to that ans. Okay, let's hold on to that. We got BC. Okay, let's just remove all the things that we don't really need right now. So the angles we have, and now we have BC. So BC. Okay, we have this as 8.30. Okay, and that is in meters. Now we have to use that to find EC. So you're going to use trig functions here because this is a right angle triangle. So it's easier to use trig functions here. So the angle that you have, okay, and that's where we need to find this angle. The angle that we're going to have here is this acute angle here, right? And we have the side that is adjacent this acute angle next to this, that's BC. And the other thing that we're looking for is EC, which is the opposite side. So you have an adjacent and an opposite. So we're going to use tan here again. Okay, so tan. So next thing is we need to find this angle. We wouldn't need a calculator for that. That's fine. Do you see again? 122 is the exterior angle of this triangle. So the exterior angle is equal to the sum of the two opposite interior angles, meaning this angle plus 90 degrees gives you that. Meaning to find that angle, you say 122 degrees minus 90 degrees. Okay, and that's going to give you 32 degrees. So there, you can just tell them as well that angle CBE is equal to 32 degrees. Okay, so we have that down. And now that we know this is 32 degrees, this can help us to find EC. So this is the angle, that's the opposite, that's the adjacent side. So we're using tan. So tan of 32 degrees is equal to, the opposite side is EC, which is what we're looking for. The adjacent side is 8.3, which is BC. We don't have to call it BC, it's fine. Okay, so then we're going to make EC the subject. Okay, so to make EC the subject, multiply both sides by 8.3, 8.30. So that's going to give you EC is on its own now. But what happens when this multiplies here is it becomes the coefficient of tan. So 8.30 tan 32 degrees. And we just have to find this. Okay, so EC equals. So on your calculator, you can use ans. I'm just going to say equal to, and I'm going to say 8.30, which is my answer, right? So I'm going to say ans and then tan 32 degrees. And then just wait for it to get the answer. And that gives us 5 point, okay, so that rounds up to 9. And so that's 5.19 units, right, that we have. And now that we have EC, finding DE is very simple. Okay, so finding DE, because this is 5.19, do you see that the entire length of DC is 16 units, right? And you know that EC is 5.19. So CD minus EC finally gives you that length DE. Okay, so we're just going to say to find the length of DE, therefore DE is equal to 16 minus 5.19 units, which you really do not need ans for that. I'm just a little too careful sometimes. Okay, so it's equal to 16 minus our final answer, and that would just be our answer. And our answer is 10.81 units. And that is it. DE is equal to 10.81 units. And that is it for trigonometry for paper 2. And I will see you guys in Euclidean geometry.